What lies beyond the observable universe? This question has captivated the minds of scientists, philosophers, and curious individuals alike for centuries. Our observable universe extends an astonishing 93 billion light-years across, yet this is only a fraction of what might actually exist. From speculative multiverse theories to the possibility of different physical laws in distant regions of space, we stand on the edge of profound ideas that could reshape our entire understanding of reality. As we venture beyond our cosmic horizon, we embark on a journey that challenges our comprehension of the cosmos and what truly lies in the unseen vastness. The observable universe is defined as the portion of the universe we can detect, stretching out to the farthest reaches where light has traveled since the beginning of time. This boundary is set by the finite speed of light, which races through space at 300,000 kilometers per second. Because light from distant objects takes time to reach us, our view of the universe is limited to regions from which light has had enough time to travel to Earth. Currently, this means we can observe objects as far as 8 billion light-years away, providing a glimpse into the past and revealing objects that are over 13 billion years old. But this limit isn't just a matter of distance. It is deeply tied to the very fabric of space and time itself. Since the Big Bang, the universe has been expanding, and with it, the maximum distance we can observe grows. However, due to the accelerated rate of expansion, certain regions of the universe are moving away from us faster than the speed of light. As a result, these areas will forever remain beyond our reach, as light from them will never have the chance to reach us. This phenomenon is referred to as the cosmological horizon, the boundary beyond which the universe remains invisible. Even though these regions are theoretically part of the same universe, they remain utterly inaccessible to us due to the relentless expansion of space itself. Beyond this horizon lies an uncharted realm, an expanse of galaxies, stars, and cosmic phenomena that are completely invisible to our instruments. While these distant regions belong to the same cosmos, their isolation reminds us of the limitations inherent in our observational reach, sparking endless curiosity about what might exist in the infinite reaches we can never touch. Our understanding of the observable universe has evolved dramatically, paralleling advancements in technology, mathematics, and scientific theory. In the earliest days, humans viewed the cosmos through a geocentric lens, with Earth believed to be the center of all celestial movements. Observations were limited to what the naked eye could perceive, and the universe seemed like a static, unchanging expanse. However, this narrow view began to shift with the revolutionary work of astronomers like Copernicus, who proposed the heliocentric model, placing the sun at the center of our solar system. This idea broadened our perspective, marking the first step in expanding our understanding of our place in the vast cosmos. The invention of the telescope in the early 17th century would forever change humanity's relationship with the stars. Galileo Galilei, armed with this new tool, was able to observe the night sky in unprecedented detail, revealing the craters of the moon, the moons of Jupiter, and the phases of Venus. These discoveries shattered the long-held belief in a perfect, unchanging heavens and laid the foundation for modern astronomy. As telescopes grew more powerful, so did our ability to peer deeper into the universe. It was in the early 20th century that Edwin Hubble made a groundbreaking discovery. The universe was expanding. This revelation revolutionized our understanding of the cosmos and opened the door to new questions about its size, age, and ultimate fate. Today, with advanced technologies like the Hubble Space Telescope and missions such as the Cosmic Background Explorer, we have glimpsed deeper into the universe than ever before. Observing the cosmic microwave background radiation, an essential remnant of the Big Bang, has provided invaluable insights into the early stages of the universe. From this, scientists developed the Big Bang theory, which posits that the universe began in an intensely hot, dense state and has been expanding ever since. This theory has reshaped our view of cosmic evolution, illustrating how the universe has cooled and expanded from its fiery origins into the vast, cooler cosmos we observe today. However, the journey of discovery is far from over. Each technological advancement in observational tools and methodologies brings new insights that refine or challenge existing theories. What we thought we knew about the universe is constantly being tested, revealing layers of complexity that we never before imagined. Our current understanding of the observable universe is far from the final word. As we continue to push the boundaries of cosmic knowledge, we come ever closer to grasping the full scale of the cosmos. But even as our instruments improve, we are left with the humbling realization that vast realms of space will always remain hidden from view, forever beyond our reach. Current estimates place the size of the observable universe at approximately 93 billion light-years in diameter. This measurement accounts for the vast distances light has traveled since the Big Bang, which occurred around 13.8 billion years ago. Yet, even this mind-boggling figure represents just a fraction of the universe that lies beyond our reach. What mysteries lie in the unexplored expanses? Could other regions of space host entirely different physical laws? Is there a multiverse where countless other universes coexist with our own, each with its own set of rules? These are questions that challenge the very core of human curiosity, urging us to think beyond the limits of the observable and into the unknown. As we push the boundaries of what is visible and detectable, we not only expand our understanding of the cosmos, but also our understanding of ourselves. However, as the universe continues to expand, the regions from which light has traveled to reach us are increasingly moving farther away. These regions, which once emitted light that we could observe, have now receded beyond their original distances due to the dynamic nature of the cosmos. As a result, the observable universe is not a fixed, static boundary. In fact, as the universe stretches and grows, so does our ability to peer further into the vast reaches of space. However, this ability is constrained by the fundamental speed of light. This means that the observable universe represents only a small fraction of the universe as a whole. New technological breakthroughs in astronomical instruments and observational methods are allowing us to glimpse even further into the depths of space. With each new advancement, astronomers refine their estimates of distances, enhancing our understanding of the cosmic expanse. This ever-growing body of knowledge is continually reshaping our view of the universe. The observable universe is only a tiny fraction of what may be the far larger or even infinite universe that stretches beyond our sight. Some theories propose that beyond the reaches of our observation, there could be regions so distant that the light from those areas has not yet had time to travel to us. This raises tantalizing possibilities of a cosmos filled with vast, uncharted territories waiting to be discovered. Our current estimates of the universe's size and structure are far from fixed and continue to evolve as we deepen our understanding of cosmic expansion and improve our observational techniques. Each new discovery offers a fresh insight into what lies beyond our observational limits and inspires endless curiosity about the unseen realms of the universe. Measuring distances within the observable universe is an intricate and complex task. Astronomers use a range of methods, each suited for different scales of cosmic distances. For relatively nearby objects, one of the most effective techniques is parallax. This method involves observing the apparent shift of a nearby star against the backdrop of more distant stars as Earth orbits the Sun. By measuring this shift, scientists can calculate the distance to the star using simple geometry. This technique works best for stars within a few hundred light years of Earth. As the distances grow larger, astronomers turn to what are known as standard candles. These are objects with a known intrinsic luminosity, such as specific types of supernovae or certain variable stars called Cepheid variables. By comparing the observed brightness of these objects with their intrinsic luminosity, scientists can determine how far away they are. Supernovae, in particular, are invaluable because they are extraordinarily bright and can be observed across vast distances. This enables astronomers to measure distances stretching over billions of light years. For even more distant objects, scientists rely on a phenomenon known as redshift. This occurs when an object moves away from us, stretching the wavelengths of light it emits. The further an object is, the faster it appears to be receding, due to the expansion of the universe. By analyzing the degree of redshift, astronomers can estimate distances based on the relationship between redshift and distance, as outlined by Hubble's law. This method has become essential for mapping the large-scale structure of the universe and understanding its expansion. By combining these various techniques, astronomers are able to build a comprehensive framework for measuring distances across the cosmos. With ongoing advancements in technology and observation, our ability to accurately measure these colossal expanses of space continues to improve, providing us with an increasingly detailed picture of the universe. Each breakthrough adds another layer to our understanding, allowing us to refine our grasp of the universe and our place within it. One of the most significant areas of research is the observation of the most distant objects in the universe. Among these are galaxies and gamma-ray bursts, some of which originated when the universe was still in its infancy, just a few 100 million years after the Big Bang. One of the farthest known galaxies is GN-Z11, which was observed at a redshift of approximately 11.1. This corresponds to a distance of about 13.4 billion light-years from Earth. GN-Z11 offers invaluable insights into the conditions of the early universe, providing a rare glimpse into the formation and evolution of galaxies during the universe's formative years. Gamma-ray bursts, which are incredibly energetic explosions, are another fascinating category of distant objects. These bursts are so powerful that they can outshine entire galaxies. The most distant gamma-ray burst ever detected, GRB 2011-21A, was observed at a redshift of around 1510-2. This explosion occurred when the universe was only about 500 million years old, presenting a unique opportunity to study cosmic phenomena from an era when the first stars and galaxies were beginning to form. Additionally, space-based telescopes like the Hubble Space Telescope and others have provided us with images of ancient massive galaxy clusters, such as MAX J1149, 5 plus 2220. These galaxy clusters extend our view of the universe's distant past, allowing astronomers to study not only the early formation of galaxies, but also the distribution of dark matter. These findings offer a glimpse into the complex processes of cosmic evolution. These extraordinary observations highlight the incredible capabilities of modern telescopes and the advancements in technology that make them possible. Each discovery of increasingly distant objects helps scientists piece together the timeline universe, providing invaluable data on its formation and the processes that have shaped the cosmos we observe today. Beyond the cosmic horizon of our observable universe lies a vast, enigmatic expanse, a region so distant that it remains cloaked in mystery. This immense stretch of space consists of realms that are too far away for light, the most reliable messenger we have, to have reached us since the dawn of time. This limitation restricts our capacity to see or measure what lies beyond our observational boundary. While this boundary is a hard limit for our instruments, it has not stopped scientists from speculating about the unimaginable wonders that might exist in these unseen regions. Could there be galaxies, stars, and other celestial structures that mirror those we already know, yet remain forever beyond our reach? This tantalizing idea stretches the imagination and raises the question, are we truly aware of all that the universe has to offer, or is there a vast hidden reality that we are blind to? Theoretical models suggest that the universe may extend infinitely, far beyond the point where our observational capabilities falter. If this hypothesis holds true, entire regions of space could be teeming with cosmic phenomena, galaxies, nebulae, and stars, strikingly similar to those within our observable universe. In such a scenario, countless galaxies, each potentially harboring billions of stars and perhaps even more planets, could exist in a realm we cannot yet probe. This expansive thought ignites curiosity, prompting profound questions about the nature of existence. Could there be other forms of life thriving in these distant galaxies, unseen and unimagined by our current technology? Moreover, some daring theories venture further still, exploring the possibility of a multiverse, where our universe is merely one of many distinct coexisting universes, each with its own set of physical laws and constants. While this concept remains speculative and a subject of heated debate among physicists, it opens up fascinating and mind-bending questions about the fundamental nature of reality itself. Could the universe we know be just one piece of a far larger, more complex cosmic mosaic? If the multiverse theory is correct, it suggests that there could be other universes with entirely different forms of matter, laws of physics, and even dimensions of space and time, each one a reflection of alternate realities. The very idea challenges our understanding of existence and raises profound questions about our place in the grand scheme of all that is. In contemplating the regions beyond our cosmic horizon, we are reminded of the profound limits of our knowledge. These vast, unseen areas serve as a humbling reminder that there is much about the cosmos that remains unknowable, at least for now. Yet, each leap forward in technology, each refinement in our observational tools, brings us closer to answering some of these great questions. Our curiosity about these uncharted territories of space continues to grow, and with it, so does the quest to understand what exists beyond the visible, pushing the boundaries of exploration further into the great unknown. Could it be that the regions beyond our observation contain galaxies or star systems with structures or compositions that are entirely foreign to us? Perhaps galaxies have formed under conditions we cannot yet comprehend, leading to cosmic landscapes filled with bizarre and exotic celestial phenomena. The possibilities are as limitless as the cosmos itself. Some scientists even speculate that these distant realms may harbor entirely new kinds of stars, planets, and perhaps even forms of matter or energy that are completely different from what we've encountered in the observable universe. There's also the tantalizing possibility that the physical laws themselves could differ in these unseen areas. If the multiverse theory holds any weight, then entire universes could operate according to entirely different sets of physical rules. Imagine stars burning with different nuclear processes or gravity behaving in entirely unexpected ways. Perhaps in these regions, the fundamental forces of nature, such as electromagnetism or the strong and weak nuclear forces, are expressed in ways we cannot yet imagine. Such variations might give rise to exotic forms of energy and matter, possibly even entirely new particles that have no counterpart in the universe we observe. Even darker, deeper mysteries await in the form of dark matter and dark energy, the invisible substances that make up the majority of the universe's mass energy content. While scientists have a reasonable understanding of how dark matter affects observable galaxies, the behavior of dark matter beyond the cosmic horizon remains one of the greatest unknowns. What if the distribution and properties of dark matter vary in these unseen realms? Could different concentrations of dark matter lead to the formation of strange, never-before-seen celestial bodies or structures? Even more intriguing, could these variations influence the expansion of the universe itself, altering the rate at which the cosmos grows and reshaping the fate of everything we know? In a universe of such vast potential, each discovery within the observable universe serves as both a triumph and a reminder of our limitations. It sparks an insatiable curiosity about what lies just beyond our reach. The notion that beyond the horizon, reality itself might differ in ways we cannot even comprehend fuels the imagination and drives the unyielding human quest for knowledge. We yearn to understand how the cosmos works, not just in the parts we can see, but in the great, mysterious regions beyond our perception. One critical theory that sheds light on the nature of the cosmos is cosmic inflation, a hypothesis proposing that in the earliest moments after the Big Bang, the universe expanded at an astonishingly rapid rate, stretching from subatomic scales to vast cosmic distances. This theory emerged to resolve several major puzzles about the uniformity of the observable universe, particularly the surprisingly consistent distribution of galaxies and matter across vast expanses. According to the inflationary model, this rapid expansion smoothed out any irregularities in the early universe, setting the stage for the relatively uniform universe we observe today. What does cosmic inflation mean for the regions beyond our observable universe? The significance lies in the fact that if inflation happened as predicted, these distant areas may have experienced the same rapid expansion, leading to uniformity even in regions far beyond our reach. However, because inflation stretched the universe so dramatically, vast regions of space may have expanded beyond the limits of what we can observe, creating a scenario where enormous portions of the universe are forever inaccessible to us. Even if variations in structure and density exist in these distant regions, they are hidden from our eyes because of the finite speed of light and the boundless nature of cosmic expansion. As we continue to peer further into the universe, we are constantly reminded that there are vast stretches of the cosmos we will never see, at least not in our lifetime. Yet the quest for knowledge persists, pushing the boundaries of what we know, opening new realms of possibility, and expanding our understanding of the universe. Whether through advances in technology or breakthroughs in theoretical physics, we will continue to ask what lies beyond the cosmic horizon in the vast, unknown expanses that remain just out of reach. In recent years, the theory of cosmic inflation has opened up a wide array of questions about the true scale and structure of the universe. At its core, inflation proposes that the universe experienced an exponential expansion in the earliest moments after the Big Bang, stretching space-time to incredible sizes in a fraction of a second. But what if inflation didn't just apply to the region of the universe that we can observe? What if it occurred on a grander scale, affecting vast swathes of space beyond our reach? This notion brings with it the mind-boggling possibility of a vast cosmic landscape that extends far beyond the limits of our observable universe. If this theory holds true, we are living in just one small section of a much larger structure, one that might be dotted with countless pocket universes, each forming its own distinct bubble. Each of these bubbles could have undergone its own inflationary process, leading to the birth of universes with different properties, rules, and physical constants. These hypothetical bubble universes could potentially operate under entirely different laws of physics, challenging everything we think we know about the nature of reality. The concept of bubble universes is deeply tied to the broader theory of the multiverse, a framework suggesting that what we call the universe is just one of many. In this context, our universe might be just one bubble in an ever-expanding cosmic foam. Each of these bubbles might be completely separate from one another, not only in their physical makeup, but in their fundamental laws of nature. The possibility that other regions of the universe could have different fundamental constants, such as the strength of gravity or the mass of fundamental particles, suggests a strikingly diverse and potentially infinite cosmos, where the laws of physics as we understand them are not universal, but region-specific. Such variations could lead to completely different cosmic environments. Imagine, for example, a universe where the cosmological constant associated with dark energy and the expansion of space takes on a different value. In one bubble, this constant could be so strong that space-time is expanding rapidly, leaving little room for structure to form. In another, it could be so weak that gravity causes all matter to collapse in on itself. These different values could dictate not only how galaxies, stars, and other cosmic structures form, but also whether life, if it exists, can take shape under those conditions. While the idea of bubble universes stretches the limits of imagination, it is not entirely without foundation. The theory of cosmic inflation, first proposed by physicist Alan Guth in the early 1980s, offers a framework in which inflation could have created pockets of space-time that inflated at different rates. Some regions of space might have ceased expanding while others continued, thus creating separate domains with distinct characteristics. This theory points to the possibility of a multiverse, where each universe is isolated with its own set of physical laws. However, despite the allure of these ideas, there is still no direct observational evidence to confirm the existence of bubble universes. The question remains speculative, and scientists are actively searching for clues that could support this hypothesis. One potential way to detect the presence of other universes lies in the study of the cosmic microwave background radiation, CMB. This faint afterglow of the Big Bang could carry subtle imprints of events from the inflationary period. If our universe has collided with another bubble universe, it might leave behind observable signatures in the CMB, providing the first direct evidence of the multiverse. Even if we cannot directly observe these realms, the idea of bubble universes forces us to confront profound questions about the nature of the cosmos. It challenges our understanding of the very fabric of reality. What does it mean to exist in a universe where our laws of physics might not be universal, but localized to our bubble? Could there be realms where entirely different forces or particles exist, radically different from those we know? Could there be life forms and even civilizations that operate under entirely different rules of physics? These possibilities ignite our curiosity and imagination, pushing us to rethink our place in the universe. The theoretical framework behind bubble universes also raises intriguing questions about the potential diversity of realities. If different bubbles can have different laws of physics, what might that imply about the nature of matter itself? In one universe, atoms might form differently, or perhaps entire new forces could emerge, forces that we are completely unaware of. This suggests that there could be realms with entirely different forms of energy or matter, and that life, if it exists in such realms, might not even resemble anything we understand as life. One fascinating possibility is the variation in the fundamental forces that govern all interactions in our universe. For example, in some bubble universes, gravity might be stronger or weaker, or electromagnetism might behave differently. Such variations could lead to entire galaxies that evolve in radically different ways, forming strange structures or even behaviors that defy our current understanding of physics. In some universes, even the fundamental particles that make up the building blocks of matter could be entirely different, giving rise to a completely new physics. However, despite its speculative nature, the concept of bubble universes pushes the boundaries of scientific inquiry. Even in the absence of direct evidence, scientists continue to investigate the potential for different physical laws in regions beyond our cosmic horizon. These investigations not only help us understand our universe, but also expand the very idea of what reality might encompass. As we explore these possibilities, we are forced to reconsider what we know about the universe, and by extension, about ourselves. In fact, the very idea of a multiverse forces us to confront the limitations of human knowledge. Our current understanding of physics is based on the assumption that the laws of nature are the same everywhere and always. But the multiverse hypothesis suggests that our universe, with its specific constants and physical laws, is just one tiny corner of a much larger, much more complex reality. While these theories remain speculative, they open the door to new ways of thinking about the cosmos. Perhaps the universe is not just a single entity, but a sprawling, interconnected landscape with multiple regions, each operating under its own set of rules. This idea forces us to grapple with fundamental questions about existence itself. What are the ultimate rules that govern all of reality? And if we are just one bubble in an infinite expanse, what does that tell us about our significance in the grand scheme of things? Finally, in the realm of quantum mechanics, the many worlds interpretation offers yet another twist on the multiverse hypothesis. Proposed by physicist Hugh Everett in the mid-20th century, the many worlds interpretation suggests that every quantum event, every time a particle is measured or observed, splits the universe into multiple parallel realities. In this view, each potential outcome of a quantum event occurs in its own separate universe, creating an ever-expanding multiverse of parallel realities, each of which is equally real but completely separate from the others. This interpretation of quantum mechanics challenges our conventional understanding of reality. It suggests that rather than a single fixed outcome arising from each quantum event, there is a branching of possibilities, with each branching universe representing a different outcome. This idea may seem fantastical, but it raises important questions about the nature of observation, measurement, and reality itself. As science continues to probe the deepest mysteries of the universe, the idea of a multiverse, whether in the form of bubble universes, parallel realities, or other exotic configurations, remains one of the most compelling and mind-expanding possibilities in theoretical physics. It offers a tantalizing glimpse into a cosmos far more complex and vast than we ever imagined, where the boundaries of what we know are constantly being pushed, and where the very nature of existence may be far stranger than we could ever have hoped to understand. The many worlds interpretation, MWI, of quantum mechanics stands as one of the most thought-provoking and radical ideas in theoretical physics, proposing a vision of reality where every possible outcome of a quantum event actually occurs, but in separate, non-communicating branches of the universe. According to this interpretation, every decision or random event creates a branching point in the fabric of reality, giving rise to a multitude of parallel universes. In essence, each time a choice is made or a quantum measurement is taken, a new reality unfolds, generating an infinite number of possible worlds. Take, for example, something as simple as flipping a coin. In one universe, the coin lands on heads. In another, it lands on tails. These two outcomes exist simultaneously in separate universes, each one real in its own right. The key idea here is that rather than the universe collapsing into a single outcome, as other quantum theories suggest, every possible result coexists in a vast, branching multiverse. One of the most captivating aspects of the many worlds interpretation is its handling of the notorious problem of wave function collapse, a long-standing debate in quantum mechanics. Traditional quantum theories often struggle with the question of what happens when a wave function, a mathematical description of quantum probabilities, collapses to a single outcome upon observation. The many worlds interpretation sidesteps this dilemma entirely. Instead of collapsing into a singular state, the universe splits, allowing all potential outcomes to play out in different branches of reality. This radical departure eliminates the need for the observer to play a special role, thereby bypassing several of the philosophical and conceptual issues tied to the measurement problem in quantum physics. Within this view, reality becomes a sprawling, intricate network of branching paths where every decision, no matter how small, gives birth to a new universe. Whether it's the flip of a coin, the movement of a particle, or the outcome of a quantum measurement, each quantum event generates its own unique parallel universe. This means that not only do all possible outcomes coexist, but they are all equally real. None of them any more or less significant than the others. Despite its intriguing appeal, the many worlds interpretation remains one of many competing theories that attempt to explain the strange and counterintuitive behavior of quantum systems. However, it offers a fascinating lens through which we can reconsider some of our deepest assumptions about reality, existence, and the very nature of time. For instance, it challenges conventional ideas of determinism and free will, suggesting that the choices we make may not just affect the world we experience, but also give rise to entirely new realities. It also invites us to reconsider our understanding of time itself, as every quantum event creates a branching moment that might unfold in an entirely different direction, at least in some version of reality. In this sense, the many worlds interpretation acts as a gateway to broader philosophical questions, ones that transcend the boundaries of physics and delve into the very fabric of existence. As scientists continue to explore the deep implications of quantum mechanics, the many worlds interpretation continues to stand as a bold and captivating possibility, pushing the boundaries of what we know and challenging us to rethink the nature of the universe on both a theoretical and existential level. The concept of parallel universes, at the heart of the many worlds interpretation, is also deeply entwined with the broader framework of multiverse theory. This theory proposes that beyond the limits of our observable universe, there exists an immense collection of universes, each with its own unique properties, laws, and physical constants. While the term parallel universes is often used to describe alternate realities that run alongside our own, multiverse theory encompasses a much wider range of possibilities, including entirely different structures and forms of universes that may not even obey the same fundamental principles as our own. Within the context of multiverse theory, the existence of parallel universes is just one of several possible models. A well-known approach draws from the many worlds interpretation of quantum mechanics, which asserts that every quantum event leads to the creation of a new universe to account for all possible outcomes. This branching process results in an interconnected web of parallel realities, where each potential decision or random event spawns a new universe that unfolds in its own distinct way. Another key facet of multiverse theory arises from cosmological models, particularly those linked to the concept of cosmic inflation. In this scenario, our universe was not the only one to undergo inflation. It was simply one of many regions that experienced rapid exponential expansion. Each of these expanding regions could have followed different paths, leading to variations in the fundamental laws of physics, the constants of nature, and even the structures of space and time itself. Over time, these regions could evolve into distinct, independent universes, each governed by its own set of rules and characteristics. This idea of an eternally inflating multiverse, where countless universes emerge from a singular, pre-existing quantum vacuum, proposes a view of the cosmos that is far more vast and varied than previously imagined. Within this framework, parallel universes are just one possible outcome of the interplay between quantum mechanics and cosmological inflation. The result is a multiversal landscape that stretches the boundaries of imagination, one where reality itself is an endless array of interconnected and ever-evolving possibilities. Thus, the many worlds interpretation and multiverse theory together offer a radical rethinking of the universe, suggesting that reality is far more complex and mysterious than we could have ever imagined. Whether through the branching paths of quantum events or the endless expanse of eternally inflating universes, these theories propose a reality teeming with countless possibilities, each one existing alongside the other in a grand multiversal tapestry. The concept of the multiverse, suggesting the existence of multiple, perhaps infinite universes beyond our own, has long captured the human imagination. Some theories delve into this notion, exploring frameworks like the string theory landscape, which proposes that our universe is only one possibility among a vast number of others. In this model, an immense array of potential vacuum states gives rise to a multitude of universes, each with different fundamental forces and particle types. These universes could operate under entirely unique physical realities, potentially supporting diverse configurations of space-time itself. Despite the varying details across theories, a common thread unites them: the idea that our universe is just one of many. This shared vision invites profound questions about existence, pushing us to reconsider not only the universe but also the very nature of life itself. The exploration of parallel universes within the broader framework of the multiverse sparks imaginative inquiries that extend well beyond science fiction. It opens the door to the possibility of vastly different experiences across multiple realms, where realities could be vastly different from our own. From this perspective, the multiverse challenges our understanding of what is possible, suggesting that existence, in all its forms, might be far more varied than we can currently grasp. Within this infinitely complex cosmic tapestry, theories like eternal inflation push the boundaries of our knowledge, proposing new ways to think about the birth and evolution of universes. Eternal inflation extends the traditional model of cosmic inflation, which describes the rapid expansion of the universe following the Big Bang. While cosmic inflation suggests a universe that grew exponentially in a very short time, eternal inflation posits that this expansion process doesn't end everywhere simultaneously. Instead, certain regions of space can continue inflating indefinitely, while others stop inflating and settle into what we observe as distinct, stable universes. In essence, this constant state of inflation could give birth to countless new universes, each one potentially governed by different physical laws or constants. These bubble universes may emerge continuously, each one representing a unique snapshot of reality, formed under its own set of conditions. Eternal inflation reinforces the idea of a vast, perhaps infinite multiverse by suggesting that our observable universe is merely one small patch within an expansive cosmic landscape. According to this theory, regions surrounding our universe could have entirely different physical conditions, perhaps with distinct structures, forces, or even dimensions of time and space. Moreover, the continuous nature of this inflationary process implies that this is not a one-time event, but a dynamic and ongoing system that continually shapes the cosmos. In this way, the theory of eternal inflation offers a compelling framework for understanding the complexities of the universe, radically transforming our conception of reality. It challenges the conventional view of the universe as singular and fixed, proposing instead a cosmos teeming with countless possibilities and parallel realms, each potentially governed by its own set of rules. On another front, the landscape multiverse theory, arising from the complex realm of string theory, offers another profound perspective on the multiverse. String theory, in an attempt to reconcile quantum mechanics with general relativity, posits that the fundamental particles of the universe are not point-like, but rather one-dimensional strings. In this framework, the landscape refers to the extraordinary number of possible vacuum states that could exist, each giving rise to distinct physical realities. These vacuum states define the properties of a given universe, determining its physical constants, dimensions, and even its fundamental forces. One of the most intriguing aspects of string theory is its proposition that additional dimensions exist beyond the familiar 3 of space and 1 of time. These dimensions, however, are compacted and not directly observable. In the landscape model, the way these extra dimensions are compactified, folded into tiny spaces, can lead to an astonishing variety of possible universes. Estimates suggest that the number of distinct vacuum states could be on the order of 10 to the power of 200, an incomprehensibly large number. Each configuration within this landscape results in a unique set of physical laws, such as the strength of gravity or the masses of elementary particles. This means that our universe, with its specific conditions, is just one possibility among a nearly infinite number of potential realities. In some of these universes, conditions might be suitable for life as we know it. In others, the fundamental forces may not align in a way that supports the emergence of complex structures. This realization suggests that the properties we observe in our own universe, things like the specific strength of gravity or the masses of certain particles, are not universal truths, but rather particular outcomes shaped by the vacuum state we occupy. This raises profound questions about what fine-tuning means in the context of our universe. Why do the physical constants seem so perfectly calibrated for life? One potential answer is that in a multiverse with so many possible configurations, it becomes statistically likely that at least one universe would evolve to support life. In this way, the existence of multiple universes could offer an explanation for the seeming improbability of life in our own universe. The landscape multiverse theory, drawing from the principles of string theory, offers a rich and intricate view of the cosmos. It suggests that the universe we experience is just one of an almost unimaginable variety of realities, each governed by different laws and shaped by its own unique conditions. However, detecting evidence of other universes is no simple task. It presents one of the most significant challenges in modern cosmology, pushing the limits of our current understanding and technological capabilities. The implications of this theory, if proven, would dramatically shift our understanding of reality itself. It would not only redefine the concept of the universe, but also expand the horizons of human knowledge, unveiling a cosmos far more intricate and diverse than we could ever have imagined. In conclusion, both eternal inflation and the landscape multiverse theory present compelling arguments for a vast, diverse, and ever-evolving cosmos. They challenge our deepest assumptions about the universe, inviting us to contemplate a reality filled with infinite possibilities. Whether these theories can be proven or not, they offer an exciting glimpse into the potential future of cosmological discovery, where the boundaries of space and time may stretch far beyond what we have yet to understand. The notion of a multiverse, an infinite ensemble of parallel universes, has captivated the imagination of scientists and philosophers alike for decades. At the heart of this bold idea lies a concept known as cosmic inflation. According to this theory, shortly after the Big Bang, our universe underwent an extraordinary and rapid expansion, a period of exponential growth. This expansion was so rapid that it could have resulted in what are known as bubbles of space-time, each of which could potentially give rise to its own separate universe, governed by distinct physical laws and constants. While direct evidence of these other universes remains elusive, one proposed method for testing their existence involves examining the cosmic microwave background, CMB radiation. This faint afterglow left behind from the Big Bang carries vital clues about the very beginnings of our universe. Scientists meticulously analyze this radiation, looking for any anomalies or unusual patterns that could suggest interactions between our universe and others. For example, if two universes were to collide, it is theorized that such a monumental event could leave a telltale mark on the CMB. Detecting such irregularities would require highly advanced instruments and precise data interpretation, but with recent advancements in observational technology, this once impossible task is inching ever closer to becoming reality. In addition to this, there is another avenue of exploration in the pursuit of a multiverse. String theory. This revolutionary framework proposes that our universe may not be limited to the familiar four dimensions of space and time, but instead could consist of additional dimensions beyond our perception. Some physicists suggest that these extra dimensions could serve as gateways, allowing for the interaction of parallel universes. Experimental research, such as that conducted at particle accelerators, is actively seeking evidence of these hidden dimensions. If such dimensions were to be detected, it could provide a compelling case for the existence of a multiverse. Even the enigmatic force known as dark energy, responsible for the accelerating expansion of our universe, raises further questions about the nature of the cosmos. If dark energy behaves differently across multiple universes, understanding its properties could reveal crucial insights into the fabric of the multiverse. Despite the limitations imposed by current technology, researchers continue to explore both theoretical and observational avenues, pushing the boundaries of human knowledge. With each new discovery, the possibility of a multiverse grows ever more tantalizing, offering the potential for groundbreaking revelations about the true nature of reality itself. As we look beyond the theoretical, our observable universe presents a remarkable array of colossal structures, demonstrating the immense scale and complexity of cosmic architecture. Among these giants are galactic superclusters, enormous groupings of galaxies bound together by gravity. One of the most prominent superclusters is the Laniakea supercluster, which is home to approximately 100,000 galaxies and spans more than 150 million light-years. This mind-boggling scale provides a glimpse into the vastness of the cosmos and the intricate organization of matter on the largest scales. Beyond superclusters, even more awe-inspiring structures exist: cosmic filaments. These are vast, interconnected strands of galaxies and dark matter, forming a web-like structure that stretches across the universe. The Sloan Great Wall, one of the most significant examples, is a cosmic filament that extends for over 100 million light-years. These colossal filaments weave together galaxies, creating an intricate network that fills the universe. Between these filaments lie enormous voids, vast, empty expanses where few galaxies exist, highlighting the uneven distribution of matter across the cosmos. One of the most extraordinary discoveries in this cosmic landscape is the Hercules Corona Borealis Great Wall, the largest known structure in the observable universe. This supercluster stretches a staggering 10 billion light-years across, challenging our understanding of cosmic evolution and the forces that govern the formation of such immense structures. The discovery of this vast cosmic formation has profound implications for our understanding of how regions of space coalesce and the physical mechanisms that drive such processes. The study of these immense structures offers us a window into the underlying forces that have shaped our universe over billions of years. As scientists continue to delve into these phenomena, they uncover new insights about the fundamental nature of matter, energy, and the very fabric of space-time. The pursuit of knowledge about these cosmic giants fuels our insatiable curiosity and deepens our desire to understand our place in this grand, ever-expanding cosmic tapestry. The formation of galaxy filaments and the vast cosmic web is the result of gravitational interactions and the complex dynamics of dark matter. In the early stages of the universe, shortly after the Big Bang, matter began to clump together under the influence of gravity, creating regions of higher density. Dark matter, an invisible yet pervasive force, played a pivotal role in this process. Though it does not interact with light, its gravitational pull has a profound impact on the distribution of galaxies throughout the cosmos. As regions of slightly higher density began to form, they attracted more matter, leading to the creation of galaxies and clusters of galaxies. Over time, these gravitational wells deepened, resulting in the formation of cosmic filaments, long, elongated structures that link vast clusters of galaxies. These filaments create a vast, interconnected network that spans the universe. As the universe continues to expand, the dynamics of matter evolve, with galaxies within these filaments drawn toward one another, eventually forming larger clusters at the intersections of these cosmic strands. This intricate cosmic web hints at a beautifully orchestrated arrangement of matter and energy, shaped by the fundamental forces of gravity and dark matter. Observational data from telescopes, combined with powerful computer simulations, have further advanced our understanding of this process. Large-scale surveys, such as the Sloan Digital Sky Survey, have enabled astronomers to map these vast cosmic filaments, providing crucial insights into the structure and evolution of the universe. These simulations and observations illustrate how dark matter influences the growth of the cosmic web, revealing the dynamic processes that have shaped the universe into the remarkable structure we observe today. Among the most striking features of the universe's large-scale structure are the vast cosmic voids, immense regions of space that are nearly devoid of matter. These voids can stretch for tens to even hundreds of millions of light years, offering a striking contrast to the densely packed galaxies and clusters found elsewhere. While these voids may appear empty at first glance, they are not completely devoid of matter. In fact, they often contain faint galaxies, dark matter, and diffuse gas, albeit in much lower concentrations than their denser counterparts. The existence of these cosmic voids offers important insights into the overall structure of the universe. The distribution of voids, along with their surrounding filaments and galaxy clusters, reveals the intricate web-like architecture of the cosmos. These voids are essential to our understanding of cosmological evolution, as they provide a unique perspective on the early universe and the processes that led to the formation of galaxies and large-scale structures. By studying these voids, researchers can uncover valuable clues about the density fluctuations that occurred in the universe's infancy, helping to shed light on the origins of cosmic structure. Through these combined efforts, observational, theoretical, and computational, we are gradually piecing together the story of the universe's grand design. From the formation of filaments to the discovery of colossal superclusters, the study of the cosmos reveals an intricate, interconnected structure that reflects the profound influence of gravity, dark matter, and the fundamental forces that have shaped our universe since its inception. The quest for knowledge about the multiverse and the vast, invisible forces at work within our universe continues to captivate our collective imagination, urging us ever forward in our search for understanding. The study of cosmic voids offers profound insights into some of the most significant and enigmatic phenomena in the universe. These vast expanses of empty space, devoid of galaxies and matter, not only challenge our current understanding of cosmic structure, but also provide essential clues about the forces shaping the universe's evolution. The behavior of these voids, particularly in relation to dark energy, sheds light on one of the greatest mysteries in modern astrophysics: the accelerated expansion of the universe. Dark energy, a force thought to permeate all of space, is responsible for driving this accelerated expansion. Understanding how matter behaves within and around cosmic voids could provide critical data on how dark energy influences the universe's growth. For example, by observing the movement of galaxies that reside near or within these voids, scientists can infer the distribution of mass throughout the cosmos. This, in turn, may reveal how dark energy is shaping the large-scale dynamics of the universe. The interactions of galaxies and the way they cluster or drift apart within these voids offer invaluable insight into the nature of cosmic expansion. The study of cosmic voids also serves as a laboratory for testing and refining cosmological models. As we advance in observational technology, these voids allow researchers to challenge and validate fundamental theories, including the widely accepted standard model of cosmology. Through improved telescopes and more sophisticated simulations, we are continually expanding our understanding of the universe's grand design. These investigations help to peel back the layers of the universe's intricate history, giving us a deeper comprehension of its evolution, from the birth of galaxies to the continuing expansion of space itself. Inextricably linked to the study of cosmic voids is the role of dark matter, an invisible yet dominant force that shapes the structure of the universe. Despite not emitting or absorbing light, dark matter constitutes roughly 27% of the universe's total mass energy content. Its presence is felt through its gravitational effects, which are crucial to understanding how galaxies, galaxy clusters, and even larger structures such as superclusters and cosmic filaments form and persist. Immediately after the Big Bang, matter began to clump together under the influence of gravity. While ordinary matter, which emits light, began to aggregate into stars and galaxies, it was dark matter that provided the framework for these structures to take shape. Dark matter interacts only through gravity, not electromagnetism, meaning it does not dissipate energy by colliding with regular matter. This property allows it to remain gravitationally bound, forming massive halos around galaxies and galaxy clusters. These halos act as gravitational wells, drawing in ordinary matter and facilitating the creation of stars, galaxies, and larger cosmic structures. Dark matter's influence extends beyond the initial formation of galaxies. As galaxies collide and merge, their dark matter halos interact, potentially leading to the growth of even larger galaxies and galaxy clusters. Understanding these interactions is crucial for explaining phenomena such as the rotation curves of galaxies. These curves, which describe the speed at which stars orbit the outskirts of galaxies, suggest that galaxies contain far more mass than what we can observe. The additional unseen mass is attributed to dark matter, which cannot be directly detected but whose gravitational effects are clear. Further astronomical observations and simulations of large-scale structures provide more evidence of dark matter's role in the universe. By mapping the distribution of galaxies and clusters, scientists can infer where dark matter is located. Projects like gravitational lensing, which measures how light from distant objects bends when passing through massive structures, offer direct evidence of dark matter's existence and distribution. These findings continue to refine our understanding of how dark matter shapes the cosmos and contributes to the very structure of the universe itself. Beyond our observable universe lies an entire realm that remains largely shrouded in mystery. While we can study and map structures within our cosmic neighborhood, speculation about the nature of structures beyond the observable limit introduces a host of intriguing possibilities. These speculations are influenced by various cosmological theories, each proposing different scenarios for how the universe might behave outside our view. One prominent idea suggests that regions beyond our observable horizon could be vastly different from what we see nearby. For instance, these regions might have variations in the density and arrangement of galaxies, clusters, and voids. The distribution of mass and energy in these distant regions could be radically different, potentially leading to the formation of entirely new kinds of celestial structures. Another hypothesis posits that physical laws might not be universal, but could vary in different parts of the cosmos. If fundamental constants, such as the strength of gravity or the speed of light, were different beyond our observable universe, the evolution of cosmic structures in those regions could produce entirely different outcomes. These variations might give rise to exotic astrophysical objects or new forms of matter and energy that challenge our current understanding of physics. In addition to these potential variations in physical laws, the geometry of space-time itself plays a critical role in shaping the universe. Current measurements of the cosmic microwave background radiation suggest that the observable universe is flat. However, beyond this observable boundary, space-time could take on a different curvature, potentially leading to entirely different forms of cosmic structure and evolution. The possibility of alternate physical laws or altered geometry presents exciting new challenges for cosmologists and physicists as they continue to push the boundaries of our understanding of the universe. As we continue to explore the vastness of the cosmos, both near and far, each new discovery brings us closer to unraveling the deepest mysteries of the universe. From the enigmatic voids and the elusive nature of dark energy to the invisible influence of dark matter and the possibility of parallel cosmic regions, the universe continues to surprise and intrigue. With each new breakthrough, we not only expand our knowledge of the universe, but also deepen our understanding of our place within it. The journey of cosmic discovery is far from over. Each step forward brings us one step closer to uncovering the grand, intricate tapestry that is the universe. And yet, if the universe truly is infinite, stretching far beyond the limits of what we can observe, it may possess complex curvature characteristics that influence how cosmic structures emerge and evolve on a grand scale. Beyond the horizon of our telescopes, space could bend and twist in unfamiliar ways, altering the fate and formation of galaxies, clusters, and voids. This notion challenges the idea that our observable universe is representative of the whole. In fact, it might be just a tiny patch in an immeasurable cosmic landscape. Enter the provocative theory of the multiverse, a concept that suggests our universe is only one in an enormous ensemble of countless others. Each of these hypothetical universes could obey a different set of physical laws, constants, and structural patterns. Some might host matter and forces unlike anything we've ever conceived. Others could be entirely unrecognizable, bizarre, turbulent realms governed by rules that defy the physics we know. Though deeply speculative, these ideas expand the frontier of scientific thought, igniting bold theories and inspiring new approaches to understanding existence itself. In this vast and still mysterious cosmos, such speculative frameworks aren't just mental exercises. They fuel scientific curiosity, pushing astronomers, cosmologists, and physicists to explore the farthest edges of knowledge. The pursuit of what lies beyond our cosmic reach deepens humanity's appreciation of the unknown, compelling us to ask what is reality and how much of it have we yet to uncover. Among the most compelling puzzles in our universe is the elusive substance known as dark matter. This mysterious material neither emits, absorbs, nor reflects light, rendering it invisible to conventional observational tools. Yet, despite being undetectable by sight, dark matter is believed to comprise about 27% of the universe's total mass energy composition. Its presence is inferred indirectly through the powerful gravitational fingerprints it leaves on the cosmos. One of the strongest lines of evidence supporting dark matter comes from galaxy rotation curves. When astronomers study the motion of stars orbiting the outer edges of galaxies, they find something astonishing. The stars move at much higher speeds than predicted by the gravitational pull of visible matter alone. According to Newtonian physics, their velocities should drop off as they move away from the galactic core, but they don't. Instead, the speeds remain largely constant, suggesting the presence of an invisible mass, an extensive dark matter halo, surrounding each galaxy and holding it together. Gravitational lensing provides another striking clue. In this phenomenon, light from distant galaxies is bent as it travels through the gravitational fields of massive foreground objects like galaxy clusters. Observations show that the degree of bending far exceeds what can be accounted for by visible matter alone. This discrepancy implies a significant amount of unseen mass consistent with dark matter, exerting a gravitational influence on the light's path. The structure of the universe itself further supports the dark matter hypothesis. On the largest scales, galaxies are not distributed randomly. They form a complex web-like pattern known as the cosmic web. Simulations of cosmic evolution that include dark matter produce patterns that closely match real astronomical observations, sprawling filaments of galaxies, dense clusters, and vast empty voids. These simulations show how dark matter acts as a gravitational framework, around which visible matter aggregates, shaping the architecture of the cosmos. Despite its importance, the true nature of dark matter remains a cosmic enigma. Theories abound, with one leading candidate being WIMPs, weakly interacting massive particles, which are thought to interact with regular matter only through gravity and perhaps the weak nuclear force. Scientists are deploying increasingly sophisticated instruments in underground laboratories and deep space observatories to detect these elusive particles, either through direct collisions or indirect signatures like particle decay or gamma-ray emissions. Dark matter doesn't just influence galaxies from afar, it was instrumental in shaping them from the very beginning. In the early universe, mere moments after the Big Bang, dark matter began to clump together, forming immense gravitational wells. These dark halos acted as anchors for ordinary matter, gas and dust, which fell into these wells, condensing over time to form the first stars and galaxies. Without dark matter's gravitational pull, this process might never have happened. As galaxies evolved, dark matter continued to guide their destiny. The shape, mass, and rotational dynamics of galaxies were largely dictated by the invisible scaffolding surrounding them. It provides a stabilizing force that allows galaxies to resist the chaotic energies of formation and collision. When galaxies merge, their dark matter halos collide as well, affecting how the newly formed galaxies grow and settle. These interactions help explain why larger galaxies often show different properties than their smaller counterparts. On the grandest scale, dark matter plays a defining role in the formation of the cosmic web. It creates the gravitational highways along which galaxies travel, cluster, and evolve. As the universe expands, dark matter's influence shapes how galaxies move through space, how they interact, and how large-scale structures continue to develop. It choreographs the cosmic dance we observe across billions of light years. So, dark matter is not just an obscure ingredient in the cosmic recipe. It is a fundamental force behind the scenes, guiding the evolution of galaxies and the expansion of the universe itself. Understanding it may unlock new laws of physics and offer a deeper glimpse into the origins and fate of the cosmos. The hunt for dark matter has become one of the most important quests in modern science. From deep underground detectors searching for rare interactions to space telescopes scanning for subtle distortions in light, scientists are determined to uncover its secrets. Each experiment brings us one step closer to understanding the shadowy side of the universe, and perhaps to rewriting the very foundations of physics. One of the most extensively studied contenders in the quest to understand dark matter is the particle known as the weakly interacting massive particle, or WIMP for short. WIMPs are theorized to possess masses roughly equivalent to hundreds of giga-electron volts, a unit that might seem abstract but represents an enormous amount of energy on the quantum scale. These particles are predicted to interact with the rest of the universe primarily through the weak nuclear force, one of the four fundamental forces of nature, and through gravity. According to prevailing cosmological theories, WIMPs were abundantly produced in the first fleeting moments following the Big Bang, when the universe was still an unimaginably hot and dense plasma of particles and energy. Detecting WIMPs directly poses a formidable challenge because their interactions with ordinary matter are incredibly feeble. They hardly leave a trace as they slip through detectors, making scientists rely on highly sensitive experiments designed to capture the rare occasions when a WIMP might collide with an atomic nucleus. These collisions, if observed, would provide tantalizing evidence of WIMPs' existence and unlock new insights into the invisible scaffolding holding galaxies together. Alongside WIMPs, another fascinating dark matter candidate captures the imagination of physicists, the axion. Proposed as a solution to deep puzzles in quantum chromodynamics, the theory describing the strong nuclear force, axions are hypothesized to be ultralight, slow-moving particles that could compose a substantial fraction of dark matter. Their interactions with other particles are so incredibly weak that detecting axions requires ingenious experimental setups. One promising approach involves exposing a strong magnetic field to coax axions into transforming into photons, or particles of light, thereby revealing their presence indirectly. These experiments are at the cutting edge of physics, pushing the boundaries of what we can observe and measure. Beyond these, theories that extend the standard model of particle physics introduce an entire family of particles known as supersymmetric partners. In these frameworks, every known elementary particle has a heavier superpartner with unique properties. Among these, the neutralino stands out as a particularly promising dark matter candidate. Neutralinos are stable, electrically neutral particles that interact via the weak force, fitting many criteria needed to explain dark matter's gravitational effects. Although supersymmetry remains theoretical and has yet to be confirmed experimentally, it provides a compelling blueprint that could reconcile gaps in our understanding of the universe's fundamental building blocks. In a different vein, primordial black holes present a radically alternative possibility. Unlike particles, these black holes are thought to have formed from density fluctuations in the infant universe, long before stars and galaxies took shape. If they exist in sufficient numbers, these tiny yet dense objects could contribute to the gravitational influence attributed to dark matter. While this idea diverges sharply from the more particle-focused explanations, it remains an active and intriguing area of research, especially because it intertwines cosmology with the enigmatic physics of black holes and early universe conditions. Together, these diverse candidates illustrate the wide-ranging approaches scientists have embraced to decode the mystery of dark matter. Current and future experiments aim to detect or exclude these possibilities, pushing the frontier of both particle physics and cosmology. Each approach holds the potential to revolutionize our understanding of the universe's composition and reveal fundamental laws that govern reality on the largest scales. Meanwhile, dark energy represents an equally perplexing cosmic puzzle. This mysterious form of energy fills all of space and is driving the accelerated expansion of the universe, comprising approximately 73% of the total mass energy content of the cosmos. Unlike ordinary matter and dark matter, which attract through gravity, dark energy behaves oppositely, exerting a repulsive force that causes galaxies to drift apart faster and faster. The discovery of dark energy traces back to the late 20th century, a breakthrough born from the study of distant supernova, exploding stars that serve as cosmic mile markers. In the mid-1990s, two independent research teams, the Supernova Cosmology Project and the High-Z Supernova Search Team, set out to measure the brightness of Type 1a supernovae. These stellar explosions are considered standard candles because their intrinsic brightness is well understood, allowing astronomers to calculate cosmic distances with great precision. The scientists anticipated that the universe's expansion would be slowing due to gravitational pull. Instead, their observations revealed a surprising acceleration, challenging long-held assumptions and opening a new chapter in cosmology. This accelerated expansion raises profound questions about the nature of the cosmos, compelling scientists to explore new theories that could explain dark energy's origin and behavior. As researchers continue to refine their measurements and develop more sophisticated models, dark energy remains one of the greatest enigmas in modern science, its invisible influence shaping the fate of the universe itself. And yet, their data revealed something utterly unexpected. The supernova, those brilliant beacons of stellar death, appeared dimmer than they should have been. Not because the stars themselves were weak, but because they were farther away than scientists had calculated. This single observation sent ripples through the astrophysical community. It meant one astonishing thing. The expansion of the universe wasn't slowing down, as once assumed, it was speeding up. To explain this cosmic acceleration, scientists turned to a concept as mysterious as it was profound: dark energy, a term that sounds pulled from science fiction but is grounded in the most precise measurements of the cosmos. Dark energy, as currently understood, is a force that permeates space itself, pushing galaxies apart with an invisible hand. The roots of this idea stretch back to Albert Einstein. In the early 20th century, when Einstein developed his theory of general relativity, he introduced a term into his equations to maintain a static universe, a belief widely accepted at the time. He called it the cosmological constant. But when the universe was later discovered to be expanding, Einstein reportedly dismissed the term as his greatest blunder. Ironically, that discarded constant has resurfaced as one of the leading explanations for dark energy. It describes a constant energy density that fills space uniformly, unaffected by the expansion of the universe. Yet not all theorists agree with a static cosmological constant. Some propose that dark energy may not be constant at all. The theory of quintessence, for example, suggests that dark energy's density could vary over time and space, shifting in intensity and effect as the universe evolves. These models paint a more dynamic picture of dark energy, one that interacts with the cosmos in ways we've only begun to imagine. Despite these theoretical advances, the true nature of dark energy remains one of the greatest enigmas in modern physics. Researchers analyze data from a broad array of cosmic signals: the faint glow of the cosmic microwave background, the distribution of galaxies on the largest scales, and the shifting light of distant supernova, all to refine their understanding of this invisible force. What makes dark energy so significant is not just its mystery, but its immense influence on the future of the universe. Since its discovery, evidence has mounted that the accelerated expansion began billions of years ago and continues today. As dark energy pushes galaxies apart, it's shaping what could be the ultimate fate of everything in existence. One widely accepted scenario is known as the Big Freeze. In this model, the universe keeps expanding under the influence of dark energy. Galaxies drift farther apart, eventually vanishing beyond our cosmic horizon. Star formation ceases. Existing stars burn out and die. Black holes and white dwarfs become the relics of a bygone cosmic age. Over unfathomably long periods, trillions of years, the universe would grow cold, dark, and still, approaching a state of absolute thermodynamic equilibrium, a silent universe frozen in time. Another, more dramatic possibility is the Big Rip. If dark energy becomes stronger over time, if its energy density grows without limit, it could overwhelm all gravitational forces. First, galaxy clusters would be torn apart, then individual galaxies, then solar systems. Eventually, even atoms could be unraveled as space itself is pulled apart. This would be the ultimate disintegration, an end where time and space dissolve in a catastrophic final expansion. Yet some cosmologists speculate about an alternative future. What if dark energy changes form? Some theories suggest it might one day become weaker, or even reverse into an attractive force. If so, the expansion could slow, halt, or even reverse. Galaxies might collide and merge, forming new stars and new worlds in a rejuvenated universe. This could lead to a cyclical cosmology, a universe that expands, contracts, and is reborn endlessly in a rhythm beyond comprehension. Today, teams of scientists around the globe are racing to uncover answers. Advanced telescopes peer into the depths of space and time, mapping galaxies, studying supernovae, and measuring the cosmic microwave background, the fossil light of the early universe. Each observation sharpens the picture, offering subtle clues about dark energy's behavior and its long-term role in cosmic evolution. Whatever the final answers may be, one thing is clear. Dark energy holds the key to understanding our universe's destiny. Whether we face a frozen eternity, a violent unraveling, or a cosmic rebirth depends on this elusive force. Its presence, unseen but powerful, reminds us that the universe is far stranger, more complex, and more awe-inspiring than we ever imagined. And so one of the most profound discoveries in modern cosmology began not with a theoretical equation, but with a telescope pointed toward the night sky. In the late 1920s, astronomer Edwin Hubble made a startling observation at the Mount Wilson Observatory in California, an observation that would forever change humanity's understanding of the cosmos. He noticed something curious in the light coming from distant galaxies, a shift toward the red end of the spectrum. This phenomenon, now known as redshift, wasn't merely a trick of light. It was a cosmic message, one that spoke of motion, of distance, and of an expanding universe. As Hubble measured the redshift of these galaxies, a pattern emerged. The farther away a galaxy was, the faster it appeared to be receding. This relationship, now encapsulated in Hubble's law, revealed that space itself was stretching. Not that galaxies were moving through space like ships across an ocean, but rather that space, the very fabric of the cosmos, was expanding, carrying galaxies along with it. This redshift, explained through the Doppler effect, meant that light waves were being stretched as galaxies moved away, much like the change in pitch we hear when an ambulance speeds past. But Hubble's discovery was only the beginning. Decades later, in 1965, another piece of the cosmic puzzle emerged. Quiet, persistent, and ancient. Two radio astronomers, Arno Penzias and Robert Wilson, detected a faint, uniform background noise in their antenna, seemingly coming from every direction. They had stumbled upon the cosmic microwave background radiation, or CMB, a relic glow from the early universe. This afterglow, a whisper from a time just 380,000 years after the Big Bang, provides a snapshot of the infant universe as it cooled and allowed atoms to form. Satellites like NASA's Wilkinson Microwave Anisotropy Probe and the European Space Agency's Planck mission later mapped this radiation in exquisite detail, revealing tiny fluctuations, like ripples frozen in time, that encoded information about the density, temperature, and structure of the early cosmos. These cosmic fingerprints confirmed that the universe had indeed been expanding ever since its fiery beginning. Another striking line of evidence came from the study of supernova, specifically type Ia supernovae. These exploding stars act as standard candles because their intrinsic brightness is known, allowing astronomers to calculate their distance based on how dim they appear from Earth. In the 1990s, two independent research teams observed distant supernovae and made a surprising discovery. These supernovae were dimmer than expected. That meant they were farther away than previously thought. The universe's expansion wasn't just continuing, it was accelerating. Something mysterious, something powerful was driving this acceleration. Today, we call that force dark energy. And then there's the large-scale structure of the universe itself. Galaxies are not scattered randomly like grains of sand, but instead arranged in colossal filaments, sheets, and voids that form a vast cosmic web. This structure, observed through detailed surveys of the sky, is shaped by billions of years of gravitational interactions guided by the initial fluctuations seen in the CMB. It's another powerful confirmation that the universe has expanded and evolved over time, with gravity sculpting matter into the sprawling architecture we see today. Threaded through all these discoveries is a vital quantity known as the Hubble constant. This value tells us how fast the universe is expanding by describing the relationship between a galaxy's distance and its velocity. In simpler terms, for every additional megaparsec, about 26 million light-years of distance, a galaxy recedes from us faster by a specific number of kilometers per second. This elegant relationship, measured in kilometers per second per megaparsec, serves as the universe's cosmic speedometer. Determining the exact value of the Hubble constant has become one of modern astronomy's most debated quests. Measurements based on the CMB yield one number. Observations from supernovae and other local methods yield another. This discrepancy hints at the possibility that our understanding of cosmic expansion, and perhaps the very nature of the universe, may still be incomplete. Yet from redshift to radiation, from dying stars to the stretching of space-time, all the evidence points to a single, awe-inspiring conclusion. The universe is not static. It is expanding, growing, and evolving. And with each new measurement, with each deeper look into the cosmos, we are piecing together the story of where we came from, where we are, and perhaps where we are headed. However, it is important to note that recent measurements of the Hubble constant, the rate at which the universe is expanding, have produced slightly different values depending on the methods used. Observations from the Planck satellite, which measured the cosmic microwave background radiation, the faint afterglow of the Big Bang, suggest a specific value for the Hubble constant. Meanwhile, measurements from large surveys of supernovae and the distribution of galaxies consistently yield a higher value. This discrepancy, often referred to as the Hubble tension, has sparked intense discussions and ongoing research in cosmology as scientists strive to reconcile these differences and better understand the fundamental physics governing the universe's expansion. Ultimately, the Hubble constant serves as a crucial bridge linking observations of recessional velocities and distances. It stands as a cornerstone in our comprehension of the expanding universe and guides future inquiries into its fate. Understanding the precise value of this constant is not just a technical detail. It shapes our broader picture of cosmic history and destiny. Cosmic acceleration, on the other hand, refers to the remarkable phenomenon in which the expansion of the universe has been observed to speed up over the past several billion years. This counterintuitive behavior suggests that galaxies are moving away from one another at an ever-increasing rate, rather than slowing down under the influence of gravity as once expected. The discovery of cosmic acceleration fundamentally shifted our understanding of the universe's dynamics and opened the door to profound implications for cosmology. The leading explanation for cosmic acceleration is the presence of dark energy, a mysterious form of energy that permeates all of space and acts in opposition to gravitational attraction. Dark energy is thought to constitute roughly 73% of the universe's total energy density. Unlike ordinary matter, which exerts a gravitational pull, dark energy appears to have a repulsive effect, pushing galaxies apart and driving the accelerated expansion. Despite its dominance, the nature of dark energy remains one of the most profound enigmas in modern astrophysics. Various theories have been proposed to describe its properties, including the cosmological constant, a constant energy density filling space uniformly, as well as dynamic fields that might evolve over time. Yet no definitive explanation has been established, keeping the mystery alive. Observational evidence supporting cosmic acceleration primarily stems from studies of distant supernovae, particularly type 1a supernovae. These cosmic explosions serve as reliable standard candles, allowing astronomers to measure cosmic distances with remarkable precision. When researchers discovered that these supernovae appeared dimmer than expected, it indicated they were farther away than previously thought. This unexpected finding led to the groundbreaking conclusion that the universe's expansion was not slowing down but accelerating. Further evidence comes from detailed observations of the cosmic microwave background radiation and the large-scale structure of the universe. Measurements of tiny fluctuations in this ancient radiation provide insight into the density and composition of the early universe, while the distribution of galaxies and galaxy clusters observed today aligns with the accelerated expansion model influenced by dark energy. Yet, despite extensive research into dark energy and cosmic acceleration, many questions remain unanswered. Scientists continue to explore the true nature and behavior of dark energy, conducting ongoing experiments and observational campaigns aimed at refining our understanding. These efforts hold the potential to reveal new physics that could fundamentally reshape our comprehension of the universe's evolution and ultimate fate. The implications of cosmic acceleration and dark energy go far beyond mere scientific curiosity. They delve into profound questions about the very fabric of reality itself. The expansion of the universe affects not only the regions we can observe, but also stretches into realms beyond our observational limits. As the universe expands, it influences the dynamics and distribution of matter on vast scales, continuously driving the evolution of cosmic structures both within the observable universe and in the unseen regions beyond. One of the key consequences of this expansion is the concept that regions beyond our observable universe may be receding from us at velocities exceeding the speed of light, not because they are moving through space, but because the fabric of space itself is expanding. This means that light emitted from galaxies in those distant regions may never reach us, remaining forever beyond our cosmic horizon. As the universe continues to expand, more regions will slip out of our observable reach, leading to a future where the night sky gradually empties of distant galaxies. This eventual isolation could result in a cosmos that appears increasingly dark and desolate, fundamentally altering our perception of the universe over immense cosmological timescales. Moreover, these effects raise intriguing questions about the potential existence of structures beyond our observable universe. While we cannot directly observe these regions, theoretical models suggest they may harbor additional galaxies, clusters, and cosmic filaments similar to those found within our observable limits. However, these structures could evolve differently depending on local conditions, gravitational interactions, and the influence of dark energy. Such variations imply that the universe beyond our sight may not merely be an extension of what we observe, but could possess unique characteristics yet to be understood. In exploring these mysteries, cosmologists continue to push the boundaries of knowledge, seeking to unlock the secrets of cosmic expansion, dark energy, and the ultimate destiny of the universe itself. Furthermore, the rate at which the universe expands could fundamentally shape its destiny, especially if the elusive force known as dark energy changes its nature over time. Some theoretical models suggest that dark energy might not remain constant. Instead, it could evolve, altering the cosmic landscape in ways we are only beginning to imagine. Such shifts could give rise to vastly different futures, not only in the parts of the universe we can observe, but also in those that remain forever beyond our reach. Imagine a universe where dark energy grows stronger and stronger. This scenario might culminate in what cosmologists call the Big Rip, a dramatic and violent end where galaxies, stars, planets, and even the very atoms that compose them are torn apart. The cosmic fabric itself would unravel, destroying structures across the vastest expanses, even those in the most distant corners of space. This possibility stretches our understanding of physics and challenges the limits of what we consider possible. Scientists tirelessly study the fundamental laws that govern cosmic expansion, seeking to unlock the secrets behind this mysterious energy. As their knowledge deepens, so does our grasp of what the future holds. Beyond the familiar regions mapped by telescopes lie uncharted territories, mysterious and enigmatic. These hidden domains may harbor phenomena that defy current theories and offer profound insights into the very fabric of reality, even if we may never observe them directly. The fate of the universe is a question that grips cosmologists worldwide. Several leading theories attempt to describe what lies ahead, each hinging on how the universe's expansion interacts with dark energy. As the cosmos stretches, galaxies move farther apart, driven by this repulsive force. If the expansion keeps accelerating, the universe might end in a chilling state known as the Big Freeze. In this scenario, stars burn out, galaxies drift beyond each other's reach, and the cosmos becomes an ever-growing cold void, a silent darkness swallowing all light and life. Alternatively, some scientists envision the Big Crunch. Should the density of the universe be sufficient, gravity might eventually counteract the expansion, pulling everything back together. The universe could collapse inward, condensing into a single infinitely dense point, reminiscent of the primordial state before the Big Bang. This cosmic rewind could even trigger a new Big Bang, birthing another universe in an endless cycle of creation and destruction. Another captivating theory, the Big Rip, predicts a future where dark energy strengthens without limit. This unstoppable force could progressively dismantle galaxies, stars, and planets down to the tiniest particles and atoms. The disintegration of all cosmic structures would mark a catastrophic end, a universe shredded to its very core. Then there is the steady-state theory, a more tranquil vision where expansion continues forever, yet the universe maintains a consistent appearance. New matter is continuously formed to fill the gaps created by expansion, preserving the overall structure and density of the cosmos. Though less favored today, this idea underscores the profound complexities involved in understanding cosmic evolution. These diverse scenarios highlight not only the incredible scope of cosmology, but also the vast uncertainties that persist in our quest to comprehend the universe's fate. Each theory invites deeper investigation, sparking curiosity and driving research into the unknown. Equally fascinating is the story of antimatter, a mysterious mirror image of the matter we know. Every particle has an antimatter counterpart with the same mass but opposite electric charge and quantum characteristics. For example, the electron, carrying a negative charge, has an antiparticle called the positron, which holds a positive charge. When matter and antimatter meet, they annihilate each other in a brilliant burst of energy, often releasing gamma rays. This annihilation reflects a deep symmetry and balance within the universe's laws. Yet there is a puzzling imbalance. The universe seems dominated by matter, with antimatter scarce and elusive. This asymmetry is one of the most profound mysteries confronting physicists today. According to theories of the Big Bang, equal amounts of matter and antimatter should have formed at the universe's inception. Understanding why matter prevailed, allowing stars, planets, and life to exist, remains a critical question, one that drives much of modern research into the origins of everything we see around us. However, our observable universe presents a profound mystery. It is overwhelmingly composed of matter, while antimatter seems almost entirely absent. This striking imbalance raises a fundamental question that has puzzled scientists for decades. Where did all the antimatter go? This puzzle is at the heart of one of the greatest unsolved problems in cosmology and particle physics. The leading explanation for this disparity is a phenomenon known as baryogenesis. This theory suggests that in the earliest moments following the Big Bang, the physical processes governing the cosmos favored the creation of matter over antimatter. Yet, despite decades of research, the precise mechanisms behind this preference remain elusive. To uncover these secrets, researchers around the world are conducting experiments designed to detect subtle differences in the behavior of matter and antimatter. Scientists are probing particle interactions in environments of extreme energy, conditions that echo those just after the Big Bang, to determine if tiny asymmetries exist. For example, the study of neutral kaons, subatomic particles that can decay in surprising ways, has revealed possible violations of charge parity, CP symmetry. These violations are key because they suggest that the laws of physics might treat matter and antimatter slightly differently, offering a potential explanation for why matter dominates the universe we observe. Understanding antimatter isn't just about solving a cosmic riddle. It has far-reaching implications that could revolutionize our understanding of fundamental physics. These insights challenge long-held assumptions and may unlock clues about the elusive dark matter and dark energy, mysterious components that together make up about 95% of the universe's total mass and energy. As experiments continue, the quest to decipher antimatter's mysteries could ultimately lead to a deeper, more comprehensive understanding of the cosmos itself. Rewinding to the earliest seconds of the universe's existence, the conditions were nothing short of extraordinary. The Big Bang began as a singularity, a point of infinite density and temperature packed with incomprehensible energy. Within the first fleeting moment, known as the Planck epoch, all four fundamental forces of nature, gravity, electromagnetism, the weak nuclear force, and the strong nuclear force, were unified into a single force. But as the universe expanded rapidly, undergoing a process called cosmic inflation, this unity shattered. During cosmic inflation, the universe grew exponentially, expanding from subatomic dimensions to roughly the size of a grapefruit in less than a blink of an eye. This dramatic swelling smoothed out the fabric of space-time, eliminating any primordial irregularities and setting the stage for the formation of galaxies and larger cosmic structures. As the universe cooled, the four forces separated into their distinct forms, and the first elementary particles, such as quarks and electrons, began to form. Within minutes, as temperatures fell to around 1 billion degrees Celsius, these particles combined through nuclear fusion to create the universe's first light elements, primarily hydrogen, helium, and trace amounts of lithium. This process, known as Big Bang nucleosynthesis, yielded roughly 75% hydrogen and 25% helium, with only tiny traces of other elements. These primordial elements became the essential building blocks for stars, galaxies, and ultimately, the rich tapestry of cosmic structures we see today. Approximately 380,000 years later, the universe had cooled enough for electrons to join with protons, forming neutral hydrogen atoms in a process called recombination. This event freed photons to travel unimpeded through space, producing the cosmic microwave background radiation, a faint glow permeating the entire universe. This radiation serves as a snapshot of the cosmos in its infancy, providing invaluable clues about its origin and evolution. Fast forward to the present day, and some of the most energetic particles known, ultra-high energy cosmic rays, continue to intrigue scientists. These particles carry energies millions of times greater than those produced by even the most powerful human-made particle accelerators. Primarily consisting of protons or heavier atomic nuclei, their origins remain one of the universe's most tantalizing enigmas. Current research points to several potent cosmic phenomena as possible sources of these ultra-high energy cosmic rays. Among the prime suspects are supernovae, the cataclysmic explosions marking the death of massive stars. These titanic blasts hurl particles into space at nearly the speed of light, accelerating them to astonishing energies. Unraveling the mysteries of these cosmic rays not only sheds light on the violent processes shaping the universe, but also provides a deeper understanding of the fundamental physics governing matter and energy on the grandest scales. However, the sheer energy needed to produce the ultra-high energy cosmic rays that we detect far exceeds what supernovae alone can generate. This has led scientists to look beyond stellar explosions for explanations. One of the most compelling candidates is active galactic nuclei, or AGN, which are tied to supermassive black holes residing at the centers of galaxies. These enormous black holes, surrounded by swirling gas and dust, unleash powerful jets of high-energy particles. The incredible gravitational forces and rapid spins at play near these black holes accelerate particles to mind-boggling energies, making AGN prime suspects as the cosmic particle accelerators responsible for some of the highest energy cosmic rays. Gamma-ray bursts, on the other hand, represent some of the most violent explosions known in the cosmos. These fleeting but intense bursts of gamma radiation arise from catastrophic events such as the collapse of massive stars or the merger of neutron stars. The shock waves generated by these cataclysms are believed to be capable of accelerating particles to energies rivaling those produced by supernovae and active galactic nuclei. Their contribution to the cosmic ray population is a subject of active research, expanding the horizon of what might fuel these energetic messengers. Intriguingly, some theories propose that ultra-high energy cosmic rays may also originate from interactions between cosmic rays and the cosmic microwave background radiation, the faint afterglow of the Big Bang permeating the universe. Others speculate that these particles might trace their origins back to phenomena from the universe's earliest moments, hinting at connections to fundamental physics operating at unimaginable scales. As scientists worldwide deploy vast observatories and conduct intricate experiments, the quest to unravel the origin of ultra-high-energy cosmic rays intensifies. Each new discovery not only fills critical gaps in our knowledge of high-energy astrophysics, but also deepens our grasp of the fundamental forces and cosmic processes that govern the vast universe around us. Fast radio bursts, or FRBs, add another layer of mystery to our cosmic exploration. These are incredibly brief yet intense flashes of radio waves lasting only milliseconds. Since their discovery in 2007, FRBs have captivated astronomers and astrophysicists alike, challenging them to decode their enigmatic signals. Though their exact origins remain elusive, several leading theories have emerged. One prominent hypothesis suggests that fast radio bursts arise from collapsing neutron stars, particularly during energetic outbursts known as magnetar flares. Magnetars are neutron stars with magnetic fields trillions of times stronger than Earth's. When these magnetic giants release energy, they can emit bursts of radio waves powerful enough to be detected across vast cosmic distances. Other researchers propose that FRBs could stem from neutron stars colliding with other cosmic bodies or processes linked to black holes. More speculative ideas even entertain the possibility that some FRBs might originate from distant galaxies, and tantalizingly, from extraterrestrial civilizations. Though this last notion remains highly speculative, it highlights the diverse theories that fuel ongoing investigations into these fleeting signals. Beyond their mysterious origins, fast radio bursts carry immense scientific potential. As these signals traverse the cosmos, their dispersion reveals crucial information about the matter between galaxies, especially the distribution of electrons in the intergalactic medium. This helps scientists refine models of cosmic evolution and shed light on invisible matter that cannot be observed through traditional telescopes. Studying the characteristics of FRBs also touches on fundamental cosmic questions such as the nature of gravity, how matter behaves under extreme densities, and the role magnetic fields play in shaping the universe's evolution. With new detections becoming increasingly frequent, fast radio bursts promise to unlock fresh insights into the fabric and history of the cosmos. Shifting focus from these energetic phenomena, we encounter the Great Attractor, a vast, enigmatic region nestled within the Laniakea supercluster, the immense cosmic structure that includes our Milky Way galaxy. Unlike a single massive object, the Great Attractor is a gravitational anomaly influencing the motion of countless galaxies across a huge swath of space, suggesting the presence of an enormous concentration of mass. Discovered in the 1980s, this mysterious gravitational pull was inferred when astronomers observed peculiar galaxy motions all pointing towards a specific sky region. The gravitational force behind these movements is believed to arise from a colossal aggregation of galaxies, gas, and elusive dark matter, though its exact makeup remains shrouded in uncertainty, partly because it lies behind the dense plane of the Milky Way, obscuring direct observation. Within this gravitational powerhouse likely reside thousands of galaxies, along with complex structures such as galaxy clusters. The Great Attractor's immense pull causes galaxies to move towards it at remarkable speeds, a dynamic that illustrates gravity's profound influence on cosmic scales. On an even grander scale, the Great Attractor forms part of the vast cosmic web, an intricate network of filaments, clusters, and voids weaving the large-scale structure of the universe. Its gravitational effects fit into this broader framework, demonstrating how localized concentrations of mass govern the motions of galaxies far beyond their immediate vicinity. Studying the Great Attractor not only unravels the mysteries of this unique region, but also enriches our understanding of the universe's large-scale architecture. It highlights the interconnectedness of cosmic structures and how gravity sculpts the universe's dynamic landscape, affecting the behavior of galaxies over millions of light years. Inside the event horizon of a black hole lies one of the universe's most enigmatic and extreme environments is the event horizon, the invisible boundary surrounding a black hole, beyond which nothing can escape, not even light itself. This remarkable threshold marks the ultimate point of no return, Once any object crosses the event horizon, it becomes completely cut off from the outside universe. It can no longer send signals or information back. This boundary is where the familiar laws of physics start to unravel under the overwhelming grip of gravity. Approaching the event horizon means entering a realm where gravity warps space and time in ways that challenge our deepest understanding. According to Einstein's theory of general relativity, time itself behaves differently near a black hole. To a distant observer watching from afar, time appears to slow down dramatically for anything falling toward the event horizon. Meanwhile, the person or object crossing this threshold experiences time in their own way, creating a mind-bending contrast known as time dilation. This strange distortion of time creates a complex and fascinating dynamic, blending science and mystery at the edges of reality. Inside the event horizon, the familiar rules of physics start to break down. At the heart of a black hole lies the gravitational singularity, a point where matter is thought to be crushed into infinite density. This singularity represents a breakdown of all known physics. Our current theories cannot fully explain the extreme conditions found there. Space and time curve infinitely, resulting in paradoxes that puzzle scientists and make it incredibly challenging to reconcile Einstein's theory of general relativity with quantum mechanics, the framework that governs the tiniest particles in the universe. To address this, researchers are exploring new frontiers in physics, such as quantum gravity, which seeks to unite these conflicting theories and fill the vast gaps in our understanding of the cosmos. Understanding what happens inside the event horizon is crucial not only for grasping the nature of black holes, but also for unlocking fundamental secrets about the universe itself. With advances in technology and observational techniques, scientists are gradually peeling back the veil surrounding these cosmic enigmas. Future discoveries could revolutionize our understanding of black holes and reshape our conception of space, time, and reality. Closely tied to the concept of black holes are the mysterious theoretical entities known as white holes. These are thought to be the exact opposites of black holes. While black holes pull matter and light inward with immense force, white holes are hypothesized to expel matter and energy outward, acting almost like cosmic fountains. In theory, white holes could serve as exit points for matter that has fallen into black holes, creating a one-way passage connecting different parts of the universe. This idea fuels fascinating speculation about the fabric of space-time and the potential for matter to move through these cosmic gateways. Unlike black holes, which have been observed indirectly through their effects on surrounding matter, white holes remain purely hypothetical. They are predicted by the equations of general relativity, but have never been detected in nature. If white holes exist, they would likely feature a singularity similar to black holes. However, instead of compressing matter into an infinitely small point, white holes would violently eject matter, potentially contributing to the formation of stars and galaxies. This expulsion would be highly energetic, releasing radiation and particles at incredible speeds. The possibility of white holes opens a new chapter of questions about the interconnectedness of the universe. Some scientists have proposed that black holes and white holes could be linked by wormholes, hypothetical tunnels through space-time that could allow passage between distant regions of the cosmos. This idea tantalizes with the possibility of shortcuts across vast cosmic distances or even pathways to alternate universes. However, white holes face significant theoretical challenges. For example, the second law of thermodynamics states that entropy, the measure of disorder, must increase in an isolated system. This principle raises questions about how white holes could consistently expel matter and energy without violating fundamental laws of physics. For now, white holes remain fascinating mathematical constructs rather than confirmed physical realities, though ongoing research into black holes and the structure of spacetime may one day reveal more. Another extraordinary phenomenon linked to black holes is the quasar, sometimes called a quasi-stellar object. Quasars are among the brightest and most energetic objects in the universe. Powered by supermassive black holes at the centers of distant galaxies, they shine with incredible intensity. As matter spirals into these black holes, it forms a rapidly spinning accretion disk, heating up to extreme temperatures and emitting vast amounts of energy across the electromagnetic spectrum, ranging from visible light to radio waves and powerful X-rays. Quasars are so luminous that they can outshine entire galaxies, making them visible across unimaginable distances in space. Studying quasars allows astronomers to peer back in time, since many observed quasars are billions of light years away. This means we see them as they existed when the universe was still young, only a few billion years after the Big Bang. The light from these distant quasars carries precious clues about the early cosmos, offering insights into the formation and evolution of galaxies during the universe's formative epochs. By examining quasars, scientists gain valuable knowledge about the environments surrounding supermassive black holes and the conditions that fostered rapid galaxy growth. Moreover, quasars help illuminate the distribution of gas and mysterious dark matter in the vast expanses between galaxies, shedding light on the large-scale structure of the early universe. In exploring black holes, white holes, and quasars, we are venturing into some of the most profound mysteries of existence. These cosmic phenomena challenge our understanding and inspire us to push the boundaries of physics and astronomy. Each new discovery offers the potential to reshape our view of the universe, revealing the astonishing complexity and wonder of the cosmos. Additionally, studying the spectra of quasars unveils a treasure trove of information about the elemental makeup of the early universe and their relative abundance. These cosmic lighthouses act as time capsules, allowing scientists to reconstruct the timeline of element formation and understand the cosmic processes that sculpted the chemical landscape of galaxies. By analyzing the light from these extraordinarily powerful beacons, researchers can trace the intricate life cycles of galaxies and deepen humanity's grasp of the universe's grand evolution. Quasars have thus become indispensable tools in cosmological research, bridging the gap between the earliest cosmic epochs and the present day. The universe itself harbors some of the most extreme and baffling environments imaginable, natural laboratories where the laws of physics are pushed to their limits. One of the most intense settings exists at the core of neutron stars, the dense remnants left behind after a supernova explosion. These stars pack masses exceeding that of our sun into volumes comparable to entire cities. The gravity in these stellar cores is so overwhelming that a tiny sugar cube-sized sample of neutron star matter would weigh more than a mountain on Earth. Such staggering densities and pressures are unparalleled elsewhere in the cosmos, offering scientists rare insights into how matter behaves under these extraordinary conditions. Another remarkable cosmic extreme lies near the supermassive black holes that sit at the centers of many galaxies. These behemoths, millions to billions of times the mass of our sun, generate gravitational fields so powerful that nothing, not even light, can escape once it crosses the event horizon, the mysterious boundary where conventional physics begins to unravel. Surrounding these black holes, matter spirals inward, heating up to millions of degrees and emitting intense radiation. Observations reveal energetic phenomena such as relativistic jets, narrow streams of particles blasting away at nearly the speed of light, which provide critical clues about the complex, dynamic processes in these regions where gravity and energy intertwine in extraordinary ways. Among the universe's most spectacular and energetic events are gamma-ray bursts. Originating from cataclysmic occurrences like the collapse of massive stars or the violent mergers of neutron stars, these bursts release more energy in mere seconds than our sun will emit over its entire lifetime. Their incredible brightness and far-reaching signals enable astronomers to peer deep into the early universe, testing theories of stellar evolution and cosmic conditions in epochs long past. These cosmic explosions illuminate the violent and dynamic nature of the universe on the grandest scales. Gravitational lensing offers yet another window into extreme cosmic environments. When light from distant galaxies passes near massive galaxy clusters, these clusters act like natural magnifying glasses, bending and distorting the light through their immense gravitational fields. This effect creates multiple images of the same galaxy and magnifies their brightness, allowing astronomers to study galaxies otherwise too faint to observe. Beyond showcasing the power of gravity, gravitational lensing also uncovers the elusive distribution of dark matter, an invisible substance that dominates the universe's mass budget. This interplay between mass, light, and gravity provides crucial insights into the universe's large-scale structure. Together, these extreme environments form a cosmic puzzle, revealing vital clues that help unravel the universe's deepest mysteries and the fundamental laws governing it. Beyond the observable universe, the region from which light has had time to reach us since the Big Bang approximately 13.8 billion years ago, lies a realm shrouded in mystery and speculation. The actual universe could be vastly larger, potentially infinite, housing objects and phenomena far beyond our current observational limits. Theories suggest the existence of even more massive black holes, formed through the merging of countless smaller ones over cosmic time, with gravitational forces and energetic processes exceeding anything observed so far. This possibility opens profound questions about the nature of reality and the full scope of the cosmos. Could there be entire realms with physics even stranger and more extreme than those we study today? As our tools and observations improve, humanity stands on the brink of uncovering these hidden corners of the universe, pushing the boundaries of our knowledge ever further into the cosmic unknown. Additionally, theories of cosmic inflation propose the existence of vast regions within space and time where the very laws of physics might differ drastically from what we know. These variations could include different fundamental constants of nature, leading to entirely unique structures and phenomena beyond our current perception. Imagine entire bubble universes, each with their own distinct physical properties, realms that might harbor exotic states of matter or forms of energy completely unknown to us. These cosmic bubbles could contain realities where matter behaves in ways that challenge our understanding, possibly unveiling new types of particles or forces that seem inconceivable within our own universe. One of the most captivating extensions of this idea is the multiverse hypothesis. This concept suggests that our universe is not alone, but rather one bubble among an immense, possibly infinite collection of bubble universes existing within a grander multiverse framework. Each of these universes could have its own set of physical laws, constants, and conditions. This staggering diversity could allow for objects or phenomena that defy the boundaries of what we consider possible. For instance, there could be universes where matter and energy exist in extreme or entirely unfamiliar forms, governed by particles that behave in astonishing and unpredictable ways. While these ideas remain speculative and largely theoretical, they open enthralling new pathways for cosmological research. As scientific methods and observational technologies continue to advance, our ability to peer deeper into the cosmos may reveal evidence of these diverse realms, reshaping our understanding of existence itself. At the heart of our current comprehension of the universe's origin stands the Big Bang Theory, which posits that approximately 13,800 million years ago, the universe began as a singularity, an infinitely dense and hot point. From this initial state, a rapid expansion unfolded, initiating a cooling process that allowed fundamental particles to emerge and combine into atoms. This expansion has not ceased. We witness its ongoing effects through the redshift of galaxies, where light stretches as these cosmic bodies speed away from us. One of the most compelling pieces of evidence supporting the Big Bang is the cosmic microwave background radiation, a faint afterglow that offers a snapshot of the universe roughly 380,000 years after the initial explosion. This relic radiation acts as a time capsule, helping scientists piece together the early moments of cosmic history. In the 1970s, the theory of cosmic inflation further enriched our understanding of the universe's infancy. This theory proposes that within an unimaginably brief moment, less than a trillionth of a second, the universe underwent an exponential growth spurt. This sudden inflation smoothed out irregularities, leading to the near uniformity we observe in the cosmic microwave background today, and explaining the large-scale structure of the cosmos. Inflation addresses one of the biggest puzzles: why the universe appears so homogeneous on a grand scale despite its vastness. While the Big Bang and inflationary models dominate modern cosmology, alternative theories offer fascinating perspectives. The cyclic model, for example, suggests that the universe experiences endless cycles of expansion and contraction. Each cycle culminates in a new Big Bang, implying that the cosmos has no definitive beginning or end, but instead exists in an eternal rhythm of birth, death, and rebirth. This idea challenges conventional notions of time and entropy, proposing a cosmos that renews itself indefinitely. Similarly, string theory presents an intriguing viewpoint by hypothesizing that our universe is one among countless others residing in a higher dimensional space. According to this framework, fundamental strings, the building blocks of reality, interact in ways that could generate numerous universes, each with its unique laws of physics and characteristics. This multiverse perspective forces us to reconsider the nature of reality and our place within an immense, possibly infinite, cosmic landscape. As scientists continue to explore these ideas and gather more data, our grasp of the universe's origins and structure may shift dramatically. Each theory, whether well-established or emerging, adds a vital thread to the intricate tapestry of cosmological thought, pushing the boundaries of what we know and illuminating the profound mysteries of existence. Within the framework of the cyclic model, the theory of cosmic rebirth holds a central place. It envisions the cosmos undergoing perpetual cycles of expansion and contraction, creating a process of eternal renewal. Unlike the notion of a single beginning or end, this model suggests that the universe is locked in a continuous loop. Each cycle begins with a Big Bang-like event and ends in a dramatic collapse known as the Big Crunch. In this cycle, after a period of expansion, the universe reaches a maximum size. At this tipping point, gravitational forces may overpower the expansion, pulling matter back together in a slow, inexorable contraction. This contraction phase compresses all matter and energy into an incredibly dense state, potentially recreating the singularity from which a new universe could emerge. Thus, the cosmos is reborn, with each new expansion marking the start of another cycle in this endless cosmic dance. This cyclical perspective also redefines our understanding of time and entropy. Instead of flowing linearly from a beginning to an end, time may reset with each cycle, offering the possibility of recalibrated entropy, a measure of disorder. The universe's repetitive rebirth could provide answers to some of the deepest questions in cosmology, challenging traditional views and opening new horizons for scientific inquiry. However, critics have raised significant concerns about the cosmic rebirth theory, particularly focusing on the issue of entropy, the measure of disorder or randomness in a system. During each cycle of the universe's expansion and collapse, entropy is thought to increase steadily. This continuous rise poses a serious question. Can the universe really undergo a smooth transition from a collapsing state back to a fresh expansion without encountering insurmountable obstacles? To address this, scientists have proposed various alternative versions of the cosmic rebirth concept, each designed to confront the growing entropy problem head-on. Some of these models introduce sophisticated mechanisms that act to reset or counterbalance entropy, weaving in intricate principles from quantum mechanics and the mysterious realm of string theory. These frameworks imagine that the universe might experience radically different physical processes with every new cycle, possibly even giving rise to new laws of physics or distinct states of reality in each reborn cosmos. Such ideas push the boundaries of our understanding, suggesting that the universe might not only be eternal, but also dynamically evolving in ways that continuously reshape its fundamental nature. As our tools for observation grow ever more precise, and as theoretical physics develops further, researchers tread cautiously but with great curiosity into the implications of these cyclical universes. The notion of an eternal cosmos challenges the traditional concepts of a definite beginning or an absolute end. Instead, it invites us to consider a more fluid vision of existence, time, and the very fabric of reality itself, an exciting frontier that promises to deepen our grasp of the universe's ultimate mysteries. Meanwhile, among the various theories concerning the universe's fate, the Big Freeze stands as one of the most widely accepted scenarios. This theory stems from the observation that the universe is not just expanding, but doing so at an accelerating rate. This acceleration is believed to be driven by dark energy, a mysterious and invisible force that counteracts gravity on cosmic scales. According to the Big Freeze, as the universe keeps stretching, galaxies will drift farther and farther apart, gradually cooling and transforming the cosmic landscape over unimaginably long periods. Looking ahead, in approximately 1 to 2 trillion years, stars will exhaust their nuclear fuel, ceasing to shine as brightly as before. The universe will become dominated by cold remnants, white dwarfs, neutron stars, and black holes. These stellar corpses, once blazing beacons of light, will slowly cool and fade, leaving behind a dark, quiet cosmos. The light and heat generated by star formation will dwindle, ushering in a cold, desolate state where the temperature edges closer and closer to absolute zero. Even though quantum fluctuations, tiny random variations at the smallest scales, may occasionally spark fleeting interactions, the overall environment will become bleak and empty. This state, where energy sources are virtually non-existent, means life as we know it would become impossible. Any structures or systems that once buzzed with activity would degrade, because ultimately succumbing to the relentless march of entropy. The Big Freeze paints a picture of a universe growing colder and darker until it reaches a lifeless end, a scenario far in the distant future, but deeply significant for understanding cosmic evolution. On a related but more extreme note, the Big Rip theory presents a more dramatic conclusion to the universe's story. This hypothesis hinges on the idea that dark energy's repulsive force might not just remain constant but intensify over time. If dark energy's influence grows stronger and stronger, it could ultimately overpower all gravitational forces that hold matter together. The expansion of the universe would not just continue but accelerate relentlessly, tearing apart galaxies, stars, planets, and even atoms themselves. Initially, the Big Rip scenario resembles the Big Freeze, with galaxies drifting apart. But as the acceleration escalates, it would begin to strain the very structure of galaxies. The gravitational bonds keeping stars clustered together would weaken, leading to the dissolution of galactic groups. Over time, even the gravity that maintains individual stars' integrity would be insufficient to resist dark energy's pull. Eventually, this relentless expansion would disrupt stars and other celestial bodies, ending with the universe torn asunder at every scale. Both the Big Freeze and Big Rip scenarios invite us to confront profound questions about the universe's destiny. They reveal the incredible power of dark energy and the delicate balance of forces shaping cosmic history. As scientists continue to gather data and refine their understanding, the fate of the cosmos remains a vibrant area of study, rich with mystery and possibility. Ultimately, the stars themselves would lose the very force that holds them together, their gravitational cohesion. This catastrophic breakdown would lead to the complete disintegration of their structures. Imagine this violent expansion progressing further and further, eventually impacting entire solar systems within galaxies. Planets, moons, and countless other celestial bodies would be pulled apart, drifting helplessly in the void. Over unimaginable spans of time, even the atoms and subatomic particles, the fundamental building blocks of matter, could be torn asunder. What remains then would be a universe where all forms of structure, from the vast to the infinitesimal, dissolve under the relentless pressure of dark energy's unyielding push. If this apocalyptic vision, known as the Big Rip, unfolds as some cosmologists suggest, it would culminate in a moment far beyond human comprehension. At some distant point in the future, all matter in the universe would be completely torn apart, reduced to its most basic components. This possibility raises profound questions about the true nature of dark energy, an enigmatic force that seems to accelerate the universe's expansion, and challenges scientists to uncover its mysterious properties. It compels an urgent exploration into dark energy's fundamental role in shaping the cosmos and influencing the ultimate destiny of everything that exists. As scientific inquiry advances, the concept of the Big Rip continues to shape the narrative about the long-term evolution of the universe. It invites both awe and deeper investigation into the mysterious cosmic forces that govern existence itself. Alongside this, the Boltzmann brain hypothesis emerges from the field of statistical mechanics as a deeply provocative thought experiment. It questions the nature of consciousness and reality in the vast expanse of the cosmos. According to this hypothesis, within an infinitely large and chaotic universe, it is statistically probable, almost inevitable, that a single brain could spontaneously form out of random fluctuations in a high-entropy environment. This brain would come into existence fully formed, complete with false memories and perceptions, existing in complete isolation and chaos. The implications are staggering. If such a Boltzmann brain could exist by mere chance, it calls into question the reliability of our own experiences and consciousness. Could the universe we perceive be nothing more than a fleeting, random arrangement of particles? Could true existence be far more chaotic and unstable than our orderly perceptions suggest? This unsettling idea intersects deeply with cosmology, especially when contemplating the nature of time and entropy. It implies that as the universe expands indefinitely, regions of low entropy, order, may grow increasingly rare. Over time, the frequency of Boltzmann brains might surpass that of genuine conscious observers. This paradox prompts intense philosophical debates about the nature of knowledge, existence, and what it truly means to be aware. As we reflect on our place in the vast cosmos, the Boltzmann brain hypothesis serves as a stark reminder of the immense complexity and mystery that envelop reality, urging us to reconsider our most fundamental assumptions about consciousness, existence, and the laws governing the universe. In a quest to uncover the universe's deepest secrets, string theory offers a revolutionary framework in physics that challenges long-held ideas. Unlike traditional models that view fundamental particles as tiny points, string theory proposes that these particles are actually one-dimensional vibrating strings. This subtle yet radical shift in perspective opens the door to new possibilities, one of the most captivating being the existence of extra dimensions beyond the familiar three of space and one of time. Depending on the version of string theory, these extra dimensions can number anywhere between 6 to 11, vastly expanding the dimensional landscape of the cosmos. These additional dimensions are thought to be compactified, curled up so tightly that they escape detection at normal scales of measurement. Despite their hidden nature, their presence could fundamentally alter the very laws of physics as we understand them. For example, the properties of fundamental particles, such as their mass and charge, might be influenced by the shape and size of these compactified dimensions. This suggests that extra dimensions could hold the key to unifying all fundamental forces of nature, including gravity, within a single theoretical framework. Moreover, the existence of these hidden dimensions might help unlock answers to some of the most stubborn mysteries in physics today. They could provide insights into dark matter and dark energy, the elusive components that constitute the majority of the universe's mass energy content but remain poorly understood. By exploring how forces and particles interact within these extra dimensions, scientists hope to piece together a more complete understanding of the universe's behavior on both the largest cosmic scales and the smallest quantum levels. Finally, the implications of string theory's extra dimensions inspire imaginative possibilities, including the tantalizing notion of parallel universes or alternate realities. This concept excites both scientists and philosophers, encouraging a radical rethinking of our notions of reality and existence. Delving into these hidden dimensions could revolutionize not only physics, but also our perception of the universe we inhabit. Higher dimensions, as proposed by string theory and related frameworks, might profoundly influence the fabric of the cosmos and its large-scale structure. In our everyday experience, gravitational and electromagnetic forces operate within the familiar three-dimensional space. However, the true nature of these forces in the universe itself might be far richer and more complex, woven through unseen dimensions that challenge and expand our understanding of reality. However, when additional dimensions come into play, the interaction of fundamental forces could undergo profound transformations, potentially giving rise to entirely new forms of matter and energy beyond what we currently understand. These extra dimensions may introduce novel gravitational effects that influence the formation and evolution of celestial bodies, such as stars, galaxies, and vast clusters that populate our universe. One intriguing possibility is that the geometry of these higher dimensions could affect the behavior of gravitational waves, ripples in the fabric of space-time generated by colossal cosmic events like merging black holes or neutron stars. If such additional dimensions exist, they might provide new pathways for these gravitational waves to travel, altering their propagation and how we detect them. This could revolutionize our understanding of violent astrophysical phenomena and allow us to observe cosmic events previously hidden from our instruments. Moreover, Considering the ongoing expansion of the universe, these extra dimensions might also play a role in shaping dark energy, the mysterious force responsible for accelerating cosmic expansion. If higher dimensions interact unexpectedly with known forces, they could modify the rate at which the universe expands, offering fresh insights into the true nature of dark energy itself. Scientists studying these hidden dimensions hope to uncover connections that might explain why the universe's expansion is speeding up, an enigma that continues to challenge modern physics. Beyond cosmology, higher dimensions could influence the fundamental properties of particles, causing variations in their behavior at extremely high energies, such as those found in cosmic rays or particle accelerators like the Large Hadron Collider. These effects may unlock new paths toward unifying the fundamental forces of nature, bringing us closer to a comprehensive theory of everything that explains all physical phenomena under a single framework. Delving deeper into this realm leads us to the concept of compactified dimensions, a key idea in string theory and other higher dimensional models. Unlike the familiar three spatial dimensions we navigate daily, these extra dimensions are thought to be curled up or compactified into incredibly tiny, intricate shapes that escape direct detection. These shapes are often described using advanced mathematical structures called manifolds, existing at scales so minuscule, on the order of the Planck length, that current experimental tools cannot yet observe them. The presence of compactified dimensions carries enormous implications for our understanding of fundamental particles and forces. The specific topology, or shape, of these curled-up dimensions influences particle properties such as mass and charge. Different compactifications might explain why certain particles appear in our universe while others do not, with each unique configuration producing its own set of particles and interactions. This suggests that the physical characteristics of our universe, its laws and constants, could be shaped by the precise way these extra dimensions are arranged. Moreover, compactified dimensions may hold the key to understanding the so-called landscape problem in string theory, where a vast number of possible configurations each lead to different sets of physical laws. This raises profound questions about the anthropic principle. Why does our universe seem finely tuned to support life? One possibility is that we live in one of many universes, each defined by a different arrangement of compactified dimensions, where only certain configurations yield the conditions necessary for life and complexity. If these hidden dimensions interact with forces we know, such as gravity, they might generate new physical effects. For example, gravitational interactions could extend into these unseen dimensions, altering our perceptions of gravity's strength and behavior at various scales. This idea is particularly compelling because it challenges the traditional understanding of gravity as described by general relativity, which views gravity as the curvature of spacetime caused by mass and energy. Extending this framework into higher dimensions introduces new complexities. Gravity might not only curve the three spatial dimensions we observe, but also influence and be influenced by the additional hidden dimensions. In such a scenario, gravity's strength could be diluted by spreading into these extra dimensions, which may help explain why gravity is significantly weaker compared to other fundamental forces like electromagnetism. This dilution effect could provide crucial insights into the hierarchy problem in particle physics, why gravity is so much weaker than the other forces governing matter. In summary, the study of higher and compactified dimensions pushes the boundaries of our understanding, opening a window into the most profound mysteries of the universe. It challenges long-held assumptions, offering tantalizing possibilities for new physics that could reshape our conception of reality, from the behavior of the tiniest particles to the grandest cosmic structures. Exploring these hidden dimensions not only enriches our knowledge, but also inspires a deeper curiosity about the fundamental nature of existence itself. Moreover, the geometry of extra dimensions holds profound implications for the behavior of gravitational waves, those subtle ripples in the fabric of spacetime created by massive objects in motion. Just as waves travel uniquely depending on the medium they traverse, gravitational waves may interact with these higher dimensions in ways unlike anything observed in our familiar three-dimensional space. This interaction could alter their speed, direction, or strength, giving rise to distinct propagation patterns. Scientists hope that with increasingly sensitive detectors, these subtle signatures might be uncovered, providing a novel window into the mysterious structure of dimensions beyond our direct perception. Furthermore, gravity itself may behave differently due to these hidden realms. In certain theoretical models, gravity is not confined to our known universe, but instead leaks into compactified or curled up extra dimensions. This leakage could explain why gravity appears so much weaker compared to the other fundamental forces, like electromagnetism or the strong nuclear force. The possibility that gravity extends into unseen dimensions challenges our current understanding and could reshape how we view the universe's fundamental dynamics. The implications are vast, suggesting new ways that the cosmos evolves and interacts on both the largest and smallest scales. Theoretical investigations into these complex, dimensional interactions push the boundaries of physics, challenging established concepts and opening pathways toward a grand, unified theory, one that might reconcile gravity with the other forces of nature in a seamless framework. Such unification would illuminate the intricate web connecting all dimensions of the universe, revealing a deeper harmony underlying reality itself. From this perspective emerges the breathtaking idea of multiple universes, each existing with its own unique dimensional blueprint. Rooted in frameworks like string theory and the multiverse hypothesis, this concept proposes that countless universes arise from different configurations of higher dimensions. These varied arrangements, or compactifications, give birth to universes with distinct physical laws, constants, and even fundamental forces. The sheer diversity could be staggering. Some universes might foster complex chemistry and life, while others could be dominated by entirely unfamiliar forms of matter and energy. In such a multiverse, every universe's properties are shaped by its dimensional structure. For example, a universe with more compactified dimensions might experience particle interactions that differ dramatically from our own, possibly preventing the formation of atoms as we know them, or creating exotic alternatives. This immense variability prompts profound questions about existence itself. If these universes coexist, are they forever isolated from one another? Could we ever detect signs of their presence? The idea aligns intriguingly with interpretations of quantum mechanics, like the many worlds theory, which suggests that each quantum event spawns a branching reality, an ever-expanding tree of parallel universes. The philosophical and scientific ramifications of such dimensional diversity are enormous. They challenge our notions of reality, forcing us to consider that the universe we inhabit might be but one of an uncountable multitude. This expands the scope of cosmology, encouraging fresh debates about why our universe's physical laws appear fine-tuned for life, and whether alternative life forms could exist under entirely different rules in other dimensional landscapes. The allure of these unknown realms captivates both researchers and thinkers, drawing them into the quest to unravel the ultimate nature of reality. At the quantum level, Entanglement offers another astonishing glimpse into the universe's hidden connections. Quantum entanglement occurs when particles become linked so profoundly that the state of one instantaneously influences the state of another, no matter how far apart they may be. This phenomenon defies everyday intuitions about distance and cause, famously dubbed by Albert Einstein as spooky action at a distance. When two particles are entangled, measuring one immediately reveals information about its partner, even if separated by light years. The consequences of entanglement stretch beyond isolated particles, hinting at roles in the vast cosmos. It may help explain mysterious behaviors in extreme environments like black holes or during the universe's earliest moments after the Big Bang. During this rapid expansion, entangled particles could have maintained instantaneous communication, shaping the cosmic web's large-scale structure by influencing how matter and energy distributed throughout space. Understanding entanglement thus not only challenges our grasp of reality at the smallest scales, but also informs our knowledge of the universe's grand evolution, tying the quantum world to cosmic history in an elegant and surprising dance. Moreover, researchers are delving into the fascinating possibility that quantum entanglement, the mysterious connection between particles separated by vast distances, could play a crucial role not only in the tiny realm of atoms, but also on the grandest scales of the universe. Some theoretical models propose that entangled particles might influence monumental cosmic phenomena, such as the formation of galaxies or the elusive distribution of dark matter. This dark matter, invisible yet making up a significant portion of the universe's mass, has long puzzled scientists. The intriguing idea is that entanglement could help explain how these invisible threads weave through the cosmos, shaping its large-scale structure. One particularly compelling area of investigation centers on cosmic inflation, the mind-bogglingly rapid expansion of the universe that occurred fractions of a second after the Big Bang. Certain models suggest that quantum entanglement may be deeply involved in this process, setting the foundational patterns that later evolved into the vast cosmic web we observe today. These insights highlight how entanglement could be the key to bridging our understanding between the quantum world and the cosmic realm, revealing that the universe's grand design might hinge on principles once thought confined to the microscopic scale. Exploring the connection between entanglement and the cosmos also challenges our very conception of reality. It forces us to rethink the classical notion of separateness and individuality, proposing instead that the universe might be a profoundly interconnected whole. In this view, everything, from the tiniest particle to the largest galaxy cluster, is woven into an intricate cosmic tapestry, united through the subtle threads of quantum phenomena. As scientists venture further into this frontier, they stand at the crossroads of quantum mechanics and cosmology, aiming to uncover deeper truths about the universe's origins, structure, and the fundamental laws that govern it. Another astonishing phenomenon at the heart of quantum mechanics is quantum tunneling, a process that defies our classical intuitions about energy and barriers. Classically, a particle must possess enough energy to climb over a barrier, much like a ball needing sufficient speed to roll over a hill. If it lacks this energy, it simply bounces back. However, in the quantum world, particles behave like waves representing probabilities rather than definite positions. This wave-like nature allows them to sometimes tunnel through barriers, emerging on the other side without ever climbing over the obstacle. To imagine this, picture a ball rolling toward a hill. In classical physics, if it doesn't have enough energy, it will never reach the other side. But quantum mechanics tells us there is a small non-zero chance the ball could suddenly appear on the other side, as if it passed through the hill itself. This counterintuitive phenomenon becomes especially significant at the microscopic scale, where quantum effects dominate and shape the behavior of particles. Quantum tunneling has profound implications far beyond laboratory experiments. It is essential for the process of nuclear fusion, which powers stars, including our sun. In the hearts of stars, hydrogen nuclei must overcome a massive electrostatic barrier due to their positive charges repelling each other. Classical physics predicts fusion would require far higher temperatures and energies. Yet, thanks to quantum tunneling, protons can penetrate this barrier and fuse into helium, releasing the tremendous energy that fuels starlight and warmth. This process not only drives the life cycle of stars, but also governs the synthesis of heavier elements vital for the formation of planets and life itself. Beyond stars, quantum tunneling may also provide critical clues about the earliest moments of the universe. Some cosmological theories propose that tunneling mechanisms contributed to the phenomenon of cosmic inflation, possibly triggering the birth of bubble universes within a grand multiverse. In this expansive vision, tunneling transcends the microscopic world and shapes the very fabric of reality at a cosmic scale, influencing how entire universes might emerge, evolve, and interact. At the foundation of these quantum wonders lies the quantum vacuum, a concept that revolutionizes our understanding of empty space. Unlike the classical idea of a vacuum as nothingness, the quantum vacuum is a restless sea of activity, alive with virtual particles that spontaneously pop into and out of existence. These ephemeral particles exist for unimaginably brief moments, too fleeting to observe directly, yet their influence is undeniable. One striking example of the quantum vacuum's tangible effects is the Casimir effect. When two closely spaced conductive plates are placed in a vacuum, they experience a mysterious attractive force caused by the suppression of virtual particles between them. This phenomenon vividly demonstrates that empty space is far from empty. It is a dynamic arena buzzing with hidden energies and forces. On the cosmic scale, the quantum vacuum's energy fluctuations might be linked to dark energy, the mysterious force accelerating the expansion of the universe. The energy inherent in this vacuum could shape the evolution of the cosmos, influencing how galaxies, clusters, and vast cosmic structures form and change over billions of years. The idea that the very fabric of space has energy properties challenges our deepest assumptions and opens new pathways to understanding the universe's past, present, and future. As scientists continue to unravel these quantum mysteries, the connections between the smallest particles and the largest cosmic phenomena become ever clearer. Quantum entanglement, tunneling, and the restless vacuum are no longer just curiosities of the microscopic world. They are fundamental threads in the grand cosmic story, inviting us to rethink the nature of reality itself. Furthermore, the quantum vacuum may hold profound implications for the earliest moments of our universe, right after the Big Bang. During this nascent phase, the universe underwent a period of astonishingly rapid expansion, known as inflation. This inflationary epoch might have been deeply influenced by the extreme energy conditions present in the quantum vacuum. Such conditions could have shaped the large-scale structure of the cosmos we observe today, the vast cosmic web of galaxies, clusters, and voids stretching across unimaginable distances. At its core, understanding the quantum vacuum is more than just a niche in physics. It's a gateway that connects the seemingly disparate worlds of quantum mechanics and cosmology. It reveals how the most fundamental properties of space and energy are not just abstract concepts, but active players in the unfolding history and architecture of the universe itself. As we probe deeper into these ideas, we uncover the intricate tapestry woven by the very fabric of reality. Quantum mechanics and general relativity stand as two monumental pillars in the grand edifice of modern physics. Yet these pillars rest on vastly different foundations. Quantum mechanics governs the strange, probabilistic dance of particles at unimaginably small scales, the realm of electrons, photons, and quarks. General relativity, meanwhile, describes gravity not as a force, but as the bending and warping of space-time caused by mass and energy, governing the cosmic ballet of stars, galaxies, and black holes. Reconciling these two frameworks remains one of the most formidable challenges in theoretical physics. At the grandest cosmic scales, issues arise especially in extreme environments where gravity is overwhelmingly intense, such as the singularities at the heart of black holes, or the primordial conditions in the moments immediately following the Big Bang. In these realms, general relativity's predictions collapse into infinities, singularities, where known laws of physics break down. Quantum mechanics offers a radically different view. It embraces uncertainty and probabilistic outcomes rather than absolute certainty. This stands in stark contrast to the deterministic nature of general relativity, where the future trajectory of space and time can be predicted precisely from initial conditions. This fundamental clash hints that our current understanding is incomplete, and a more profound, unified theory is necessary to describe reality at all scales. The quest for this elusive theory of quantum gravity is among the most ambitious pursuits in physics. Among the leading candidates are string theory and loop quantum gravity. String theory suggests that the universe's fundamental building blocks are not point-like particles, but tiny, one-dimensional strings vibrating at different frequencies. This elegant idea promises a framework where gravity and the other fundamental forces coexist harmoniously within quantum mechanics, while also incorporating the geometric nature of space-time. On the other hand, loop quantum gravity takes a radically different approach by attempting to quantize space-time itself. It posits that space is not smooth and continuous, but made up of discrete, tiny loops, potentially resolving the problem of singularities and providing a coherent quantum description of gravity. Adding even more layers to this complex puzzle are concepts like holography and the black hole information paradox, which challenge our very notions of information, locality, and reality. The holographic principle proposes that all information contained within a volume of space can be fully described by data encoded on its boundary, a profound idea that bridges the concepts of locality and non-locality and hints at a deep connection between gravity and quantum information. As researchers delve further into these mysteries, the hope is to reveal how quantum mechanics and general relativity intertwine to create a unified understanding of the universe, one that seamlessly connects the tiniest particles with the vast cosmic expanse. This reconciliation promises not only to deepen our grasp of fundamental physics, but also to illuminate profound questions about the very nature of existence. One of the most captivating implications of quantum mechanics is the phenomenon of quantum entanglement, where pairs or groups of particles become linked so that the state of one instantaneously influences the state of another, no matter the distance between them. This spooky action at a distance, as Einstein famously described it, challenges our traditional ideas about space, time, and causality. Some physicists speculate that entanglement could create connections spanning vast cosmic distances, or even link separate universes, hinting at a universe more interconnected than we ever imagined. It suggests that information or influence might traverse the cosmos without being limited by the speed of light, reshaping our understanding of space-time and the very fabric of reality itself. These ideas open up tantalizing possibilities and raise fundamental questions. Could quantum entanglement provide a hidden bridge between distant regions of space? Might it serve as a conduit for information exchange beyond the familiar boundaries of the observable universe? As we explore these mysteries, we edge closer to uncovering the hidden connections that weave the cosmos together in a breathtaking, unified whole. Furthermore, when we delve into the extraordinary concept of the multiverse, the idea that countless universes exist alongside our own, each governed by its own distinct physical laws or constants, quantum mechanics emerges as a powerful framework to explore how these vast realms might interact. Within certain interpretations of quantum mechanics, especially the many worlds interpretation, every quantum event causes the universe to branch out, creating a multitude of parallel realities. This branching suggests that interactions or subtle connections could potentially occur between these distinct universes, possibly influencing each other in ways we are only beginning to imagine. Detecting such interactions, however, remains an immense scientific challenge due to their elusive and subtle nature. Adding to this cosmic intrigue are theoretical propositions that quantum entanglement, the phenomenon where particles become linked so that the state of one instantly influences another, regardless of distance, might play a pivotal role in the large-scale structure of the cosmos. Some researchers speculate that entanglement could have been instrumental in orchestrating the early universe's behavior, contributing to phenomena like cosmic inflation, where the universe expanded rapidly in its infancy, or the remarkable uniformity observed in the cosmic microwave background radiation, the faint afterglow of the Big Bang. Although these ideas reside primarily in the realm of theory and face formidable obstacles in empirical testing, they illuminate the profound ways quantum mechanics forces us to rethink the very fabric of reality. The ongoing dialogue between quantum physics and cosmology holds the promise of unveiling a more unified and expansive understanding of the cosmos and its hidden connections. Turning now to an even more mind-bending concept, negative mass is a hypothetical form of matter that defies our conventional intuition. Unlike ordinary positive mass, which accelerates in the direction of an applied force, negative mass would react oppositely. If pushed, instead of moving forward, it would accelerate backward. This bizarre behavior directly challenges the foundations of classical and relativistic physics. Imagine a scenario where a particle with negative mass interacts with positive mass. The negative mass would accelerate toward the positive mass, while the positive mass is pushed away, creating a runaway motion that amplifies itself indefinitely. Such a phenomenon raises deep questions about stability, causality, and the fundamental nature of forces. The implications of negative mass stretch far into the realms of gravity and cosmology. Some theoretical physicists speculate that if negative mass were to exist in the universe, it could influence cosmic dynamics in profound ways, perhaps offering new explanations for enigmatic phenomena like dark energy, the mysterious force driving the accelerating expansion of the universe. Incorporating negative mass into our models of gravity could revolutionize our understanding of attraction and repulsion on a cosmic scale, opening doors to insights that challenge centuries of physics. Yet, it is crucial to emphasize that despite intriguing theoretical explorations, negative mass has never been observed or experimentally confirmed. While certain frameworks in general relativity and quantum field theory allow for the possibility of exotic matter, negative mass remains a speculative concept that pushes the boundaries of our imagination and encourages deeper inquiry. Beyond these speculative ideas, modern physics has revealed that the universe likely harbors forms of matter vastly different from the atoms and molecules we encounter daily. Ordinary matter, the familiar protons, neutrons, and electrons making up stars, planets, and life itself, constitutes only a small fraction of the universe's total mass energy content. An astounding roughly 26% is believed to be dark matter, an invisible substance that neither emits nor absorbs light and cannot be seen directly. Despite its invisibility, dark matter exerts a powerful gravitational pull, influencing the motion of galaxies and the large-scale structure of the cosmos. Its true nature remains one of the greatest mysteries in physics. Leading candidates for dark matter particles include weakly interacting massive particles, or WIMPs, and axions, hypothetical particles with unique properties that differ fundamentally from ordinary matter. This mysterious dark matter exemplifies how much remains to be discovered about the universe's hidden components and forces. It challenges scientists to look beyond the visible and measurable, inspiring new theories and experiments that aim to illuminate the unseen majority of the cosmos. Through the lens of quantum mechanics, cosmology, and theoretical physics, our understanding of reality continues to expand, revealing a universe far stranger and more intricate than ever imagined. Additionally, researchers are venturing into the fascinating and uncharted territory of exotic matter, a realm where the very fabric of reality seems to shift beyond our everyday experience. Exotic matter encompasses a range of hypothetical substances that defy the conventional laws governing the matter we interact with daily. Among the most captivating ideas is that of negative mass, a concept that turns our intuitive understanding of physics upside down, suggesting materials that could, in theory, repel rather than attract under gravity. One particularly compelling candidate within exotic matter is quark matter. Quarks, the fundamental building blocks of protons and neutrons, are typically locked tightly inside these particles, bound by the strong nuclear force. However, some advanced theories suggest the possibility of quark matter existing as a free, unconfined state. In this form, quarks would roam freely, no longer restricted within atoms. This phase could display astonishingly different behaviors, perhaps with properties unlike anything we observe in the familiar solid, liquid, or gas states. Such matter could exist in extreme environments, such as the dense cores of neutron stars, where gravity compresses matter to unimaginable densities. Another fascinating avenue of exploration comes from supersymmetry theories, which predict the existence of supersymmetric particles. These hypothetical particles would be the partners of the known particles, but possess unique traits, often expected to be heavier and to interact with forces in entirely new ways. If these particles are discovered, it could profoundly transform our understanding of the fundamental forces and particles that construct the universe. Supersymmetry could provide solutions to long-standing puzzles, such as the nature of dark matter or the unification of forces at high energies. These investigations into exotic matter are more than just academic exercises. They challenge the core framework of physics itself. They push beyond the standard model, which has long been the cornerstone of particle physics, into new territories filled with questions and possibilities. What principles govern these mysterious forms of matter? Could entire cosmic phenomena be explained by their existence? As researchers probe these mysteries, they edge closer to unraveling some of the most profound questions about the cosmos and humanity's place within it. One particularly thought-provoking idea within this spectrum is that of mirror matter. This theory proposes a parallel form of matter that mirrors ordinary matter but possesses opposite characteristics. The concept stems from extensions to the standard model, particularly those dealing with parity, the symmetry that, in simple terms, suggests that the laws of physics should behave the same way if viewed in a mirror. However, in the case of certain weak interactions, parity is violated, opening the door to speculation that a mirror counterpart to our matter might exist. In this mirrored realm, particles such as electrons, protons, and neutrons could exist as mirror electrons, mirror protons, and mirror neutrons, exhibiting reversed interactions and possibly carrying opposite charges. These particles could combine to form mirror atoms, giving rise to an entire parallel universe composed of mirror matter. One striking feature of mirror matter is that it would interact very weakly with our ordinary matter, making it incredibly elusive to detection. The primary connection might be through gravity or rare interactions mediated by hypothetical particles. This suggests that mirror matter could quietly coexist alongside our own universe, hidden from direct observation. If mirror matter does exist, it could offer explanations for several cosmic mysteries. For example, it might contribute to dark matter, the invisible substance that makes up a significant portion of the universe's mass, but remains undetectable by emitted light or electromagnetic radiation. Moreover, mirror matter might help explain why there is an imbalance between matter and antimatter in the universe, or shed light on the enigmatic dark energy driving cosmic acceleration. Under certain extreme conditions, such as high-energy collisions in particle accelerators or within dense astrophysical environments, interactions involving mirror matter might produce detectable effects, offering glimpses into this shadowy counterpart. Despite remaining theoretical and unconfirmed, the idea of mirror matter opens a thrilling avenue of inquiry. It challenges scientists to rethink the boundaries of reality and explore the interplay between visible and hidden realms. As ongoing research unfolds, the concept may reveal new dimensions of fundamental physics and enhance our comprehension of the cosmos as a whole. Pushing the boundaries even further, some theories speculate about entire galaxies or large cosmic structures made up of exotic matter. Imagine a galaxy composed of negative mass particles, in stark contrast to familiar galaxies where mass attracts and clumps under gravity. Negative mass would respond oppositely, repelling rather than attracting. This could lead to formations that behave in ways unimaginable to current astrophysical models, with structures that disperse rather than collapse, challenging our understanding of galactic dynamics and cosmic stability. Such hypothetical galaxies would rewrite the rules of cosmic architecture. Their existence would demand a reevaluation of how galaxies form, evolve, and interact on the grandest scales. The presence of exotic matter in these forms could even hint at new forces or interactions yet to be discovered, opening a window into a universe far stranger and richer than the one we thought we knew. In sum, the quest to understand exotic matter is a journey into the deepest mysteries of existence, an exploration that could reshape the foundations of physics and revolutionize our view of the cosmos. As researchers push the frontiers of knowledge, they illuminate pathways toward answers that could redefine reality itself. Additionally, the intriguing possibility of exotic matter opens new doors in our quest to understand the cosmos. If some portion of the mysterious dark matter, the invisible substance thought to make up most of the universe's mass, were composed of exotic matter, it could offer alternative explanations for puzzling inconsistencies between what we observe through telescopes and the predictions made by our current models of galaxy formation. These exotic states of matter, such as quark matter, an ultra-dense form of matter believed to exist under extreme conditions, might behave in unique ways, potentially influencing how quickly stars are born or how matter is distributed within a galaxy. Expanding our perspective beyond single galaxies to encompass the vast cosmic structures that weave the universe together, the interplay between ordinary matter and exotic matter might lead to unexpected cosmic phenomena. Imagine a colossal cosmic web composed of both familiar and exotic matter. Such a hybrid structure could possess unusual properties that affect the universe's expansion rate or interact with gravitational waves, ripples in space-time produced by massive cosmic events in entirely new ways. Though the concept of entire galaxies made purely of exotic matter remains speculative, it pushes the boundaries of our understanding of how cosmic structures form and evolve. It challenges scientists to explore unconventional theories in physics, prompting fresh investigations into how these exotic materials might shape the cosmos. This line of inquiry invites us to reconsider the fundamental nature of the universe, uncovering hidden complexities that could revolutionize our view of galaxy formation and cosmological dynamics. As research in fundamental physics advances, contemplating such exotic cosmic forms may become a central theme in the ongoing exploration of space. Alongside exotic matter, exotic forms of energy, particularly dark energy, play a critical role in shaping the universe's destiny. Dark energy, an enigmatic force comprising roughly 70% of the universe's total energy content, drives the accelerated expansion of the cosmos. As space stretches ever wider, dark energy's influence grows, pushing galaxies further apart and sculpting the large-scale structure of the universe itself. In the universe's earliest epochs, gravity reigned supreme, pulling matter together to form stars, galaxies, and clusters. Yet, as dark energy has become dominant over time, it has gradually counteracted gravity's pull, leading to an expansion that appears to be speeding up. This accelerated expansion profoundly affects how galaxies and clusters interact, determining their fate over billions of years. Beyond dark energy, other exotic energy forms could also be at work, influencing cosmic evolution in ways yet to be fully understood. Some theories propose modifications to gravity itself, suggesting that the force may operate differently on vast cosmic scales. Such modifications could alter the behavior of dark energy or the way cosmic structures emerge and evolve. While dark energy remains the most extensively studied, the universe may still harbor surprises. These mysteries challenge us to deepen our understanding of cosmic evolution, reshaping not only how we see the universe's past, but also our predictions for its ultimate fate. Will cosmic expansion continue forever, culminating in a cold, desolate universe, or might new forms of energy emerge that shift this destiny entirely? The answers to these questions hold the key to a profound transformation in our comprehension of the cosmos and its unending journey through time and space. Time itself behaves in fascinating ways near the edge of the observable universe, the limit set by the maximum distance light has traveled since the Big Bang. Approaching this cosmic horizon, the effects of the universe's expansion and the fabric of space-time reveal phenomena that challenge our everyday experiences of time. Because the universe is expanding, the farther an object lies from us, the faster it appears to be moving away. This cosmic recession influences how we perceive time's passage. When observing distant galaxies near this horizon, we are effectively looking back in time. The light reaching us from these remote galaxies has traveled for billions of years, offering glimpses of the universe in its infancy. Peering deeper and deeper into space allows us to witness events that occurred long ago, unfolding when the cosmos was still young, a cosmic time machine revealing the universe's earliest chapters. Moreover, time itself does not tick away uniformly throughout the cosmos. According to the profound insights of Einstein's theory of general relativity, time can actually flow at different rates, depending on the intensity of gravitational fields it encounters. Near massive celestial bodies, such as black holes or neutron stars, the gravitational pull is so immense that it warps the very fabric of space and time, what physicists call space-time. This warping causes time to slow down dramatically compared to regions that lie farther away from such gravitational giants. While this time dilation effect is most striking near these extreme objects, it is not confined to just those zones. Over vast cosmic distances, the cumulative influence of gravity subtly shifts how time unfolds across different parts of the universe. As astronomers peer toward the farthest edges of the observable universe, these distortions of time and space present profound puzzles. For instance, did time, or the universe itself, even exist before the moment we call the Big Bang? What mysteries lie beyond the boundary of what we can currently observe? Our understanding of time is deeply linked with the shape and structure of space-time, and as scientific discoveries progress, our view of time's behavior on a universal scale continues to evolve. One of the most extraordinary manifestations of time's malleability emerges near black holes. These enigmatic objects exert such an intense gravitational pull that they drastically bend space-time around them. As an object moves closer to the event horizon, the invisible boundary beyond which escape is impossible, time appears to slow dramatically from the perspective of an outside observer. The closer the object gets, the slower time ticks, until at the event horizon itself, time could theoretically come to a complete halt. This phenomenon illustrates how differently time can be experienced depending on one's position within a gravitational field. From the vantage point of someone far away, a clock near a black hole might seem to crawl to a stop, while for the traveler falling in, time flows normally. Another fascinating chapter in the story of time unfolds during cosmic inflation, the brief, explosive expansion of the universe in its earliest moments. During this rapid growth, the universe ballooned exponentially, creating conditions that could give rise to what physicists call pocket universes, or bubble universes. These hypothetical regions might possess their own localized gravitational environments, causing time to behave differently compared to our own observable cosmos. In such a scenario, new universes with distinct timelines could emerge, disconnected from the temporal flow we experience. This raises the tantalizing possibility that time might not be a single universal river, but a patchwork of streams flowing at varying paces or even directions. Delving deeper into the quantum realm, the concept of time becomes even more enigmatic. Quantum mechanics introduces phenomena where particles can exist in superpositions, states where they are in multiple conditions simultaneously. If these quantum effects influence the universe on larger scales, they might challenge our traditional ideas of past, present, and future. Time's flow may not be uniform, potentially breaking down the clear sequence we usually rely on. The boundaries of physics are continually tested by these questions, with every new discovery shedding light on whether time is a fixed constant or a flexible dimension capable of warping and twisting in unimaginable ways. Among the most mind-bending ideas in theoretical physics are closed timelike curves. These are paths through space-time that loop back on themselves, theoretically allowing an object to travel back in time and revisit an earlier moment. Such a concept, while speculative, opens up the possibility of time travel within the framework of general relativity. One famous theoretical model featuring these curves is the rotating or Kerr black hole. This exotic object drags space-time around with it in a region known as the ergosphere, creating conditions where closed time-like curves might exist. Traveling along one of these loops could let a traveler meet their past self, raising complex questions about cause and effect. Beyond black holes, other hypothetical cosmic phenomena, such as cosmic strings and wormholes, also suggest the possibility of closed time-like curves. Cosmic strings are theorized as narrow, high-density defects in space-time that might stretch across vast distances, while wormholes are conceptual tunnels connecting separate points in space-time. Both offer intriguing pathways where time might bend back on itself, igniting the imagination about interacting with the past. In the grand quest to understand the nature of time, scientists continue to explore these enigmatic frontiers. Whether time is a constant backdrop to the universe or a dynamic dimension shaped by gravity, quantum mechanics and cosmic expansion remains one of the most profound mysteries in physics. Each breakthrough brings us closer to unraveling how time flows, bends, and possibly loops within the vast, awe-inspiring tapestry of the cosmos. However, the existence of closed time-like curves introduces some of the most profound and puzzling paradoxes in the study of time and physics. Among these, the infamous grandfather paradox stands out as a particularly striking example. Imagine a time traveler journeying into the past and accidentally or intentionally preventing their own grandfather from meeting their grandmother. This interference would prevent the traveler's very existence, raising a fundamental question. How could someone prevent their own birth without negating their ability to travel back in time in the first place? This paradox forces us to confront the intricate relationship between cause and effect in ways that challenge our everyday understanding of reality. In response to these perplexing contradictions, theoretical physicists have developed intriguing ideas aimed at resolving such paradoxes. One leading proposal is the concept of self-consistent histories. According to this view, any action taken by a time traveler would ultimately be part of the timeline they originated from, ensuring that the timeline remains consistent and free of contradictions. In other words, even if a traveler attempts to alter the past, the universe would somehow conspire to prevent any changes that could erase the traveler's own existence. This principle offers a fascinating way to preserve the logical flow of cause and effect within the framework of time travel. Closed time-like curves, while still hypothetical, offer profound insights into the possible structure of our universe. They represent paths through the fabric of space-time that loop back on themselves, potentially allowing travel to the past. Yet, despite their theoretical elegance and the excitement they generate in scientific discussions, there is currently no experimental or observational evidence confirming their existence. The search continues as scientists probe the cosmos and the deepest laws of physics for hints that might validate or disprove these extraordinary ideas. The very notion of closed time-like curves challenges the way we perceive time itself. Time is generally seen as a steady progression from past to future, with cause preceding effect, a principle known as causality, which forms the backbone of our understanding of the natural world. But in some of the universe's most extreme environments, such as near black holes or neutron stars, this principle might not hold in the straightforward way we expect. Near a black hole, especially at its event horizon, the point beyond which nothing, not even light, can escape, the structure of spacetime is radically distorted by gravity. For a distant observer watching an object fall toward this boundary, it appears as though time slows down and almost stops at the horizon. This extreme gravitational warping raises mind-bending possibilities, including scenarios where the usual sequence of cause and effect could be turned upside down. For instance, any signal or information originating from inside the event horizon would be trapped and unable to reach the outside universe, complicating how we understand causality across this boundary. Even more extreme are the conditions surrounding neutron stars, incredibly dense remnants of collapsed massive stars. These objects have densities surpassing that of atomic nuclei, and their gravitational fields are so intense they can significantly influence the flow of time itself. Observers situated in different gravitational zones around a neutron star might disagree on the sequence in which events occur, sparking debates about how to connect causes and effects when viewed from multiple reference frames. The early universe, immediately following the Big Bang, offers yet another extraordinary context in which causality may be stretched or broken. During this period of rapid cosmic expansion and intense energy, the usual rules governing cause and effect may not have been firmly established or might have operated differently from how we understand them today. The very fabric of time, space, and matter was in flux, making it challenging to define a clear order of events or to measure time in the ways we do now. As our understanding of the cosmos deepens, these radical concepts continue to inspire scientists and dreamers alike. The mysteries surrounding closed time-like curves, causality, and the behavior of time under extreme conditions keep pushing the boundaries of what we know. They invite us to imagine a universe far stranger and more complex than our everyday experience suggests, where time may not be the simple, linear journey we once believed it to be. The quest to unravel these mysteries not only advances physics, but also reshapes our very perception of reality, opening doors to discoveries that could forever change how we understand the universe and our place within it. The early universe experienced a dramatic and mysterious phase known as the inflationary epoch, a period when space itself expanded at a rate far surpassing the speed of light. This rapid expansion created vast regions so distant from each other that they became causally disconnected. In simpler terms, events unfolding in one area of the universe might have no influence on events occurring in another, challenging our deeply rooted notions about cause and effect. This phenomenon pushes the boundaries of classical physics, revealing cracks in our understanding of how the cosmos operates on its most fundamental level. General relativity, Einstein's revolutionary theory, has served as the foundation for modern cosmology, elegantly describing how gravity shapes the fabric of spacetime. Yet, these paradoxes arising from inflation and causality hint at limits within this framework when confronted with the universe's most extreme forces. These paradoxes beckon scientists to venture beyond established theories in search of a more complete understanding. A theory that harmonizes the intricate dance of time, space, and cause and effect relationships amid an ever-expanding cosmos. Time itself, once thought to be an absolute and universal flow, is now understood to be far more complex and variable. Theoretical physics and cosmology suggest that the concept of time might differ radically in other universes beyond our own. According to these ideas, the fabric of spacetime is shaped by the fundamental laws that govern a given universe. If those laws vary, then the very nature of time could shift dramatically, creating realities where time behaves unlike anything we experience. One of the most fascinating concepts arises from the multiverse theory, the proposal that countless universes exist, each with its own unique set of physical constants and laws. Within this framework, time might flow differently from one universe to another. In some, time could accelerate or slow down. In others, it might not be linear at all. Imagine a universe where past, present, and future coexist simultaneously, or where time loops back on itself, allowing events to recur or intertwine. Such scenarios completely upend the familiar idea of time as a one-way journey moving steadily from past to future. Adding further complexity is the suggestion that time may not be a fundamental aspect of reality, but rather an emergent property. Instead of existing independently, time could arise from deeper, more elemental interactions, like a complex web of relationships between particles and fields. In this view, time would resemble a network of entangled connections rather than a simple, continuous river. The experience of time might then depend on how matter and energy interact, varying across different regions or universes. Explorations into extra dimensions, especially within string theory, open even more possibilities for how time could operate. Beyond our familiar three-dimensional space, these additional spatial dimensions might interact with time in ways that defy everyday intuition. In certain mathematical frameworks, time could take on entirely new forms, providing glimpses into alternate temporal structures far removed from human experience. As humanity pushes forward in unraveling cosmic mysteries, the idea that other universes might harbor fundamentally different notions of time captivates scientists and philosophers alike. Through ongoing research and the relentless pursuit of a unified theory of physics, we edge closer to grasping the true nature of time and its remarkable flexibility throughout existence's vast tapestry. To understand the shape and destiny of our universe, scientists use different geometric models, each reflecting how matter and energy are spread throughout spacetime. Three primary geometries dominate cosmological studies: flat, positively curved, and negatively curved. Each offers unique implications for the universe's overall shape and eventual fate. A flat universe follows the principles of Euclidean geometry, where parallel lines remain forever apart and the angles of a triangle add up precisely to 180 degrees. This geometry suggests a critical balance in the universe's density of matter and energy. In this scenario, the cosmos will expand forever, but its growth rate will slow gradually over time. Observations, especially those analyzing the cosmic microwave background radiation, the faint afterglow of the Big Bang, indicate that our universe is very close to this flat model. In contrast, a positively curved universe resembles the surface of a sphere. Here, parallel lines eventually meet, and the angles in a triangle add up to more than 180 degrees. This shape implies a closed universe, where expansion will slow, stop, and eventually reverse, culminating in a big crunch where all matter collapses back together. For this to happen, the universe's density must be greater than the critical level. The third possibility is a negatively curved universe, shaped like a saddle. Parallel lines in this geometry diverge, and the angles of a triangle add up to less than 180 degrees. Such a universe has density lower than the critical value, leading it to expand forever at an accelerating pace, driven in part by mysterious dark energy pushing space apart ever more rapidly. Determining which of these shapes truly describes our cosmos requires meticulous measurements and sophisticated techniques. Scientists study the cosmic microwave background radiation's subtle variations, the distribution of galaxies, and the universe's large-scale structure to piece together this cosmic puzzle. Each piece of data brings us closer to understanding the grand design and ultimate fate of the universe we call home. Additionally, observations of distant supernovae play a crucial role in measuring the universe's expansion rate, while comprehensive surveys of galaxy clusters contribute significantly to understanding the large-scale distribution of matter. The dynamic interplay between these two types of observations allows scientists to refine and enhance cosmological models that describe the shape and geometry of the universe itself. By combining data from multiple sources, ranging from supernovae brightness to the spatial arrangement of galaxy clusters, researchers can more accurately assess whether the universe is fundamentally flat, positively curved like a sphere, or negatively curved like a saddle. This deeper insight not only improves our grasp of the universe's current structure, but also sheds light on its evolution and potential ultimate fate. Intriguingly, the universe can be finite, yet unbounded, a concept that often defies intuitive understanding, but can be illustrated by analogy to the surface of a sphere. Imagine walking on the surface of a globe. While the total surface area is limited, there are no edges or boundaries. If you traveled continuously in one direction, you would eventually return to your starting point, having traversed the entire surface without ever encountering a border or end. Similarly, a finite but unbounded universe could be shaped so that space wraps around itself. For example, if the universe's geometry resembles a three-dimensional hypersphere, a higher dimensional analog of a sphere, then it would have a finite volume, yet an explorer traveling in a straight line could journey forever without hitting a boundary. In this closed universe model, all spatial directions eventually loop back to the same points, much like circumnavigating the Earth's surface without falling off an edge. This idea of cosmic topology has profound implications. If the universe truly possesses such a shape, it would influence the distribution of galaxies and large-scale cosmic structures. Astronomers might observe repeating patterns or correlations in the cosmic microwave background radiation, the faint afterglow of the Big Bang, or in the arrangement of galaxies at vast distances. Detecting these repeating signatures would provide compelling evidence of a finite but unbounded universe. Confirming whether our cosmos exhibits this kind of geometry demands painstaking analysis of various cosmic data sets. Observations from the cosmic microwave background, large-scale galaxy surveys, and gravitational lensing effects all contribute critical pieces of the puzzle. Although current evidence generally supports a flat universe, the possibility of a finite yet unbounded cosmos remains an exciting frontier that challenges traditional notions of space and inspires ongoing investigation into the fundamental nature of reality. Another captivating alternative is a hyperbolic or saddle-shaped universe. This model features negative curvature, which means that as you move through space, parallel paths tend to diverge rather than remain equidistant. Visualizing such a universe can be challenging because it does not conform to the familiar flat or spherical shapes we usually imagine. In a hyperbolic universe, the geometry allows for more room within the same volume, creating complex, intricate structures. For example, in this geometry, the angles of a triangle sum to less than 180 degrees, which is a clear departure from the rules of Euclidean geometry. If you were to draw two parallel lines, rather than staying the same distance apart, they would gradually spread apart over vast cosmic distances. This divergence has significant consequences for the universe's large-scale structure. Light traveling across a hyperbolic universe would behave differently than it does in flat or positively curved space. Due to the negative curvature, multiple pathways might exist for light to reach an observer, possibly producing multiple images of distant celestial objects, a phenomenon astronomers could detect through gravitational lensing. Observationally, this could manifest as a chaotic, uneven distribution of galaxies with large voids interspersed among dense clusters, contrasting the more uniform patterns expected in flat or closed universes. The expansion rate in a hyperbolic universe would also be influenced by dark energy, likely resulting in perpetual expansion. As the universe grows, its curvature becomes increasingly negative, reinforcing the saddle-shaped geometry and pushing cosmic structures apart indefinitely. As scientists continue to probe the cosmos, unlocking the secrets of its shape demands rigorous observation and sophisticated data analysis. The nature of the universe's geometry influences not only its present state, but also what lies beyond the limits of our observable horizon. Since our observable universe is bounded by the distance light has traveled since the Big Bang, it forms a spherical volume around us. However, what lies beyond remains a mystery tied to the overall shape and topology of all space. Ultimately, understanding the universe's shape will transform our grasp of cosmology, from the origins of space and time to the cosmic fate awaiting everything within it. This quest touches the deepest questions of existence, revealing a cosmos that is as mysterious and wondrous as it is vast. However, what lies beyond the limits of our observable universe is a question that has long fascinated scientists, philosophers, and curious minds alike. The true nature of the cosmos beyond what our instruments can detect depends heavily on the overall geometry of the universe, a feature that shapes everything from how space stretches to the possible fate of all cosmic structures. Current measurements strongly suggest that our universe is flat, at least to a high degree of precision. In such a flat universe, the implications for what exists beyond our observable horizon are relatively straightforward, but astonishing. Imagine an endless expanse stretching infinitely in every direction, where the galaxies, stars, and cosmic phenomena we see continue without interruption. The vast web of cosmic structures, the clusters of galaxies, the filaments of dark matter, and the immense voids would simply go on forever. This infinite extension implies a remarkable uniformity. The laws of physics and the distribution of matter maintain their consistency across unimaginable distances. In this scenario, there could be countless regions of the universe almost identical to our own, repeating in patterns so vast that the concept of edge loses all meaning. On the other hand, if the universe's geometry bends positively, like the surface of a sphere, the cosmos takes on a profoundly different shape. Instead of infinite stretch, space could be closed and finite, looping back on itself. Picture traveling in a straight line through this cosmic sphere. After covering an immense distance, you might find yourself returning to your original point, just as explorers sailing around Earth eventually circle back to their starting port. This closed universe concept introduces the possibility that the cosmos is self-contained, with no edges but a limited volume of space. If true, some regions of the universe might connect in surprising ways, causing distant galaxies to appear as repeating patterns or mirroring each other in the vast sky. The picture becomes even more intricate if the universe is negatively curved, like a saddle or a hyperbolic surface. This kind of universe stretches outward, but with a shape that causes space to diverge rapidly. Instead of galaxies clustering uniformly, the cosmic landscape could be marked by enormous voids and complex structures arranged in patterns that defy simple categorization. This geometry allows for a cosmic architecture far more elaborate than we might expect. A tapestry where the usual rules of cosmic organization twist and turn, reshaping our understanding of space itself. Across all these possibilities, the shape of the universe influences not just what lies beyond our visible cosmic horizon, but also the fundamental dynamics that govern everything, from the behavior of light to the flow of time. Scientists continuously refine their models by studying cosmic microwave background radiation, galaxy distributions, and the expansion of space, striving to uncover which geometry best matches reality. Each new discovery pushes the frontier of knowledge deeper into the unknown, inviting us to contemplate mysteries as vast as space itself. But the universe might be even stranger than these classic geometries suggest. Some theories explore exotic topologies like a torus or a Klein bottle, shapes that challenge our intuitive ideas of space and boundaries. A toroidal universe, shaped like a giant cosmic donut, suggests a finite yet unbounded space. Traveling far enough in one direction, you could, in theory, and return to your starting point without ever encountering an edge, much like walking around a ring. This kind of looping space might cause repeated cosmic structures or patterns, observable in multiple regions of the sky due to the universe's interconnected nature. Even more mind-bending is the concept of the Klein bottle, a shape that cannot exist fully in 3 dimensions without intersecting itself. It requires 4-dimensional space to be properly realized and lacks any clear inside or outside. If the universe had a Klein bottle topology, the paths through space would twist and connect in bewildering ways, creating relationships between distant regions that defy our usual notions of direction and distance. Such a universe would force a radical rethink of how space is structured on the largest scales. Studying these complex topologies isn't just mathematical whimsy. It could explain unusual patterns in cosmic phenomena, such as certain anomalies in the cosmic microwave background or unexpected gravitational effects. By comparing these theoretical shapes with observational data, researchers hope to unlock deeper truths about the universe's fabric, its origin, and its ultimate destiny. Amid these vast cosmic puzzles lies an even more provocative idea, the simulation hypothesis. This concept proposes that what we perceive as reality might be an extraordinarily sophisticated digital simulation crafted by an advanced civilization. Much like the virtual worlds imagined in science fiction, our entire universe, including every star, planet, and particle, could be the product of computational processes running on a higher dimensional cosmic computer. Philosopher Nick Bostrom famously outlined this hypothesis as a trilemma. Either civilizations never reach the technology needed to build such realistic simulations, advanced civilizations have no interest in creating them, or, most intriguingly, we are almost certainly living inside one. If the last possibility holds, it means the chances are overwhelming that we are among countless simulated beings, existing within a programmed reality rather than a fundamental one. The implications of this hypothesis ripple through both science and philosophy. If our universe is a simulation, then the physical laws and constants we observe may not be ultimate truths, but parameters chosen by the simulation's creators. Life, consciousness, and the cosmos itself could emerge from carefully coded rules designed to mimic complexity and foster evolution. This raises profound questions about the nature of existence, free will, and consciousness. Are our thoughts and feelings authentic, or are they predetermined outcomes of computer algorithms? Does consciousness exist independently, or is it a byproduct of the simulation? These ideas push the boundaries of spirituality and metaphysics, inviting deep reflection on what it means to be real. While the simulation hypothesis remains speculative, it gains relevance as technology advances. Virtual reality, artificial intelligence, and computing power continue to grow, blurring the line between the real and the artificial. The possibility that we live in a grand cosmic simulation challenges traditional scientific inquiry, suggesting that our universe might be just a localized slice of a far larger, more complex digital environment. If so, the rules governing our cosmos, from gravity to quantum mechanics, are akin to software algorithms, carefully tuned and monitored by unknown programmers. The visible universe would then be a window into a vast, layered reality beyond our comprehension, with regions beyond our observation possibly holding even stranger secrets. Understanding the universe's topology and the potential nature of reality remains one of humanity's most thrilling scientific quests. Each new insight uncovers layers of complexity and wonder, reminding us that the cosmos is not only a vast space to explore, but also a profound mystery to contemplate. As we continue to probe the boundaries of space, time, and existence, we edge closer to unraveling the true shape and essence of everything that lies beyond the stars we can see. Additionally, the simulation hypothesis delves deep into some of the most profound philosophical questions humanity has ever faced. Questions about consciousness, existence, and the very nature of reality itself. Imagine for a moment that our entire universe is not the ultimate reality, but instead a minuscule fragment of a vast, intricate simulation. In such a scenario, are we simply characters following a predetermined script, mere players within an advanced program? Or do we possess genuine autonomy, free will, and agency to shape our destinies? This idea shakes the foundations of what it means to be an individual with identity, personal experiences, and meaningful interactions. If everything we know, feel, and do is confined within the boundaries of a simulated world, then what becomes of our sense of self? How do we understand consciousness if it exists within digital confines? These questions strike at the core of free will, challenging our traditional perceptions and inviting us to reconsider the essence of being conscious. While the simulation hypothesis remains speculative and lacks direct, tangible evidence, it has ignited a vibrant and multidisciplinary field of inquiry. Scientists, philosophers, and technologists alike grapple with the implications of cutting-edge technology and artificial intelligence, exploring how these advancements might intersect with the very fabric of our reality. The possibility that our universe could be just one layer within a grand cosmic simulation compels both rigorous scientific investigation and deep philosophical reflection, inspiring us to confront the ultimate question: what is existence? If we entertain the notion that our universe is a simulated construct, the very laws of physics that govern everything we observe might be quite different from those in the host universe, the higher reality that contains our simulation. Depending on how the creators program the simulation, the fundamental parameters and limitations could shape every aspect of our world, from the behavior of particles to the constants that underlie physical phenomena. For example, the fundamental constants of nature, such as the gravitational constant or the speed of light, might not be fixed as we currently believe. In a simulated universe, these constants could be adjusted intentionally or altered as a consequence of computational constraints within the simulation's design. The creators might tweak these values to test different physical scenarios or to create unique environments tailored to specific objectives. Such changes would lead to a universe that behaves differently than our own, producing novel physical laws and interactions that challenge our understanding of reality. The laws of thermodynamics, which govern how energy flows and how systems evolve over time, could also be subject to alteration within a simulated realm. For instance, certain thermodynamic principles might be relaxed or redefined, potentially allowing outcomes that seem impossible under our natural laws, like the creation of perpetual motion machines or the reversal of entropy. Such deviations would open new avenues for exploration inside the simulation, even if they stand in stark contrast to the immutable laws that govern our everyday experience. Furthermore, the structure of space-time itself, the four-dimensional fabric that blends space and time into a single continuum, might be radically different in a simulation. The dimensions of space and time could be manipulated in ways that defy our current scientific comprehension. This could mean that phenomena such as faster-than-light travel, alterations in causal order, or shortcuts connecting distant regions of space might be possible, breaking the conventional limits we have come to accept. These fundamental shifts would dramatically reshape our perception of the universe, offering a playground of extraordinary possibilities beyond the reach of contemporary physics. In contemplating these profound possibilities, the simulation hypothesis acts as a bridge between science and philosophy, technology and metaphysics. It beckons us to explore what lies beyond our observable reality, challenging us to rethink our place in the cosmos and the true nature of existence itself. Additionally, the behavior of particles and fields might be governed by an underlying code, designed either to simplify or to add complexity to the very fabric of reality. Imagine quantum phenomena not as random or purely natural events, but as programmed elements within a vast cosmic simulation. These quantum processes, such as entanglement and superposition, could be deliberately tuned to exhibit specific variations, reshaping the foundations of quantum mechanics as we understand them. This would profoundly influence how information is processed, measured, and ultimately how reality itself is experienced within a simulated universe. As scientists and philosophers delve into the possibility of a simulated cosmos, they confront profound questions about what reality truly means, the boundaries of human knowledge, and the creative potentials unlocked by advanced technologies. By exploring how the laws of physics might differ in such a constructed environment, we gain deeper insight into the universe we inhabit and the core principles that govern all existence. One especially captivating idea is that of nested simulated universes, simulations within simulations, forming a complex hierarchy of realities. This concept suggests that within a primary simulation, sub-simulations might exist, each governed by its own distinct physical laws, constants, and parameters. In this layered framework, each level could operate under a unique set of rules, possibly differing markedly from those above or below it. For example, a universe with specific constants might serve as a controlled environment for testing alternative scenarios created by even more advanced civilizations. This hierarchical design would allow for an extensive range of possibilities to be explored, each simulation experimenting with different laws of physics, varying notions of consciousness, or alternate historical outcomes. Such a nested structure raises profound philosophical questions about consciousness and identity. If self-aware beings exist within these simulations, do they perceive their reality as authentic, even if it's part of a larger artificial construct. What happens to the consciousness or identity of entities as they move through these layers? These questions challenge our understanding of existence, forcing us to reconsider what it means to be real. Individuals in lower-level simulations might be completely unaware of higher layers, believing their reality to be the ultimate one. Technologically, creating such nested simulations would demand staggering computational resources. The complexity grows exponentially with each additional layer, as every nested simulation must maintain coherence with its larger parent reality. This pushes the boundaries of what even the most advanced civilizations could achieve. Yet it also opens possibilities for efficient resource use. By simulating only what is necessary for inhabitants' experiences, they might run entire universes while minimizing computational costs. Even more intriguing is the idea of feedback loops between simulation levels. Actions within one layer could ripple across others, meaning events in a lower-level simulation might influence conditions or scenarios in a higher-level one. This creates a complex web of causality that defies traditional linear notions of cause and effect. While these ideas remain speculative, they provide a powerful framework for thinking about reality's complexity, consciousness, and the interplay between technology and existence. They invite us to reflect on our place in the cosmos and consider the possibility of realities far beyond our current grasp. The question of whether our universe itself is a simulation continues to captivate both scientists and philosophers. To explore this possibility, researchers have proposed various methods to detect signs of a constructed reality. One approach involves searching for anomalies or inconsistencies within the laws of physics. If we live in a simulation, we might find limits to physical phenomena, similar to how computer graphics display boundaries or imperfections. For instance, scientists look for unexpected granularity in space-time or unusual behaviors in fundamental particles. Another approach focuses on detecting computational artifacts, glitches, or shortcuts akin to those found in virtual environments. High-energy cosmic rays traveling enormous distances across the universe could reveal deviations from expected patterns that hint at underlying computational constraints. Quantum mechanics offers unique avenues for probing the nature of reality. Phenomena such as quantum entanglement and the observer effect might contain clues to whether the universe operates like a sophisticated computation. Some theorists speculate that the puzzling aspects of quantum mechanics themselves may be subtle signals that we are experiencing a constructed reality rather than a direct, unmediated universe. Mathematicians and physicists also explore these ideas through the lens of information theory. Since all physical processes can be represented as information, the universe might fundamentally function as a vast information structure, akin to software running on a cosmic computer. This perspective encourages researchers to probe the deepest levels of reality in search of signs that our universe behaves more like code than conventional matter. At the heart of our understanding lies the speed of light, a universal constant with a value of roughly 300,000 kilometers per second in a vacuum. This constant underpins much of modern physics, particularly Einstein's theory of relativity. If the laws of physics vary or show signs of artificial limits, even such fundamental constants might appear altered or subject to the constraints of an underlying simulation. By examining these possibilities, we not only challenge our assumptions about the cosmos, but also expand the horizons of science, philosophy, and technology, opening doors to new ways of understanding existence itself. However, the idea that the speed of light might vary across different regions of the universe sparks fascinating debates among scientists worldwide. This concept challenges the long-held notion that the speed of light is an unchanging, universal constant. Some theories suggest that under extraordinary circumstances, especially near objects with incredibly strong gravitational fields like black holes, the behavior of light could differ in subtle but profound ways. Near a black hole, space and time themselves bend dramatically. This extreme curvature of space-time influences how light travels, not by changing its intrinsic speed in a vacuum, but by altering the very fabric through which light moves. To an observer watching from a distance, light approaching such a massive object may appear to slow down, not because light itself has lost speed, but because gravity distorts time and space around it. This phenomenon highlights how gravity and light interact, transforming our perception of the universe's fundamental workings. Beyond gravitational effects, some scientists propose that the fundamental constants of nature, numbers like the speed of light, might not be fixed throughout the entire cosmos. They speculate that in the early moments following the Big Bang, or across unimaginable cosmic distances, these constants could have shifted or fluctuated. This idea opens up the possibility that light might have traveled differently billions of years ago, or behaves uniquely in far-flung regions of space, reflecting a universe in flux rather than one governed by immutable laws. Adding another layer to this mystery are theoretical frameworks such as string theory and models involving extra dimensions, which suggest the speed of light might be influenced by hidden realms or environmental factors beyond our current reach. These hypotheses remain speculative without direct experimental proof, yet they push scientists to reconsider the principles underpinning physics itself. Investigating these possibilities is a crucial part of expanding our cosmic understanding and uncovering the universe's deepest secrets. If constants like the gravitational constant, the measure of gravity's strength, also vary across the cosmos, the consequences for physics and cosmology would be staggering. Gravity governs the formation of stars, galaxies, and even the structure of space-time, shaping everything we see. In regions where this constant is weaker, stars might struggle to form or burn their fuel quickly, leading to unstable life cycles and dramatically altering galactic shapes, or even preventing their formation altogether. Conversely, a stronger gravitational constant would pull matter more forcefully, creating denser, more extreme environments where stars form rapidly, but conditions might become hostile and chaotic. Such variations could mean that different parts of the universe experience entirely distinct physical realities, challenging our understanding of uniformity and the laws we rely on to explain cosmic phenomena. As scientists explore these ideas through observation, theory, and advanced simulations, they uncover how little we truly know about the universe's complexity and the possibility that the rules of nature themselves may not be as fixed as once believed. Moreover, variations in the fundamental constants of nature could shake the very foundation of the laws of physics as we understand them today. These constants, those delicate numbers that govern everything from the tiniest atomic interactions to the vast gravitational forces binding galaxies, form a fragile balance. If even one were to shift, the consequences could ripple across the cosmos, destabilizing the forces that hold matter and energy in their precise dance. The dream of unifying all the fundamental forces into a single, elegant framework has long captivated physicists. But this ambitious goal hinges on the assumption that these constants remain uniform across space and time. Should they vary, the neat symphony of forces, gravity, electromagnetism, the strong and weak nuclear forces, would fall out of tune. The result could be a universe where physical laws themselves become inconsistent, where the rules that govern particles and fields change from place to place or moment to moment. This would make it impossible to define a coherent set of laws, challenging the very concept of a predictable, stable cosmos. Yet, this unsettling possibility opens a door to new realms of theoretical exploration. It might suggest that our universe is not unique, but rather one of many in a vast multiverse. In such a framework, each universe could possess its own distinct set of physical constants and laws, a cosmic patchwork of realities differing in profound ways. This vision would revolutionize our understanding of complexity and diversity in the cosmos, revealing existence as an intricate tapestry woven from countless threads, each with its own unique pattern. Consider the impact of a universe with a different number of spatial or temporal dimensions. Our familiar world is built on 3 dimensions of space and 1 of time, a framework intimately tied to the physical laws we know. But alter the number of dimensions, and the nature of reality itself shifts dramatically. In a universe with more than 3 spatial dimensions, say 4, the rules governing gravity and motion would transform fundamentally. Gravitational attraction might not behave as we expect. Objects could find it easier to escape the pull of massive bodies, disrupting the formation of galaxies, stars, and planets. Concepts like distance, volume, and surface area would extend into unfamiliar, higher dimensional geometries, challenging even our most basic intuitions about space. Conversely, if space had fewer dimensions, such as just two, everyday dynamics would change drastically. Motion would be confined to flat planes rather than volumes, affecting everything from the paths of orbiting objects to how particles collide and interact. Complex systems observed in particle physics could simplify, potentially leading to fewer types of matter and simpler structures within that universe. Temporal dimensions offer equally fascinating possibilities. Imagine a universe with 2 dimensions of time. This could allow multiple temporal paths and branching timelines, fracturing the straightforward cause and effect sequence that underpins our understanding of reality. Events might weave together in intricate patterns without clear linear progression, turning our concept of time on its head. On the other hand, a universe with only one temporal dimension, if reduced even further, might trap phenomena in more static states, fundamentally altering the nature of change and motion itself. Such shifts in dimensionality would ripple through the laws of physics, reshaping the fundamental forces and challenging the core principles of quantum mechanics and relativity. Exploring these alternative dimensional realities pushes us to reconsider the very structure of our own universe and the dimensions we often take for granted. Among the fundamental forces, the weak nuclear force holds a vital but often overlooked role. It governs processes like beta decay, where a neutron transforms into a proton, releasing a neutrino, and drives nuclear reactions in stars. Without the weak nuclear force, the universe would be starkly different. The absence of this force would have profound consequences on the behavior of particles such as neutrinos and quarks. Beta decay would cease to occur, preventing the transformation essential for the stability of atomic nuclei. Elements like carbon, nitrogen, and oxygen, cornerstones of life, might never form. This absence would deprive the universe of many critical building blocks necessary for biological complexity. Stars, too, depend on the weak nuclear force for their life cycles. Fusion processes, especially the burning of helium into carbon, rely on weak interactions. Without this force, stars might fail to produce heavier elements, truncating their evolution. The cosmic alchemy that creates the chemical diversity underpinning planets and life would grind to a halt. In short, the weak nuclear force is not merely a minor player, it is a cornerstone of cosmic evolution and the emergence of life as we know it. Together, these considerations highlight how the precise values of fundamental constants in the number of dimensions are not arbitrary details but essential ingredients shaping the cosmos. Variations or alterations in these foundations could produce radically different universes, strange, alien realms with their own physical laws, structures, and possibilities. Studying these possibilities not only expands our imagination but deepens our appreciation for the finely tuned universe we inhabit. A world where life, complexity, and order emerge from the delicate interplay of fundamental forces and dimensions. Moreover, the universe as we know it would be radically transformed if the fundamental forces that shaped its earliest moments were altered. The delicate balance of forces that governs the birth and evolution of the cosmos plays a critical role in determining its temperature, structure, and fate. Without this balance, matter would not distribute itself as it does now, potentially causing the universe to either collapse in on itself or expand at an entirely different rate. The absence of the weak nuclear force, one of the fundamental interactions in nature, could prevent the formation of galaxies and other large-scale cosmic structures, completely rewriting the story of the universe's development as we understand it. Without the weak nuclear force, the universe would likely be a far simpler, less diverse place, perhaps even inhospitable to life as we know it. This force plays a crucial role in processes that create the variety of chemical elements necessary for life, enabling the complex reactions that build stars, planets, and ultimately biological organisms. The intricate web of particle interactions and nuclear reactions that supports the rich, vibrant universe around us would be dramatically altered. In essence, the absence of this force would redefine existence itself, erasing the complexity and diversity that make our cosmos so extraordinary. One of the most captivating ideas in modern theoretical physics and cosmology is the concept of alternate universes, or multiverses, where the fundamental particles and forces differ from those in our own universe. In our universe, fundamental particles like quarks, electrons, and neutrinos interact through the forces described by the standard model of particle physics, giving rise to all known matter. However, if the very building blocks of nature were different, the nature of reality would shift in profound ways. In such alternate universes, the properties and behaviors of matter might be unrecognizable to us. Atomic structures could become unstable or behave in bizarre ways if particles were heavier or lighter than those we know. This would dramatically affect the types of elements that form and the physical phenomena that arise, resulting in matter that could defy our understanding, from the simplest molecules to the solidity of everyday objects. The forces that govern these particles, the electromagnetic, weak, and strong nuclear forces, could also function under different principles or intensities, creating cosmic environments with their own unique rules. These changes would cascade into the formation and evolution of complex structures like galaxies and planetary systems. If such structures did form, they might look nothing like the ones in our universe, evolving under physical laws so foreign that their worlds would be entirely alien to our experience. Moreover, the implications for life are profound. The mass, charge, and interaction of particles in our universe are finely tuned to enable the chemistry that supports biological systems. Alternate particles with different properties could create conditions where life, at least as we understand it, would be impossible or unimaginably different. This speculative idea of universes with fundamentally different particles highlights just how delicately balanced our own universe is for the emergence of life. It underscores the intricate interplay of forces and components that shape everything from stars to living beings, and how a small change in these fundamental building blocks could rewrite the cosmic script entirely. In our own vast universe, advanced civilizations face staggering challenges when attempting to communicate across the immense cosmic distances. The sheer scale of space and the immutable speed limit of light impose severe constraints on interstellar communication. Signals sent from one star system to another must traverse countless light years, resulting in significant time delays. For instance, a message sent from a civilization near a distant star might take decades, centuries, or even longer to reach its recipient. To overcome these obstacles, civilizations would need to devise ingenious methods of communication. One common approach involves the use of electromagnetic signals, radio waves or laser pulses, that travel at the speed of light. While effective over great distances, these signals still suffer from delays, so advanced civilizations might develop sophisticated coding and compression techniques to transmit as much information as possible in limited bursts. Additionally, natural cosmic beacons such as pulsars and quasars, which emit steady and predictable signals, could serve as reference points or synchronization tools for interstellar messaging, helping civilizations align their transmissions over vast timescales. Beyond electromagnetic communication, another frontier lies in quantum mechanics, specifically the phenomenon of quantum entanglement. If advanced civilizations could harness entanglement, they might achieve instantaneous communication regardless of distance, bypassing the speed of light barrier. Although current scientific understanding limits practical use of this phenomenon for communication, future breakthroughs could revolutionize how information is exchanged across the cosmos, allowing for a form of messaging that defies traditional constraints. Yet, technology alone is not enough. Effective interstellar communication demands a shared language or code that transcends cultural and biological differences. This might involve the creation of universal symbols, mathematical constructs, or scientific constants that convey fundamental concepts recognizable to any intelligent species. Such common ground would be essential to bridging the vast gulf of understanding between civilizations scattered across the stars. This quest for cosmic communication reveals not only the incredible ingenuity of advanced civilizations, but also the potential for collaboration and shared discovery on a universal scale. It reminds us of the profound interconnectedness that could exist among sentient beings united in their pursuit of knowledge amid the vast, mysterious expanse of space. However, the idea of any information traveling faster than light challenges the very foundation of modern physics. According to Einstein's theory of relativity, nothing can exceed the speed of light in a vacuum. This principle shapes our understanding of causality, space, and time, and any violation of it would require a fundamental revision of physics as we know it. Yet the persistent curiosity about faster-than-light phenomena continues to push the boundaries of science, driving research into the deepest mysteries of the universe. However, scientists have long pondered phenomena that might allow information or effects to be perceived or transmitted so rapidly that it could appear as if communication is happening faster than light. One of the most fascinating possibilities centers around quantum entanglement, a mysterious phenomenon where pairs of particles become linked in such a way that the state of one particle instantly affects the state of its partner, no matter how far apart they are in the universe. This remarkable connection has sparked intense debate about whether entangled particles could be harnessed for instantaneous communication across vast distances. Yet, despite the excitement, it's crucial to understand the limitations of quantum entanglement. While the measurement outcome of one particle is correlated with that of its entangled partner, these results are inherently random and cannot be controlled or manipulated to send usable information faster than the speed of light. This means that although it looks like a cosmic shortcut, entanglement does not violate the fundamental cosmic speed limit established by Einstein's theory of relativity. Beyond quantum entanglement, theoretical physics has explored extraordinary ideas that could one day revolutionize our understanding of communication. Concepts like warp drives or wormholes arise from the possibility of manipulating the fabric of spacetime itself. In theory, these phenomena could bend or connect to distant points in the cosmos, enabling information to travel in ways that bypass the traditional constraints imposed by the speed of light. Imagine sending a message through a shortcut in spacetime, folding the universe so that vast distances become negligible. However, these ideas remain purely speculative and hinge on physical principles that humanity has yet to grasp or achieve. In the natural world, known phenomena such as gravitational waves or shock waves travel at or below the speed of light, faithfully adhering to the universe's speed limit. These waves carry vital information about monumental cosmic events, like the collision of black holes or exploding stars, but their travel speeds remain firmly rooted in relativistic boundaries. As it stands, no naturally occurring phenomenon has been demonstrated to transmit information faster than light, emphasizing the profound influence of the laws of physics on communication. Delving deeper, the field of quantum communication emerges from the principles of quantum mechanics, particularly the bizarre and fascinating behaviors of subatomic particles. Unlike classical communication, which relies on bits existing as either 0 or 1, quantum communication uses quantum bits, or qubits. These qubits can exist simultaneously in multiple states through a phenomenon known as superposition, allowing quantum systems to process and transmit vast amounts of information in parallel. The true intrigue lies in quantum entanglement within these quantum communication systems. When two qubits become entangled, measuring the state of one instantly reveals the state of the other, regardless of their separation across the cosmos. This unique property has fueled hopes that quantum communication might one day enable instantaneous information transfer, seemingly defying the speed of light. To make quantum communication practical, researchers have proposed quantum key distribution, a method of exchanging cryptographic keys using quantum channels. The security of this technique comes from the no-cloning theorem, a fundamental principle of quantum mechanics which states that it is impossible to create an identical copy of an unknown quantum state. This guarantees that any eavesdropping attempt disturbs the quantum system, alerting communicators to the presence of an intruder and ensuring ultra-secure communication. For communication across interstellar distances, scientists envision devices called quantum repeaters, which would extend the range of quantum communication. These repeaters could work by entangling multiple pairs of particles along the communication path, effectively re-establishing entanglement as signals travel across vast cosmic expanses. Although building a fully operational quantum network over such enormous distances remains a tremendous challenge, ongoing advances in quantum technology continue to reveal new possibilities. This suggests a future where secure, near-instantaneous communication across the universe could become a reality. Expanding our gaze, the idea of cosmic-scale structures functioning as communication networks ignites the imagination of astrophysicists and engineers alike. Such colossal constructions could theoretically facilitate information transfer over unimaginable distances, potentially allowing advanced civilizations scattered across the stars to connect, share knowledge, or even reach out to us. One fascinating concept involves natural cosmic phenomena like pulsars, highly magnetized, rotating neutron stars that emit beams of electromagnetic radiation with incredible regularity. When these beams sweep past Earth, they appear as rhythmic pulses of light, making pulsars some of the universe's most precise natural clocks. Advanced civilizations might exploit these predictable signals as beacons for interstellar messaging, encoding information in the timing or frequency of the pulses. This method could serve as a cosmic lighthouse, communicating across the vast chasms of space. Moreover, the idea of constructing massive artificial megastructures, sometimes called Dyson spheres or similar constructs, opens even more thrilling possibilities. These hypothetical structures could harness energy on a cosmic scale, potentially generating powerful signals or establishing vast communication networks through focused laser beams or other advanced technologies. Beyond communication, such megastructures might manage and control energy resources on a scale far beyond anything humanity can currently imagine, shaping the future of cosmic engineering. Together, these scientific speculations and theoretical constructs paint a vivid picture of how communication might transcend the current limits imposed by physics, pushing humanity's understanding of the universe to new horizons. While many of these concepts remain beyond our present reach, they inspire ongoing exploration into the mysterious and boundless possibilities that the cosmos holds. Additionally, cosmic strings, hypothetical one-dimensional topological defects in the fabric of space-time, could, if they truly exist, revolutionize the way we think about communication across the cosmos. These extraordinary structures are predicted to possess unique gravitational properties capable of influencing the propagation of electromagnetic waves in remarkable ways. If future scientists were able to harness these properties effectively, cosmic strings might serve as conduits for communication, bending or connecting space itself to potentially enable faster-than-light effects. Although this idea remains firmly in the realm of theoretical physics, it sparks the imagination, offering a glimpse into how advanced civilizations might manipulate the very structure of the universe to achieve extraordinary feats of connectivity. The concept of communication on a cosmic scale suggests an incredible level of technological sophistication, one where intelligent beings can exploit the fundamental forces and geometry of space-time to bridge the seemingly insurmountable gaps between stars. This idea invites us to imagine civilizations that transcend our current limitations, creating vast networks that span galaxies and perhaps even the entire universe. While we have yet to find any concrete evidence for such networks, the pursuit of this knowledge challenges us to expand our horizons and reconsider what might be possible. Exploring this further, the search for signs of extraterrestrial intelligence pushes the boundaries of our current technology and understanding. The observable universe, extending roughly 13.8 billion light-years in every direction, sets a natural limit on how far we can see or receive information. Beyond this horizon, the universe stretches into regions that remain hidden to us, veiled by the speed of light and the expansion of space. This barrier poses a formidable challenge for detecting signals or messages that could originate from civilizations residing in these unreachable domains. Yet, scientists remain undeterred and employ several imaginative strategies to pierce this cosmic veil. One promising approach focuses on hunting for unusual electromagnetic signals, narrow bandwidth radio waves, or patterned pulses that stand out from the chaotic cosmic background noise. Projects such as the Search for Extraterrestrial Intelligence, SETI, utilize powerful radio telescopes scanning the skies for precisely such anomalies. The hope is that an advanced civilization might employ communication methods recognizable to us, even across vast interstellar distances, revealing their presence through intentional, non-random signals. Another exciting frontier lies in the study of gravitational waves, ripples in spacetime generated by massive celestial events like black hole collisions or neutron star mergers. These waves carry information about the cataclysmic processes that created them, and in theory, could also transmit clues from regions beyond our observable universe. If advanced civilizations are capable of triggering or harnessing such astronomical events, the gravitational waves they emit might bear signatures detectable by instruments here on Earth. Detecting and decoding these subtle distortions in spacetime could open a new window into the hidden cosmos, granting insights into regions we cannot observe directly. Furthermore, cosmologists employ theoretical frameworks to seek indirect evidence of phenomena outside our observable horizon. By carefully analyzing the cosmic microwave background radiation, the faint afterglow of the Big Bang, for unusual gravitational influences or disturbances, scientists hope to uncover traces of structures or events from before cosmic inflation shaped the universe we know today. These subtle fingerprints might reveal the presence of other realms or parallel universes, expanding our understanding of reality far beyond the visible stars. Quantum mechanics adds yet another layer of fascinating possibility. The phenomenon of quantum entanglement, where particles become instantaneously linked regardless of distance, has sparked speculation about future communication technologies that might surpass classical limits, potentially enabling information transfer at speeds exceeding light. While such concepts remain speculative and face significant theoretical hurdles, advances in quantum communication today hint at the tantalizing prospect of breakthroughs that could transform how we connect across vast distances. These innovations might one day allow us to receive messages from civilizations hidden beyond the confines of our current observational capabilities. Despite these ambitious quests, fundamental physical laws impose hard limits on what we can know. The speed of light, as established by Einstein's theory of relativity, acts as a cosmic speed limit, preventing any information from traveling faster than this universal constant. Consequently, vast regions of the cosmos lie forever beyond our reach, unreachable and unknowable in principle. Additionally, the Heisenberg uncertainty principle in quantum mechanics introduces intrinsic limits to our knowledge. This principle states that certain pairs of physical properties, such as position and momentum, cannot both be known with perfect precision simultaneously. This uncertainty is woven into the very fabric of reality, suggesting a fundamental unpredictability that challenges our ability to fully comprehend the universe at the smallest scales. In the grand quest to understand our place in the cosmos, these challenges both constrain and inspire us. They remind us that the universe is vast, mysterious, and filled with possibilities waiting to be discovered, whether through cosmic strings bending space-time, gravitational waves whispering secrets from the edge of the universe, or quantum links defying classical bounds. The pursuit of cosmic communication drives us to explore deeper, think broader, and imagine more boldly the interconnectedness of all intelligent life. Additionally, the staggering complexity of the universe presents profound challenges in our quest to fully understand how the fundamental forces interact. Gravity, electromagnetism, and the strong and weak nuclear forces weave together to create systems of astonishing intricacy. From the enigmatic depths of black holes to the delicate choreography within complex biological organisms, the emergent properties arising from these interactions often defy straightforward explanation or precise prediction. As we dive deeper into these labyrinthine systems, we quickly encounter the hard limits of computation. Modeling and simulating their behavior with accuracy becomes a monumental task, pushing even the most advanced supercomputers to their breaking point. These challenges reveal not only gaps in our technical capabilities, but also the fundamental intricacies of nature that resist simple quantification. Beyond the scientific and technological, philosophical questions loom large. Questions about the multiverse, the very nature of reality, and whether some truths may forever elude empirical scrutiny. Such inquiries transcend the boundaries of experiment and observation, reminding us that the quest for a unified theory that harmonizes all fundamental forces remains a daunting, ongoing journey. It is quite possible that certain dimensions of existence lie perpetually outside the reach of our instruments or even our imagination. These myriad limitations collectively define the contours of human knowledge, shaping how we pursue understanding while simultaneously revealing the vast mysteries still cloaked in cosmic darkness. Our observational tools and methods are crucial in this endeavor, yet they too come with inherent restrictions that confine what we can truly know. A major constraint arises from the limited range of electromagnetic radiation detectable by our instruments. Classical telescopes primarily observe visible light, a narrow slice of the electromagnetic spectrum that restricts our window into the cosmos. Advances in technology have expanded our gaze to infrared, ultraviolet, radio waves, and gamma rays, each unlocking new realms but bringing their own hurdles. Ground-based observations, for example, wrestle with atmospheric interference, while satellites, despite orbiting above the atmosphere, are confined to specific altitudes and vantage points, limiting access to certain regions of the sky. The resolution of our instruments adds another layer of limitation. Though technologies like adaptive optics have sharpened the clarity of images from ground-based telescopes, fundamental physical constraints, such as diffraction limits, persist. These effects restrict our ability to resolve closely spaced celestial objects or faint sources of light. Consequently, crucial details about distant galaxies forming or the dynamics of exoplanetary systems may escape detection, leaving gaps in our cosmic narrative. Time itself introduces further obstacles. Many cosmic events unfold over spans far exceeding human observational timelines. Phenomena like supernovae explosions or black hole mergers occur across timescales that challenge continuous monitoring. We often catch glimpses of these transient events only after significant delays due to the immense distances light must travel to reach us. This delay limits our ability to witness entire life cycles or fully decode the mechanisms driving these dramatic episodes. Our reliance on theoretical frameworks to interpret observations introduces an additional source of uncertainty. While these models are powerful and robust, they are frequently built on simplifications and assumptions that may overlook the universe's full complexity. As new data accumulates, existing frameworks are challenged and revised, uncovering flaws and deepening our understanding. The dynamic interplay between observation and theory continually refines our grasp of the cosmos, highlighting how our tools, while enabling extraordinary discoveries, simultaneously shape and sometimes limit our comprehension of the universe's grandeur. Several significant gaps remain in current cosmological and physical models, posing ongoing challenges. Chief among these is the nature of dark matter and dark energy. Observations suggest that dark matter makes up about 27% of the universe's total mass energy content, while dark energy accounts for roughly 70%. Yet the true essence of both remains elusive. Dark matter reveals itself only through gravitational effects, refusing to emit or absorb light, which makes direct detection exceptionally difficult. Dark energy, theorized to drive the accelerating expansion of the universe, remains an enigma with respect to its origin and fundamental properties. Another profound gap lies in reconciling gravity with quantum mechanics. General relativity beautifully explains gravity on cosmic scales, describing the warping of spacetime around massive objects. Meanwhile, quantum mechanics governs the bizarre and probabilistic behavior of subatomic particles. But a comprehensive theory uniting these two pillars into a seamless whole has yet to be found, leaving one of modern physics' greatest puzzles unresolved. In facing these formidable challenges, humanity stands at the frontier of cosmic understanding, continuously pushing the boundaries of what is known while embracing the mysteries that endure. Each discovery expands our horizon, yet also reveals how much remains hidden, inviting us to explore further into the awe-inspiring universe that surrounds us. However, reconciling the two towering pillars of modern physics, quantum mechanics and general relativity, into a single, unified framework known as quantum gravity remains one of the most profound challenges confronting scientists today. These two theories, each immensely successful within their own domains, describe the universe in fundamentally different languages. Quantum mechanics governs the microscopic world of particles and forces, while general relativity explains the macroscopic behavior of space, time, and gravity. Yet, when physicists attempt to merge them into a seamless whole, contradictions emerge, revealing deep puzzles at the core of our understanding of reality. Over the decades, this quest for a complete theory has given rise to several compelling candidates. Among the most notable are string theory, which posits that the fundamental building blocks of the universe are not point-like particles, but tiny vibrating strings, and loop quantum gravity, which reimagines space-time itself as woven from discrete loops. Despite intense research and tantalizing mathematical insights, a definitive consensus remains elusive. The fundamental nature of space-time, the true character of gravity at the quantum scale, and how these elements interlace to form the fabric of the cosmos remain shrouded in mystery, teasing physicists with questions that stretch the limits of imagination. Adding to this enigma are the profound mysteries surrounding the origins and nature of the universe itself. The Big Bang Theory, our prevailing cosmological model, offers a robust framework explaining how the universe expanded and evolved from an incredibly hot, dense state. Yet it falls short of illuminating the very earliest moments, fractions of a second after the Big Bang, where the laws of physics as we know them break down. Questions linger about what triggered the Big Bang, what preceded it, and how space and time themselves emerged from this primal event. The concept of cosmic inflation, an explosive, brief period of rapid expansion, attempts to fill these gaps, but the precise details and underlying mechanisms remain speculative, beckoning further investigation. Beyond the origins of the universe, our scientific models also grapple with explaining how complexity, and ultimately life, arose amid the vast cosmic expanse. While we possess detailed understandings of the chemical processes that can lead to life, pinpointing the exact conditions that nurture life's emergence remains a challenge. This puzzle extends from the harsh extremes found on Earth, such as deep ocean vents and acidic springs, to the possibility of life on distant exoplanets orbiting other stars. The question of how life can thrive, adapt, or even originate under such diverse conditions complicates our vision of the universe as a dynamic and varied system. It highlights a significant gap in knowledge about the interplay between cosmic evolution and biology, a frontier where astronomy and biology intersect. Together, these gaps and uncertainties underscore that while our current scientific models offer remarkable insights into the workings of the cosmos, they also spotlight the vastness of what remains unknown. They remind us that science is an ongoing journey, propelled by curiosity and the relentless pursuit of knowledge. The quest to unravel the mysteries of space, time, gravity, and life is far from complete. Looking ahead, the future of cosmic exploration holds immense promise, fueled by groundbreaking technologies poised to revolutionize how we observe and understand the universe. One of the most exciting advancements lies in the development of ever more powerful and sensitive telescopes. The James Webb Space Telescope, for example, is designed to capture faint infrared light from distant stars and galaxies, allowing astronomers to peer back billions of years to witness the birth of the earliest cosmic structures with unprecedented clarity. These observations may help unlock secrets about galaxy formation, star birth, and the conditions that shape the universe's infancy. Beyond infrared astronomy, future instruments aim to explore the cosmos across the entire electromagnetic spectrum and beyond. Telescopes capable of detecting gravitational waves, ripples in space-time caused by cataclysmic events like black hole collisions, are opening an entirely new window on the universe. Gravitational wave astronomy offers a chance to observe phenomena invisible to traditional telescopes, shedding light on the most extreme and energetic processes in existence. On Earth and in space, large-scale observatories are being envisioned that could transform observational astronomy. Imagine vast arrays of radio telescopes synchronized to work as a single colossal instrument spanning continents, or even planetary distances. Such networks would dramatically enhance resolution, producing sharper, more detailed images of cosmic phenomena and allowing scientists to explore the universe at scales never before possible. But observational power alone isn't enough. The torrent of data generated by these cutting-edge instruments demands equally advanced methods of analysis. Here, artificial intelligence and machine learning step in as transformative tools. These technologies can sift through mountains of data, swiftly identifying patterns, anomalies, and transient events that human researchers might miss. By automating classification and discovery processes, AI accelerates scientific breakthroughs and uncovers new cosmic insights. Moreover, the integration of emerging quantum technologies promises to push observational precision to new frontiers. Quantum sensors, exploiting the principles of quantum mechanics, could measure gravitational waves and other subtle phenomena with extraordinary accuracy. Such advancements might finally bridge the gap between general relativity and quantum mechanics, unveiling the fundamental forces shaping our universe. Through these leaps in telescope design, data analysis, and sensor technology, our capacity to observe and interpret the cosmos is poised for a dramatic expansion. These tools will not only deepen our understanding of celestial mechanics and cosmic history, but may also reveal entirely new phenomena that challenge current theories and spark fresh scientific revolutions. Yet, despite these technological marvels and intellectual strides, some questions may forever lie beyond human reach. Certain mysteries sit at the crossroads of science and philosophy, probing the limits of our cognition and the very nature of existence itself. As we journey ever further into the cosmos, these enduring puzzles remind us of the vastness not only of space, but of our own quest for knowledge and of the wonder that drives it forward. One of the deepest and most captivating questions humanity has ever posed concerns the very origin of the universe itself. While the widely accepted Big Bang theory provides a compelling framework for understanding how the universe expanded and evolved from an incredibly hot and dense initial state, it leaves open the profound mystery of what, if anything, existed before that moment. The notion of before the Big Bang pushes us into uncharted realms where the conventional laws of physics and even the concept of time as we understand it may no longer apply. Was time itself born at the moment of the Big Bang, or did it stretch infinitely backward? This question remains cloaked in uncertainty, beyond the reach of current empirical investigation and firmly lodged in philosophical debate. Beyond the puzzle of origins, another equally profound inquiry probes the fundamental nature of reality and existence. What, if any, is the ultimate purpose of the universe? Is there a meaning behind our cosmic home? Or is it a vast, indifferent expanse shaped by chance? These questions move beyond the descriptive power of science into the realm of philosophy and spirituality. Science excels at explaining how the universe functions, predicting celestial motions, mapping cosmic evolution, and uncovering the nature of matter and energy. But it may never fully unlock why the universe exists or what purpose, if any, it serves. The subjective experiences that define consciousness and the search for meaning stand as poignant reminders of the limits of scientific inquiry when grappling with questions of purpose and significance. Adding layers of complexity to these mysteries is the concept of the multiverse, a hypothesis suggesting that our universe may be just one of potentially countless others, each with its own physical laws and constants. If true, this idea radically expands our cosmic perspective, but simultaneously presents profound challenges. The other universes in the multiverse might be forever inaccessible to observation or interaction, placing them beyond the scope of empirical science. This introduces a vexing problem. If such universes cannot be tested or observed, can the multiverse hypothesis be considered scientifically valid? This challenges traditional notions of falsifiability, which underpin the scientific method, and forces us to reconsider the boundaries between science and metaphysics. Turning inward, the nature of consciousness itself is a frontier fraught with mystery. Neuroscience and psychology have made remarkable strides in revealing the neural mechanisms behind thought, perception, and behavior, yet the question of how subjective experience, what it feels like to be aware, arises from mere biological processes remains unresolved. Consciousness may represent a profound intersection between science and philosophy, where empirical data meets existential inquiry. It could be that the relationship between mind and universe is so intricate that it defies final explanation, representing a puzzle that sits at the boundary of human understanding. Together, these questions map the limits of current scientific knowledge and illuminate the philosophical depths that accompany our quest to understand reality. While science relentlessly expands our grasp of the universe, some mysteries may resist conclusive answers, underscoring the vast complexity and wonder of existence. Amid these cosmic enigmas emerges the concept of cosmic strings, a fascinating idea born from theoretical physics, especially within the fields of quantum field theory and cosmology. Cosmic strings are hypothesized to be ultra-thin, one-dimensional defects formed during phase transitions in the very early universe, similar to cracks forming in the ice as a lake freezes. Though incredibly narrow, these cosmic strings could be extraordinarily dense, stretching across vast expanses of space while containing immense amounts of mass and energy along their lengths. The extraordinary properties of cosmic strings mean they might exert gravitational forces strong enough to warp the fabric of space-time itself. This warping could produce remarkable and potentially observable effects. For instance, the gravitational influence of a cosmic string might bend and magnify light from distant galaxies, creating unique gravitational lensing patterns that future telescopes and observational instruments could detect. Discovering such lensing effects would provide crucial evidence for the existence of cosmic strings and open new windows into the conditions of the early universe. Furthermore, cosmic strings may have played a crucial role in shaping the large-scale structure of the cosmos. As the universe expanded, these strings could have acted as gravitational seeds, guiding matter to cluster and form galaxies and galaxy clusters. Their presence in the early cosmos might also leave subtle imprints in the cosmic microwave background radiation, the faint afterglow of the Big Bang, which scientists continue to study for clues about the universe's infancy and evolution. In essence, cosmic strings are a bridge between theoretical physics and observational cosmology, linking the mysterious physics of the early universe to the grand cosmic structures we observe today. They remind us that beneath the vastness of space lies a rich and complex tapestry of phenomena still waiting to be understood, a testament to the endless human drive to unravel the universe's most profound secrets. Moreover, cosmic strings stand as one of the most fascinating and mysterious concepts, linking the realms of high-energy physics and cosmology. These hypothetical one-dimensional defects in the fabric of space-time could serve as a critical bridge between the two pillars of modern physics: quantum mechanics, which governs the very small, and general relativity, which explains gravity and the behavior of the universe at the largest scales. By studying cosmic strings, scientists hope to unlock profound insights into the fundamental forces that shaped the early universe, especially during a dramatic phase called inflation, a period of extremely rapid expansion just moments after the Big Bang. Although cosmic strings remain purely theoretical, their study pushes the boundaries of our understanding, inviting researchers to explore the universe's very fabric. They challenge our assumptions about the universe's fundamental building blocks, hinting that reality might be far stranger and more complex than previously imagined. As scientists deepen their investigations into these cosmic anomalies, they may uncover hidden dimensions or new properties of space-time that defy current comprehension. These strings might one day reveal aspects of the cosmos that have remained concealed since the dawn of time. Equally compelling is the concept of a false vacuum in quantum field theory, a state that is metastable, meaning it appears stable but isn't the lowest possible energy configuration. Imagine a landscape where valleys represent different energy states. The false vacuum is like a valley that seems safe but sits higher than the deepest valley, the true vacuum. This false vacuum doesn't spontaneously collapse into the true vacuum, even though doing so would be energetically favorable. The idea that large regions of the universe could be trapped in this false vacuum state opens up astonishing possibilities for cosmology and the overall dynamics of the universe. If such false vacuum regions exist, their presence could drastically influence the behavior of fundamental forces, subtly changing how space-time behaves and how particles interact. These altered conditions might create exotic environments that differ vastly from our familiar universe, potentially harboring forms of matter and energy unlike anything we have ever observed. The existence of false vacuums challenges our understanding of the cosmos' structure and evolution, suggesting that what we see might be only a fraction of a much larger and more diverse reality. One of the most dramatic implications of a false vacuum is its potential to trigger a phase transition, a sudden change in the state of the vacuum. If a region of false vacuum were to decay to the true vacuum, it could create a rapidly expanding bubble of lower energy space. This process, known as vacuum decay, would unleash an enormous release of energy and could transform the surrounding regions of the universe, fundamentally reshaping the fabric of reality itself. Such an event would be catastrophic on a cosmic scale, essentially rewriting the laws of physics within its reach. Interestingly, this vacuum decay mechanism might not be just a speculative threat. It could have played a pivotal role in the early universe. The sudden phase transitions caused by shifts from false to true vacuum states might have driven the rapid expansion of space-time known as inflation. This theory helps explain why the universe appears so uniform and flat on large scales today. By investigating false vacuum dynamics, researchers gain a window into the violent and complex processes that shaped the universe's infancy, illuminating how the cosmos evolved from a chaotic quantum froth to the vast, structured expanse we inhabit now. And so the universe might be far stranger than we ever imagined. Within the realm of high-energy physics and cosmology, scientists are delving into a daring idea, an intricate mosaic known as the cosmic landscape. This isn't a landscape of hills and valleys, but of vacuum states, fundamental configurations of empty space itself. These states aren't all equal. In fact, they may coexist across a universe that's not uniform, but fractured into domains, each governed by different physical rules. Some of these vacuum states could be true vacua, the most stable form of nothingness. Others, false vacua, seemingly stable, but always on the brink of decay. Why does this matter? Because the very structure of reality might hinge on it. If false vacua exist and remain stable long enough, they could influence how matter clumps together, how fundamental forces behave, and even whether life can emerge. This isn't just theoretical whimsy. Ongoing work in quantum field theory and cosmology is building mathematical frameworks that suggest such vacua might not only exist, but shape the fabric of space and time itself. And that brings us to an even more bizarre possibility. Cosmic domain walls. Imagine the early universe as a bubbling cauldron of energy, cooling rapidly after the Big Bang. As it cooled, fields that once obeyed symmetric laws began to choose distinct configurations, a process known as spontaneous symmetry breaking. Just like different regions of a magnet can align in opposite directions, creating invisible walls between them, regions of the universe may have settled into different vacuum states. The result? Boundaries. Walls. Not made of brick or stone, but of energy. These are cosmic domain walls, two-dimensional topological defects that slice through space. These walls are not passive observers. They are active players in the cosmic theater. If they're stable, they can persist across billions of years, influencing how galaxies form, how radiation is distributed, and how the gravitational web of the universe takes shape. In theory, they could trap particles, guide flows of energy, and even impact the cosmic microwave background, the afterglow of the Big Bang itself. But that's not all. The behavior of these domain walls depends entirely on the properties of the scalar fields that formed them. If the underlying fields evolve quickly, the walls may collapse or vanish. If they're governed by stable equations, the walls might stretch across vast intergalactic distances, shaping the universe in ways we've only just begun to comprehend. Detecting their fingerprints, faint distortions in ancient light or gravitational patterns would revolutionize our understanding of cosmic evolution. And yet, even this is only the beginning. Some physicists propose a mind-bending extension to these ideas. What if every black hole in our universe hides something much larger? Something infinite. At the heart of this notion lies a paradox: the black hole information problem. According to general relativity, when a black hole forms, it wraps space and time into a singularity and surrounds it with an event horizon, a point of no return. Not even light can escape its grip. But quantum mechanics doesn't like losing information. So where does that information go? Some theorists suggest that within these black holes, the rules of space and time may warp so completely that a new universe could be born inside. Think of it like a cosmic nesting doll. Each black hole a portal, each singularity a seed for another cosmos. The event horizon becomes not an ending, but a doorway. Inside, the laws of physics might take on entirely new forms. Space might stretch, time might flow differently, and whole galaxies could arise, undetectable to us, yet very real within their own horizons. This idea echoes the concept of wormholes, tunnels through space-time that link distant regions, or even different universes. While we have no empirical proof that wormholes exist, the equations suggest they're possible, at least mathematically. And if black holes are the mouths of such tunnels, then what lies beyond could be another branch of the multiverse, complete with stars, planets, and perhaps even life governed by unfamiliar laws. Each of these theories, from false vacua and domain walls to black hole cosmogenesis, paints a universe that's not only vast, but dynamic and layered. A universe where empty space is not so empty, where cosmic walls divide realities, where death by gravitational collapse might actually be birth, and we, here on our small planet, might just be scratching the surface of a grander architecture, an endless cosmic cathedral filled with rooms we've yet to enter. Moreover, the idea that black holes could contain entire universes within them opens a provocative window into one of the most audacious scientific concepts, the multiverse. At the frontier of cosmological thought, this notion finds a surprising kinship with the theory of cosmic inflation, a period of unimaginably rapid expansion that occurred in the earliest moments following the Big Bang. According to inflationary theory, as the universe ballooned outward, it may have created isolated bubbles of space-time. Each of these bubbles, detached from the others, could evolve into its own separate universe, each with its own laws of physics, its own fundamental constants, and its own cosmic story. Now imagine, if black holes truly harbor such bubble-like domains within their inescapable depths, then every black hole might be a gateway, not just to destruction, as traditionally imagined, but to birth. Each one could cradle a unique, self-contained universe. In this scenario, black holes are not the ultimate dead ends in the cosmos, but instead they might serve as cosmic seeds in a larger, unfathomable structure, a multiverse where every black hole blossoms into a new reality. This idea isn't just science fiction, it sits at the speculative edge of real theoretical physics. And while the concept stirs wonder and invites us to reimagine the nature of existence, it's important to remember that, for now, it remains purely hypothetical. We currently lack direct empirical evidence to confirm that black holes birth new universes. Still, as the boundaries of physics are stretched by new explorations into quantum gravity, loop theory, and string theory, the picture may yet change. One particularly intriguing development in this realm is the Fuzzball theory, a radical reimagining of black holes that arises from the framework of string theory. This theory aims to resolve one of the most persistent puzzles in theoretical physics, the black hole information paradox. For decades, physicists have been grappling with a troubling question: what happens to information that falls into a black hole? In classical models, black holes are thought to contain a singularity, a point of infinite density, shrouded by an event horizon from which nothing, not even light, can escape. In this view, any information swallowed by the black hole is lost forever, violating fundamental principles of quantum mechanics. But fuzzball theory defies that paradigm. It proposes that black holes are not mysterious empty voids dominated by a central singularity. Instead, they are dense, tangled configurations of strings and branes, the fundamental entities of string theory. In this model, a black hole is more like a ball of tightly packed, vibrating strands of energy with no central singularity and no traditional event horizon. According to this vision, the surface of the fuzzball replaces the event horizon. Rather than being a point of no return, this surface is a complex, dynamic boundary where quantum effects dominate. Information, rather than being irretrievably lost, becomes woven into the intricate structure of the fuzzball itself. This would allow information to be preserved, encoded in the geometry of the fuzzball, and possibly even radiated back out via quantum processes. The implications of this theory are nothing short of revolutionary. If true, it could mean that space-time itself is not smooth and continuous as Einstein envisioned, but instead is composed of a fine-grained, interconnected network shaped by the behavior of fundamental strings. The very geometry of reality could be emergent, built from the ground up by quantum processes and the tangled relationships of energy and information. And so, with theories like cosmic inflation and fuzzballs, we stand on the edge of a vast intellectual frontier. We are beginning to glimpse a universe that is more complex, more layered, and more mysterious than anything previously imagined. Black holes, once considered the darkest secrets of the cosmos, may instead be the most illuminating, revealing not only what lies beyond the visible universe, but also what reality itself is made of. As we continue to push the boundaries of understanding, the path forward may demand not just more powerful telescopes or deeper equations, but a willingness to see the cosmos through entirely new eyes. And so begins one of the most extraordinary dialogues in modern theoretical physics, a conversation that challenges the very nature of reality as we perceive it. At the heart of this discussion lies the fuzzball theory, an ambitious proposition emerging from string theory that reimagines black holes not as singular points of infinite density, but as vast conglomerates of strings, fuzzballs, with no definitive interior. Rather than harboring a gravitational abyss, these fuzzballs may instead encode all the information of the matter that formed them across their surface structure. What makes this idea particularly compelling is its alignment with the holographic principle, a radical concept asserting that all the information contained within a three-dimensional volume of space can be fully described by a theory operating solely on its two-dimensional boundary. This principle, born from efforts to unify quantum mechanics and general relativity, suggests that space and gravity themselves might be emergent phenomena, projections from a deeper informational substrate. It's a proposition that stretches our imagination and reveals a universe far more interconnected than our conventional notions of space-time allow. Although fuzzball theory remains a theoretical construct not yet confirmed by empirical data, its implications are staggering. If correct, it offers a solution to the black hole information paradox, one of the greatest unsolved problems in physics, and may ultimately pave the way for a consistent quantum theory of gravity. As research into string theory and quantum gravity evolves, the fuzzball framework could provide fresh insights into the very fabric of the cosmos, inviting us to reconsider what black holes really are and how information is conserved across space-time. This drive to comprehend the cosmos isn't confined to black holes alone. The Anthropic principle presents another captivating perspective, one that shifts the lens from the external universe to the observers within it. At its core, the Anthropic principle explores why the physical laws and constants of the universe appear so finely tuned to permit the existence of conscious life, particularly human life. It confronts us with an unsettling question. Could it be that the universe must have properties compatible with life simply because we are here to observe it? This principle comes in two major forms. The weak anthropic principle suggests that the conditions of the universe we observe must allow for the existence of observers like us. Otherwise, we wouldn't be here to observe them in the first place. The strong anthropic principle, on the other hand, goes further. It proposes that the universe is somehow compelled, or perhaps destined, to develop properties that make life not just possible, but inevitable. These ideas carry profound implications, especially when we examine the apparent fine-tuning of fundamental constants. Take, for example, the gravitational constant, the strength of electromagnetic forces, or the mass of elementary particles. If even one of these values were slightly altered, the consequences would be catastrophic for the development of stars, galaxies, and ultimately life. A slightly weaker strong nuclear force, for instance, would prevent atomic nuclei from binding together, stifling the formation of essential elements like hydrogen and helium. No stars, no chemistry, no life. According to the Anthropic principle, we observe a universe so perfectly calibrated for life because we exist in one of the rare cosmic regions, or possibly one of many universes, where those conditions happen to prevail. This idea dovetails with the concept of a multiverse, an enormous, perhaps infinite, ensemble of universes, each with its own set of physical laws and constants. In this vast cosmic landscape, most universes might be sterile or chaotic, but in a few rare pockets, such as ours, the physical parameters fall just right, allowing stars to shine, planets to form, and conscious beings to ponder their origins. Yet, this principle is not without its critics. Detractors argue that it lacks explanatory power. It doesn't predict why the constants have the values they do. It merely states that we observe them because we can. Some scientists argue that this reasoning skirts the deeper question: why do these constants emerge in the first place? Instead, they advocate for a more fundamental theory, perhaps rooted in quantum gravity or string theory, that could derive these values from first principles. Nonetheless, the Anthropic principle continues to inspire philosophical and scientific reflection. It prompts us to explore the deep link between our existence and the structure of the universe. Why should the cosmos permit life at all? Is this alignment mere coincidence, or does it reflect an underlying necessity? These questions remain central to the search for a deeper understanding of reality. Further compounding this mystery is the tantalizing possibility that the values of fundamental constants may not be uniform throughout the cosmos. Some theories suggest that beyond the edge of our observable universe, beyond what our telescopes and instruments can currently detect, physical constants like the speed of light, the gravitational constant, or the charge of the electron might take on different values. In certain cosmological models, particularly those that include inflation or quantum fluctuation mechanisms, each pocket universe or bubble of the multiverse could emerge with its own unique blend of fundamental forces. Imagine a universe where gravity is 10 times stronger, where atoms bind differently, or where the electromagnetic force is barely perceptible. Such variations would lead to entirely different physical realities, potentially shaping alien galaxies, unfamiliar chemistry, or universes where life, if possible, looks nothing like what we know. This bold idea opens a doorway to an astonishing truth. Our universe might not be the only way reality can manifest. It may simply be one iteration among countless others, each with its own internal logic, structure, and perhaps even forms of life. As we continue to explore these profound questions, one thing becomes increasingly clear. The universe is far stranger, richer, and more complex than our early models ever suggested. From the enigmatic interiors of black holes to the dizzying expanses of the multiverse, we are just beginning to grasp the cosmic symphony of forces and principles that gave rise to our existence. And with each new theory, be it fuzzballs or the anthropic lens, we take one step closer to understanding not just where we are in the universe, but why we are here at all. Moreover, theories on the frontiers of modern physics, particularly string theory, propose something astonishing: that our universe may not be confined to the familiar 3 spatial dimensions and one of time. According to these groundbreaking ideas, additional dimensions may exist, hidden from our perception, curled up in intricate geometries that influence the very fabric of reality. These unseen dimensions could subtly, yet profoundly, shape the physical constants that define the behavior of matter and energy. Imagine a cosmos where gravity isn't a fixed force, but a fluid one, bending differently based on how it moves through unseen spatial folds. In these higher dimensional frameworks, the very laws that govern particles, atoms, and galaxies might differ from one region to another. The interactions between matter and these extra dimensions could give rise to entirely new physical realities, each governed by its own distinct set of rules. The implications are profound. Instead of a single universal law book, there could be countless variations. If fundamental constants like the strength of the electromagnetic force or the ratio of electron to proton mass were even slightly different, the universe we know might never have existed. A slight deviation might prevent atoms from forming, eliminate the possibility of stable stars, or even render chemistry as we know it impossible. Yet, in a universe where those constants differ in just the right ways, life might arise in a completely alien form. Silicon-based organisms, floating plasma intelligences, or even physics itself unfolding in ways we cannot yet imagine, these are the possibilities when the constants shift. This speculative yet captivating notion leads us to one of the most thought-provoking ideas in theoretical physics: the multiverse. According to this concept, our universe might be just one among countless others, an infinitesimal part of a vast cosmic ensemble. Emerging from interpretations of quantum mechanics, cosmic inflation, and string theory, the multiverse suggests that universes are constantly being created, each with its own unique set of physical laws. Mechanisms like quantum fluctuations or the inflationary expansion of space could generate an eternal cascade of bubble-like universes, each governed by a distinct configuration of constants and dimensions. In this scenario, our universe appears finely tuned for life, not because of divine calibration or sheer coincidence, but because we exist in one of the few universes where such conditions happen to support observers like us. It's a form of cosmic natural selection. With so many universes out there, it is statistically inevitable that at least one would have the right mix of forces, particles, and energies to allow stars, planets, and biological life to flourish. In universes where gravity is too strong or the nuclear force too weak, stars might never ignite, or atoms might fall apart before molecules could form. The multiverse then provides a compelling response to the fine-tuning problem. Rather than requiring a singular explanation for why our universe has the precise values it does, this framework proposes that we are simply inhabiting the version where everything works, where the constants align just right. In an eternally expanding cosmic landscape, with universes emerging like bubbles in a never-ending sea, the probability of one like ours increases dramatically. It's not a miracle, it's a statistical certainty born from immense cosmic diversity. However, not everyone is convinced. The multiverse theory, while elegant and intellectually satisfying, confronts a daunting challenge: empirical testability. By its nature, it proposes the existence of realms beyond our observational horizon, regions of space and reality we may never access or detect. Critics argue that if these other universes can never be observed, measured, or influenced, then they reside outside the realm of traditional science. Are we describing reality or engaging in metaphysical speculation? This question continues to stir deep debate among physicists, cosmologists, and philosophers alike. Yet, the pursuit of such ideas reflects humanity's relentless drive to understand the cosmos, not merely as it appears, but as it might be. As our tools grow sharper and our theories more refined, we edge ever closer to the limits of what we can know. The notion that we are just one thread in a much larger cosmic tapestry invites both wonder and humility. Whether or not we ever prove the existence of other universes, the multiverse serves as a powerful reminder that reality might be far more vast, strange, and beautiful than anything we've yet imagined. Furthermore, it raises profound questions about the hidden mechanisms shaping our universe, especially the diversity of fundamental constants and the deeper implications these variations might have for the very nature of reality. As research in cosmology and theoretical physics advances, the multiverse concept emerges not just as a speculative idea, but as a compelling framework that invites us to reimagine existence itself. The notion that countless universes may exist, each governed by its own unique set of physical laws and constants, challenges our assumptions about what is necessary for a universe to function, or even to support life. While this conversation remains largely theoretical, the implications are nothing short of cosmic in scale. It forces us to question whether the parameters that define our universe are uniquely suited for life, or whether they represent just one of many viable configurations among an unimaginable cosmic ensemble. If the fundamental constants of our universe, those critical values like the gravitational constant, the speed of light, and the strengths of fundamental forces, were even slightly different, the consequences would be profound. These constants aren't arbitrary. They serve as the cosmic blueprint for how matter, energy, and the fabric of space-time behave. A mere shift in their values could alter everything from the structure of atoms to the fate of galaxies. Take, for instance, the gravitational constant. If gravity were even modestly stronger, stars would become far larger and burn through their nuclear fuel at accelerated rates, leading to shorter stellar lifespans. Planets might become denser under stronger gravitational pressure, and stable planetary orbits, necessary for life as we know it, could become rare or non-existent. The universe might then be populated by massive, short-lived stars, flickering out before they could incubate life-bearing worlds. On the other hand, if gravity were weaker, the story changes entirely. Stars might fail to ignite the fusion reactions necessary for their stability, resulting in a universe filled with dim, cool stars, or perhaps no stars at all. Galaxies, which rely on gravity to coalesce and bind their constituent stars, might never form, leaving a cosmos scattered and structurally chaotic. The delicate balance needed to create complex systems, from solar systems to life itself, would be lost. The electromagnetic force also plays a vital role in this cosmic balance. If it were stronger, electrons would cling more tightly to atomic nuclei, making chemical reactions less dynamic and potentially limiting the diversity of molecules. If it were weaker, atoms might fail to hold together at all, unraveling the chemical foundations required for life. Complex chemistry, so vital for DNA, proteins, and the mechanisms of biology, could become impossible. Other constants, such as the masses of elementary particles, further demonstrate this fine-tuning. Alterations here could disrupt the stability of atomic nuclei, prevent the formation of key elements like carbon or oxygen, and render processes like stellar nucleosynthesis, the forging of elements within stars, non-viable. In such universes, the periodic table might look unrecognizable or be devoid of elements crucial for the chemistry of life. In essence, the universe we inhabit appears to be precariously balanced. These constants must fall within incredibly narrow ranges for stars to shine, for planets to form, and for life to arise. If even one of them were nudged too far in either direction, the universe might remain lifeless, dark, and inert. Yet this delicate equilibrium also opens a window to astonishing possibilities. Could there be other universes where different constants prevail, yet complex structures or even life still emerge? Theoretical physics suggests that life, or something akin to it, might not require the same rules we know. If the fundamental forces were drastically different, alternative forms of order and complexity could still arise. Imagine a universe with significantly weaker gravity. While such a universe might lack massive stars, it could foster countless smaller ones, each nurturing unique chemical environments. Or consider a reality where different atomic interactions produce entirely new chemistries, perhaps not reliant on carbon, but on silicon or even stranger elements. Such chemistries could give rise to life forms adapted to exotic conditions, life not based on water, but on ammonia, methane, or even plasma. Some scientists speculate further, imagining universes governed by mathematical laws entirely foreign to our own. In such realities, life might not be biological at all, but could emerge from radically different patterns of organization. Perhaps intelligence could arise within fields of energy or as stable information patterns embedded in quantum structures, entities that simulate life, but on a canvas alien to our biology. These speculative scenarios challenge the notion that our universe is the only possible setting for complexity. They suggest that life, broadly defined, could emerge in countless ways, under countless rules, and they compel us to look beyond our own cosmos, not just in space, but in concept. The multiverse, with all its myriad possibilities, may be more than an abstract theory. It may be the key to understanding not just why we exist, but how existence itself can take form across the infinite tapestry of realities. However, the challenge in discussing universes governed by vastly different fundamental laws begins with the profound limitations of the human mind itself. Our ability to predict, imagine, or even grasp such alien frameworks is severely constrained by our own universe's familiar patterns. The very fabric of life as we know it, our biology, chemistry, physics, is inextricably woven into the unique tapestry of constants and forces that define our cosmos. Gravity, electromagnetism, the speed of light, and quantum mechanics are not just abstract concepts. They are the invisible scaffolding that supports our entire existence. Alter just one of these constants and the world we know might unravel into something unrecognizable. To contemplate life under an entirely different set of physical rules is to step into the unknown. Could consciousness arise in a universe where time flows in reverse? Could matter cohere where gravity repels instead of attracts? These are not just thought experiments. They are invitations to stretch the limits of human inquiry. Yet any attempt to model or envision life in such realms inevitably circles back to our own biases. We imagine extraterrestrial beings with arms, eyes, and minds, but this could be as naive as a deep-sea fish trying to picture a bird. Our imaginations, brilliant as they are, remain tethered to what we know. Still, despite the barriers, the mere consideration of such alternative universes serves a vital purpose. It expands the scope of science and philosophy alike, challenging us to break free from anthropocentric thinking. This line of inquiry asks us to be humble in the face of the unknown and to entertain the possibility that existence itself may be far broader and stranger than we have dared to believe. Perhaps there are realms where life takes forms we cannot name, where intelligence dances to rhythms outside our mathematics, where structures and systems function by laws we've never conceived. In asking, what if, we aren't just toying with speculation. We are peering into a mirror that reflects the limitations of our understanding. The multiverse, if it exists, could be teeming with an unimaginable variety of realities, each with its own laws, logics, and perhaps even lives. These universes, whether forever beyond our reach or awaiting future discovery, remind us that the journey of exploration isn't only about telescopes or spacecraft. It's also about expanding the frontiers of thought itself. And in that sense, the unknown becomes a kind of compass. It points not just to new places, but to new ways of thinking, new ways of being. The question isn't simply whether life can exist under different laws. It's whether we can ever truly understand what life means outside the narrow confines of our own cosmic home.